Hello everyone, this is Saurabh from EduReka. Welcome everyone to today's session on what is deep learning. We'll understand how deep learning emerged. That is, what were the limitations of the previous technologies that led to the evolution of deep learning. So let us have a look at the agenda for today. First, we'll understand what is artificial intelligence and what exactly is machine learning. Then we'll look at various limitations of machine learning and how deep learning solves or overcame those limitations. After that, we'll understand what exactly is deep learning, and we'll also look at various applications of deep learning. So let us move forward and understand artificial intelligence. But the first thing that we need to focus on is why artificial intelligence? Why do we need artificial intelligence? Now let us understand this with an example. So nowadays, if you have noticed, if your car exceeds the speed limit, so you'll get a letter or basically a challan at your home. How do you think that happens? Do you think that there's a person who is sitting in a chair and actually noting down all the number plates that crosses the speed limit? Well, that is not possible because there might be millions of cars that pass through that road. And at once there might be many cars that will be passing through that road. So for a human being to actually do this task is next to impossible. Now let us see another approach to this particular problem. So what we can do, we can actually make use of cameras that will click the picture of the car that exceeds the speed limit, and then we can convert that picture into a text. For example, we have a UKPLATE. So in this way, the risk of human error has been reduced, and at the same time, machines, they never get tired. So because of that, you can capture all the images of cars that actually crosses the speed limit. Similarly, you can think of many other examples as well. It is used in order to recognize a sign, that is in banks if you want to authenticate whether that person is the bank customer or not. Apart from that, it is even used for self-driving cars as well. So in US, around 30,000 people die every year because of road accidents. So that can be completely removed if we use the self-driving cars, which is based on the concept of artificial intelligence. And let me tell you guys, you might find it very fascinating that people in MIT are using artificial intelligence in order to predict the future. So you can imagine why we need artificial intelligence. It is even used in places where humans can't reach. For example, deep oceans or navigation in Mars. So in those places, we need machines which are smart enough to carry our tasks. So this is why we need artificial intelligence. Let us move forward and understand what exactly is artificial intelligence. Now, artificial intelligence, I know the word sounds pretty complex, and there are a lot of Hollywood movies that are based on artificial intelligence. If you have seen Terminator or Matrix, so all these movies are based on artificial intelligence, but you don't need to worry about it because till now we haven't reached that level as they have shown in movies like Terminator. But yeah, the concept is pretty similar. So basically, we want systems and softwares in such a way that they can imitate the human behavior. Now, what happens in artificial intelligence? Artificial intelligence is accomplished by studying how human brain thinks and how human brain learns, decide and work while trying to solve a problem. And then we use the outcome of this study as the basis of development of intelligent software and systems. So our major goal is to have systems or softwares that can imitate the human behavior. The way they think, the way they decide, the way they solve a problem. So in that similar fashion, we want our machines to do that. So this is basically artificial intelligence in a nutshell. Let us move forward and look at various applications of artificial intelligence. So this slide basically talks about the application of artificial intelligence. Now I've listed only 3 of them, but there are millions of applications. For example, it is used in speech recognition. So whenever you search something on Google, so you can just tell Google and it will search it for you. Similarly, it is used for understanding natural language as well as for image recognition as well. And there are many other applications in which artificial intelligence finds its use. For example, it can be used in self-driving cars, it can be used in Siri for recommending some products, and even when you go to websites like YouTube or Pandora, YouTube knows which video you want to next. Pandora knows which song you want to listen to. How do you think this happens? It happens all because of artificial intelligence. So all of these are a few examples of artificial intelligence, but nowadays it is used almost everywhere, guys. Trust me on that. Now let us move forward and understand how to achieve artificial intelligence. Now in order to achieve artificial intelligence, there were a few technologies that came. First came machine learning. Now there were certain limitations of machine learning. In order to overcome those limitations came deep learning. Now let me tell you guys, the concept of artificial intelligence is not new. It was first coined in 1956, but it was just a theoretical concept. Then in 80s and 90s, we were talking about neural networks. But since we didn't have enough computational power, so we couldn't utilize it properly. But in late 90s and 2000s, we started using neural networks for machine learning. Then in 2006, the term deep learning was coined for the first time that overcame the limitations of machine learning. And from 2010, deep learning was used commercially as well. So this was just a small history about artificial intelligence, machine learning, and deep learning. Now, in order to understand this deep learning, we need to first look at machine learning and what were the various limitations of machine learning that led to the evolution of deep learning. So we'll move forward and understand what exactly is machine learning. Now, what is machine learning? So machine learning is nothing but a type of artificial intelligence, or you can say a subset of artificial intelligence. And it provides computers with the ability to learn without being explicitly programmed. So you don't need to hard code your machine for that. Let us understand this with an example. So we have a problem statement in which whenever you give a certain input, we need to determine the species of the flower. And what is that input? That input will be sepal length, sepal width, petal length, and petal width. So whenever we get these four parameters or these four variables, our machine should be able to predict what sort of a flower it is. Now, how do you think that will happen? First, what we need to do, we need to train our machine on the basis of the data that we have. So in this data, we have sepal length, sepal width, petal length, and petal width, and we have species. So our machine will learn from this data. It will determine what should be the length and width of the sepal and petal in order to classify it as setosa or versicolor or other species of flowers as well. Now what happens next? So you have trained your data. So you have trained your machine from the data set. Then what happens whenever you give a new input to this particular machine, it will predict the species of the flower. So this is how machine learning works. It is nothing but machine learning in a nutshell. So basically, I'll just revise it once more. So you have a data set. So you split that data into training and testing data. So what happens with the help of training data, you train your particular machine. And after that, you test it in order to determine the accuracy. And once it is done, whenever you give the new input, it'll predict the outcome or the desired outcome. So this is how machine learning works, guys. Let us move forward and understand various types of machine learning. So the first type is called supervised learning. Now in supervised learning, what happens, you have input variables X and an output variable Y. And you can use an algorithm to learn mapping function from the input to the output. Now let me simplify it for you. So what happens in supervised learning, the data that you have already contain the classification. Now let me talk about the previous example itself. So from our data set, we knew that if we have this width, this length of our sepal and petal, so that will be the species of flower. So the classifications are already defined. So that will be under supervised learning. Now let me tell you how it actually works. So you have data, you divide that data into training data as well as test data. So on the basis of this training data, you train your machine, and after that you create a model. So as you can see that this phase is called training phase, and after that you create a model. Now in order to check this model to get the accuracy, you have test data. So you'll pass that test data and you'll see the accuracy. That is nothing but the actual output minus the output that is present in the test data. So with that you can get the accuracy. So this is all about supervised learning. So we'll move forward and understand unsupervised learning. Now in unsupervised learning, unlike supervised learning, you don't have any predefined classes. So what happens, you have data. So on the basis of that data, you try to create your own class. You try to make sure that whatever class you create has high intra-class similarities and have low inter-class similarities. That means if I've created two classes like this, class 1 and class 2, so the elements of this particular class should have high similarity, but at the same time, it should have low similarity with the elements of class 2. So you can think of examples as well of unsupervised learning. For example, if I have a data about my customers, so if I have a website and there are millions of visitors on my website, and I want to make sure that I group people on various criteria. For example, I can group people on the basis of willingness to purchase a product that is there on my website, or where they are coming from, what is the source, all those things. So I want to group my customers, and I want to make sure that I have certain high priority customers and I have low priority customers and I have medium priority customers. So with the help of unsupervised learning, I can actually do that. I can make certain classes of people on whom I should focus more on as compared to the other class. So this was just an example, guys. You can use it in various other fields as well. So in marketing, this is how you can use unsupervised learning. So this brings us to our next type of machine learning, which is called reinforcement learning. Now this is reinforcement learning, guys. Now what happens in reinforcement learning? The machine learns by interacting with space or an environment. So it learns with its experience, with its past experience, and also by new choice exploration. Now I'll take the analogy of dogs. So if you have any dog or a pet at your home, so if you have trained your dog in order to get the newspaper, and if it gets it, then you reward it with some chocolate or things that the dog likes, right? So the dog will know whatever he has done, he's actually rewarded for that. So it'll continue doing that. But apart from that, if he does something else, if instead of the newspaper, he brings something else. So what you'll do, you might even punish it. So because of that, the dog will come to know that it has to get a newspaper every morning. Now, the same example is there in front of your screen. So you have this machine. So it has two choices, either to touch the fire or touch the water. Now, first, what it does, it goes on and touch the fire. So because of that, it gets some burning sensation. Now it has only other option, that is to touch the water. So when it touches the water, it gets some reward. So because of that, it'll understand that it does not have to touch fire ever again. Now there's a diagram that is there in front of your screen. So what happens is you have an agent, all right, that agent performs some action. And on the basis of that action, it'll be exposed to some sort of an environment. Now if that action is correct, then it'll be rewarded with that. But if it is not, then it'll change its choice and it'll again perform some action. So this process will keep on repeating. So this is how reinforcement learning works. So let us move forward and understand when we have machine learning, why do we need deep learning? That is, we'll look at various limitations of machine learning. Now the first limitation is high dimensionality of the data. Now the data that is now generated is huge in size. So we have a very large number of inputs and outputs. So due to that, machine learning algorithms fail. So they cannot deal with high dimensionality of data, or you can say data with large number of inputs and outputs. Now there's another problem as well in which it is unable to solve the crucial AI problems, which can be natural language processing, image recognition, and things like that. Now one of the biggest challenges with machine learning models is feature extraction. Now let me tell you what are features. So in statistics, we consider features as variables, but when we talk about artificial intelligence, these variables are nothing but the features. Now, what happens because of that? The complex problems such as object recognition or handwriting recognition becomes a huge challenge for machine learning algorithms to solve. Now, let me give you an example of this feature extraction. Suppose if you want to predict that whether there will be a match today or not. So it depends on various features. It depends on whether the weather is sunny, whether it is windy, all those things. So we have provided all those features in our data set. But we have forgot one particular feature, that is humidity. And now our machine learning models are not that efficient that they will automatically generate that particular feature. So this is one huge problem, or you can say limitation with machine learning. Now obviously we have limitation, and it won't be fair that if I don't give you the solution to this particular problem. So we'll move forward and understand how deep learning solves these kind of problems. Now, as you can see that the first line on your slide, which says that deep learning models are capable to focus on the right features by themselves, requiring little guidance from the programmer. So with the help of little guidance, what these deep learning models can do, they can generate their features on which the outcome will depend on. And at the same time, it also solves the dimensionality problem as well. If you have a very large number of inputs and outputs, you can make use of a deep learning algorithm. Now, what exactly is deep learning? Again, since we know that it has been evolved by machine learning, and machine learning is nothing but a subset of artificial intelligence, and the idea behind artificial intelligence is to imitate the human behavior. The same idea is for the deep learning as well, is to build learning algorithms that can mimic brain. Now let us move forward and understand deep learning, what exactly it is. Now the deep learning is implemented with the help of neural networks, and the idea or the motivation behind neural networks are nothing but neurons. What are neurons? These are nothing but your brain cells. Now here's a diagram of neuron. So we have dendrites here which are used to provide input to our neuron. As you can see, we have multiple dendrites here, so these many inputs will be provided to our neuron. Now this is called cell body, and inside the cell body we have a nucleus which performs some function. After that, that output will travel through axon, and it will go towards the axon terminals, and then this neuron will fire this output towards the next neuron. Now the studies tell us that the next neuron, now, or you can say the two neurons are never connected to each other. There's a gap between them. So that is called a synapse. So this is how basically a neuron works like. And on the right hand side of your slide, you can see an artificial neuron. Now let me explain you that. So over here, similar to neurons, we have multiple inputs. Now these inputs will be provided to a processing element like our cell body. And over here in the processing element, what will happen? Summation of your inputs and weights. Now, when it moves on, then what will happen? This input will be multiplied with our weights. So in the beginning, what happens? These weights are randomly assigned. So what will happen if I take the example of x1? So x1 multiplied by w1 will go towards the processing element. Similarly, x2 and W2 will go towards the processing element, and similarly the other inputs as well. And then summation will happen, which will generate a function of S, that is f of S. After that comes the concept of activation function. Now what is activation function? It is nothing but in order to provide a threshold. So if your output is above the threshold, then only this neuron will fire, otherwise it won't fire. So you can use a step function as an activation function, or you can even use a sigmoid function as your activation function. So this is how an artificial neuron looks like. So a network will be multiple neurons which are connected to each other will form an artificial neural network. And this activation function can be a sigmoid function or a step function. That totally depends on your requirement. Now once it exceeds the threshold, it will fire. After that, what will happen? It will check the output. Now if this output is not equal to the desired output, so these are the actual outputs and we know the real outputs. So we'll compare both of that and we'll find the difference between the actual output and the desired output. On the basis of that difference, we are again going to update our weights. And this process will keep on repeating until we get the desired output as our actual output. Now this process of updating weight is nothing but your backpropagation method. So this is neural networks in a nutshell. So we'll move forward and understand what are deep networks. So basically deep learning is implemented by the help of deep networks, and deep networks are nothing but neural networks with multiple hidden layers. Now what are hidden layers? Let me explain you that. So you have inputs that comes here. This will be your input layer. After that, some process happens and it'll go to the next node, or you can say to the hidden layer nodes. So this is nothing but your hidden layer 1. So every node is interconnected if you can notice. After that, you have one more hidden layer where some function will happen. And as you can see that again, these nodes are interconnected to each other. After this hidden layer 2 comes the output layer. And this output layer, again, we are going to check the output, whether it is equal to the desired output or not. If it is not, we are again going to update the weights. So this is how a deep network looks like. Now there can be multiple hidden layers. There can be hundreds of hidden layers as well. But when we talk about machine learning, that was not the case. We were not able to process multiple hidden layers when we talk about machine learning. So because of deep learning, we have multiple hidden layers at once. Now let us understand this with an example. So we'll take an image which has 4 pixels. So if you can notice, we have 4 pixels here, among which the top 2 pixels are bright, that is, they are black in color, whereas the bottom 2 pixels are white. Now what happens? We'll divide these pixels and we'll send these pixels to each and every node. So for that we need 4 nodes. So this particular pixel will go to this node, it will go to this node, this pixel will go to this node, and finally this pixel will go to this particular node that I'm highlighting with my cursor. Now what happens? We provide them random weights. So these white lines actually represent the positive weights and these black lines represents the negative weights. Now this particular brightness, when we display high brightness, we'll consider it as negative. Now what happens? When you see the next output or the next hidden layer, it will be provided with the input with this particular layer. So this will provide an input with positive weight to this particular node, and the second input will come from this particular node. Since both of them are positive, so we'll get this kind of a node. Similarly, this node as well. Now when I talk about these two nodes, the first node over here, so this is getting input from this node as well as from this node. Now over here we have a negative weight. So because of that, the value will be negative, and we have represented that with black color. Similarly, over here as well, we are getting one input from here which has a negative weight, and the another input from here which again has a negative weight. So accordingly, we get again a negative value here. So these two becomes black in color. Now if we notice what will happen next, we'll provide one input here which will be negative and a positive weight, which will be again negative, and this will be also negative and a positive weight. So that will again come out to be negative. So that is why we have got this kind of a structure. If you notice, this is nothing but the inverse of this particular image. When I talk about this node over here, we are getting the negative value with a positive weight which is negative, and a negative value with a negative weight which is positive. So we are getting something which is positive here. Now obviously I want this particular image to get inverse. I want these black strips to come up. So what I'll do, I'll actually calculate the inverse by providing a negative weight like this. So over here I've provided a negative weight, it will come up. So when I provide a positive weight, so it'll stay wherever it is. After that it'll detect, and the output you can see will be a horizontal image, not a solid, not a vertical, not a diagonal, but a horizontal. And after that we are going to calculate the difference between the actual output and the desired output, and we are going to update the weights accordingly. Now this is just an example, guys. So guys, this is one example of deep learning where what happens, we have images here. We provide these raw data to the first layer, to the input layer. Then what happens, these input layers will determine the patterns of local contrast, or it will fixate those patterns of local contrast, which means that it will differentiate on the basis of colors and luminosity and all those things. So it will differentiate those things. And after that, in the following layer, what will happen? It will determine the face features. It will fixate those face features. So it will form nose, eyes, ears, all those things. Then what will happen? It will accumulate those correct features for the correct face, or you can say that it will fixate those features on the correct face template. So it will actually determine the faces here, as you can see it over here. And then it will be sent to the output layer. Now, basically, you can add more hidden layers to solve more complex problems. For example, if I want to find out a particular kind of face, for example, a face which has large eyes or which has light complexion, so I can do that by adding more hidden layers. And I can increase the complexity also at the same time if I want to find which image contains a dog. So for that also I can have one more hidden layer. So as and when hidden layer increases, we are able to solve more and more complex problems. So this is just a general overview of how a deep network looks like. So we have first patterns of local contrast in the first layer. Then what happens? We fixate these patterns of local contrast in order to form the face features such as eyes, nose, ears, etc. And then we accumulate these features for the correct face, and then we determine the image. So this is how a deep learning network, or you can say deep network, looks like. And I'll give you some applications of deep learning. So here are a few applications of deep learning. It can be used in self-driving cars. So you must have heard about self-driving cars. So what happens? It'll capture the images around it. It'll process that huge amount of data, and then it'll decide what action should it take. Should it take left, right? Should it stop? So accordingly, it'll decide what action should it take. And that will reduce the amount of accidents that happens every year. Then when we talk about voice control assistants, I'm pretty sure you must have heard about Siri. All the iPhone users know about Siri, right? So you can tell Siri whatever you want to do. It'll search it for you and display for you. Then when we talk about automatic image caption generation, so what happens in this, whatever image that you upload, the algorithm is in such a way that it will generate the caption accordingly. So for example, if you have, say, blue colored eyes, so it will display a blue colored eye caption at the bottom of the image. Now, when I talk about automatic machine translation, so we can convert English language into Spanish, similarly Spanish to French. So basically, automatic machine translation, you can convert one language to another language with the help of deep learning. And these are just few examples, guys. There are many, many other examples of deep learning. It can be used in game playing. It can be used in many other things. And let me tell you one very fascinating thing that I've told you in the beginning as well. With the help of deep learning, MIT is trying to predict future. So yeah, I know it is growing exponentially right now, guys. Welcome to today's session on deep learning tutorial with TensorFlow. So let us move forward and have a look at the agenda for today. So this is the agenda for today, guys. We'll understand what exactly is deep learning and how it works. So we'll look at the motivation behind deep learning and how it actually evolved. Then we'll focus on single layer perceptron, which are nothing but the early deep learning models. We'll also look at various examples of single layer perceptron. And guys, when I talk about perceptron, these are nothing but the artificial neurons. And what are neurons? Neurons are your brain cells. Then we'll also understand the limitations of single layer perceptron that led to the evolution of multilayer perceptron. We'll understand how multilayer perceptron overcame those limitations, and we'll also look at various examples of multilayer perceptron. Fine, guys, let us move forward and understand what all things we have understood so far. So guys, these are the things that we have studied in the previous session. We first understood why artificial intelligence, what is the need of artificial intelligence. Then we saw what exactly it is, and we also focused on various subsets of artificial intelligence, that is machine learning and deep learning. Then we understood how we came from machine learning to deep learning, and we saw what exactly is deep learning along with various applications of deep learning. So guys, we'll move forward now and understand what exactly is deep learning and how it works. So guys, let us understand deep learning with an analogy. So how do you think our brain is able to identify the difference between a dog and a cat? So the reason is, since the day we are born, we are actually seeing different types of cats and dogs in our day-to-day life. And because of that, we are able to identify the difference or spot the difference between the two, that is dog and a cat. Even if we see different types of cats and dogs, we still know which is a cat and which is a dog. So this is because we have seen a lot of cats and dogs in our entire life. But what if I want a machine to do that task for me? So how will a machine identify whether the given image is of a dog or a cat? So one way of doing that is we can train our machine to a lot of images of different cats and dogs, that is different breeds of cats and dogs. And then what will happen once our training is done, we can provide it with an input image. Then we'll manually extract certain features. Features like nose, whiskers, colors, edges, it can be anything. The important features which actually helps us in classifying whether the input image is a cat or a dog. Then we make a machine learning model with that. And once it is done, our machine learning model is able to predict whether the input image is of a cat or a dog. But if you notice here, one very big disadvantage with this is we have to manually extract features. Features such as nose, whiskers, all those features we have to manually extract it and provide it to our machine learning model. And trust me guys, in every scenario it is not possible. If you have large number of inputs, you cannot do that. You cannot manually extract the features, or basically you can say columns which are important for you in order to predict what the object is, right? And that led to the evolution of deep learning. So what happens in deep learning? We skip the manual step of feature extraction. So what we do, we directly take the input image and feed it to our deep learning algorithm. And because of that, what happens, whatever features are we already manually provided, apart from that, there might be many other features which are important. For example, if our features don't include the length of the neck, and that is one of the major features in order to identify or classify whether it is a cat or a dog. Now what will happen, our algorithm will automatically determine that feature and will take into consideration, and then it will classify whether the input image is a cat or a dog. So what happens here, we provide an input image of a dog, and then it will automatically learn certain features even if we don't provide it with those features. And after that, it will give us the probability, and according to this particular scenario, it says 95% chances of being a dog, 3% chances of some other animal, similarly 2% chances of some other animal. So since the highest probability goes with the dog, so the prediction says that the object or the input image is nothing but a dog. Fine guys, so we'll move forward and we'll understand how exactly deep learning works. So the motivation behind deep learning is nothing but the human brain. As we have seen in the previous analogy as well, what we are trying to do, we are trying to mimic the human brain. We are trying to mimic the way we think, the way we take decisions, the way we solve problems. We are trying to make sure that we have a system that can mimic our own brain. So obviously the motivation for deep learning has to be our brain, and how our brain works with the help of our brain cells, which we call neuron. Now let us understand how a neuron works, and let me tell you guys, this is what we think how a neuron works. This is what our studies tell us. So yeah, so these are called dendrites. So dendrites receive signals from other neurons, and then it passes those signals to the cell body. Now this cell body is where we perform certain function. It can be a sigma function. That's what we believe. We believe it performs a sigma function. That is nothing but sums all the inputs. Then through axon, what happens? These signals are fired to the next neuron. And the next neuron is present at some distance, and that distance is nothing but synapse. So it fires only when the signals coming from the cell body exceeds a particular limit. Then only the cell or this neuron will fire the signals to the next neuron. And this is how the neuron or the brain cell works. And we take the same process forward and we try to create artificial neurons. So let us understand why we need artificial neurons with an example. So I have a data set of flowers, say, and that data set includes sepal length, sepal width, petal length, and petal width. Now what I want to do, I want to classify the type of flower on the basis of this data set. Now there are two options. Either I can do it manually. I can look at the flower manually and determine by its color or any means, and I can identify what sort of a flower it is. Or I can train a machine to do that. Now let me tell you the problem with doing this process manually. First of all, there might be millions of inputs that will be given to you. And for a human brain to perform that particular task is next to impossible. And at the same time, we always get tired at some point of time, right? So we cannot just continue working for a long period of time in single stretch. And the third point is human error risk, which is always there. So these are a few limitations with the human brain. So what we can do, we can train a machine to do that task for us, or we can put our brain inside a machine so that it can classify the flowers for us. So with this, what will happen? The machine will never get tired and it will make better predictions as well. So this is why we create artificial neurons, so that there's a system present that can mimic our brain. And this is what exactly happens. So this particular artificial neuron can actually classify the flowers, or you can say can divide the flowers on the basis of certain features. In our case, it is sepal length, sepal width, petal length, and petal width. So on that basis, it can classify the two flowers. So what we need here, we need some sort of a system that can actually separate the two species. And what is that system is nothing but an artificial neuron. So we need artificial neuron, and one type of artificial neuron is a perceptron. Now let me explain you perceptron with the flow diagram that is there in front of your screen. Now over here what happens, we have set of inputs like x1, x2, dash, dash, dash till xn. Now these inputs will be multiplied with their corresponding weights, which is W1, W2, W3 till Wn in our case. Now these weights actually define how important our input is. So if the value of weight is high, we know that this particular input is very, very important for us. After multiplication, all of these are summed together and then it is fed to an activation function. Now the reason of using activation function is to provide a threshold value. So if our signal is above that threshold value, our neuron, or you can say our perceptron, will fire, else it won't fire. So that is the reason why we use an activation function. There can be different types of activation function. There can be sigmoid, there can be step function, sine function. Depending on our use case, we define the activation function. Now the main idea was to define an algorithm in order to learn the values of the weights, which are W1, W2, W3 in our case, to learn the values of the weights that are then multiplied with the input features in order to make a decision whether a neuron fires or not. In context of pattern classification, which is in our case flowers, so we are trying to classify the two species of flowers, such an algorithm could be useful to determine if a sample belongs to one class or one type of a species or another class or another type of the flower. We can even call perceptron as a single layer binary linear classifier to be more specific, because it is able to classify inputs which are linearly separable. And our main task here is to predict to which of the two possible categories a certain data point belongs based on a set of input variables. Now there's an algorithm on which it works, so let me explain you that. So the first thing we do is we initialize the weights and the threshold. Now these weights can actually be a small number or a random number, and it can even be 0. So it depends on the use case that we have. Then what we do, we provide the input and then we calculate the output. Now when we are training our model or we are training our artificial neuron, we have the output values for a particular set of inputs. So we know the output value. But what we do, we give the input and we see what will be the output of our particular neuron. And accordingly, we need to update the weights in order to reduce the loss, or you can say in order to reduce the difference between the actual output and the desired output. So what happens, let me tell you that. So we need to update the weights. So how we are going to update the weights is, we can say the new weight is equal to the old weight plus the learning rate. Learning rate, we'll discuss about it later in the session. But generally we choose learning rate somewhere between 0.5 to 0.01. After that, what happens, we find the difference between the desired output and the actual output. And then we multiply it with the input. So on that basis, we get a new weight. So this is how we update the weights. And then what happens, we repeat the steps 2 and 3. So we are going to repeat the steps 2 and 3. That is, we are going to apply this new weight. Again, we are going to calculate the output. Again, we are going to compare it with the desired output. And if it matches, then it's fine. Otherwise, we are going to update it again. So this is how the whole perceptron learning algorithm works. And don't worry guys, I'm going to show it to you practically how it actually works in my PyCharm. Fine guys, so we'll move forward and we'll see the various types of activation functions. So these are the various types of activation functions that we use, although there can be many more activation functions. Again, I'm telling you, it depends on your use case. So we have a step function. So if our output is actually above this particular value, then only our neuron will fire, or you can say the output will be +1. Or if it's less than this particular value, then we'll have no output, or we'll say 0 output. Similarly for the sigmoid function as well, and same goes for sine function. So let us move forward and we'll focus on various applications of this perceptron. Now, as I've told you earlier as well, it can be used to classify any linearly separable set of inputs. Now, let me explain to you with the diagram that is there in front of your screen. So we have different types of dogs and we have horses, and we want a line that can separate these two. So our first iteration will produce this sort of a line. But here we can notice that we have error here. As we have classified one of the horses as a dog and a dog as a horse. So error is 2 here. Similarly, what happens, we have updated the weights. Now after updating the weight, what happens, our error has reduced. So what happens now, we have actually classified all the horses correctly, but one dog we have classified wrong and we have considered it as a horse. So our error becomes 1. Once again, what will happen, if you can remember, the step 2 and 3 of our perceptron learning algorithm will be done. And then after that, our weights will be updated and our desired output will become equal to our actual output, and we get a line something like this. So what we have now, we have properly classified dogs and horses. So this line separates both of them. This is how we can actually use a single layer perceptron in order to classify any linearly separable set of inputs. Now we can even use it in order to implement a logic gates, that is OR and AND. Now let me tell you how you can do that. First we'll look at OR gate. Now in OR gate, what happens here is the truth table. Truth table, according to that, we have two inputs, x1 and x2. So if both are 0, we get a 0. If any one of the input is high or any one of the input is 1, we get the output as 1. So what we need to do is we need to make sure that our weights are present in such a way that we get the same output. So how we have done that, when the value of weight is equal to 1, and then we provide the input x1 and x2, after passing through this activation function, we get this sort of a graph, which is the graph for our OR gate. Now, if you want, I could use a pen and I can explain it to you. Now we have x1 and x2 as inputs. So we provide first input as 0, x1, and this also as 0. So 0 into 0 is again 0, 0 into 0 is 0. And then we pass it through this activation function. Now we need to make sure that whatever value that comes here should be greater than 0.5, then only our neuron or the perceptron will fire. But since this value is actually less than 0.5, so the neuron won't fire and our output will be 0, as you can see it over here. Now let's take the other set of inputs. Now our x1 is 0 and our x2 is 1. So 1 into 1 will be obviously 1. Now in this case, our output is bigger than 0.5. Then what will happen? Our neuron will fire and will get 1, the output 1 here, as you can see it in the graph. Similarly, when my x1 is 1 and x2 is 0, in that case also, our output is greater than 0.5, our neuron will fire and will get this sort of a graph. When I talk about 1, 1, then our output will be 2, which is greater than 0.5. So we get an output that is 1. And this is how we get the graph. So this is how we get this graph. And now if you notice, with the help of the single layer perceptron, we are able to classify the ones and zeros. So this line, anything above this line is actually 1, and anything below this line, we have zeros. So this is how we are able to classify or able to implement OR gate. Similarly, when I talk about AND gate as well, so there's a difference in the truth table of AND gate. In AND gate, what happens? We need to make sure that both of our inputs are high in order to get a high output. If any of the input is low, we get a low output. And that's the reason we choose an activation function that is 1.5, which means that if our value or the output is above 1.5, then only our neuron will fire and we'll get 1 here. And there is only one case, that is when both the inputs are high. So when both the inputs are high, let me just use my pen again and I'll explain to you. So x1 is 1, x2 is 1, we get something which is 2, which is obviously greater than 0.5. Pardon me for my writing, but yeah, this is how it is. Yeah. So 1 plus 1, 2, which is obviously greater than 0.5. So what we get, our neuron fires and we get 1 here. But for the rest of the inputs, all will be less than 1.5. So that is why our neuron doesn't fire and we get a 0 output. Don't worry guys, I'll actually tell you how to implement it. I'll open my PyCharm and I'll be showing it to you practically how to implement these gates. So for that, what I'm going to do is I'm going to first import a Python library called TensorFlow. The installation guide of this particular library is present in an LMS for both Windows as well as for Linux. So you can just go through it and it's very easy to install that. And I'll actually execute this practically later in the session. You don't need to worry about it. So this is how we can implement AND and OR gate. So let's move forward guys, and we'll actually understand with a use case that is of MNIST Dataset. The reason for using MNIST Dataset is because it is already clean and will be a perfect example for this. Now what this MNIST Dataset contains, it basically contains handwritten digits from 0 to 9, and in that dataset we have 50,000 training images along with 10,000 testing images. So we will train our model with those 55,000 training images, and then we are going to test the accuracy of a model with the help of those 10,000 testing images. And for all of this, we need to understand first what exactly is TensorFlow. So let us move forward guys and we'll understand TensorFlow, and then we are going to implement all these things that we have discussed, that is AND gate, OR gate, and the MNIST dataset that I'm talking about. So let us move forward guys and understand what exactly is TensorFlow. Now what is TensorFlow? As I've told you earlier as well, we use this TensorFlow library in order to implement deep learning models. And the way the data is represented in the deep learning model is called tensors. Now what are tensors? Now tensors are just the multi-dimensional arrays, or you can say an extension of two-dimensional tables, matrices, to data with higher dimension. Now let me explain to you with the examples that are there in front of your screen. So this particular data is nothing but a tensor of dimension 6, because we have 6 rows and we have only one single column. Now over here we have 4 columns as well as 6 rows, so this becomes a tensor of dimension 6, 4. Similarly over here as well, so we have another dimension, that is the third dimension, in which we have two values. So we consider this as a tensor of dimension 6, 4 and 2. So this is nothing but a way of representing data in TensorFlow. Now if you consider the TensorFlow library, at its core it is nothing but a library that performs matrix manipulation. That is what TensorFlow is. Now let us move forward and understand TensorFlow in a bit detail. So as the name tells that it consists of two words, tensor as well as flow. Now we understood what exactly tensor is. We saw it in the previous slide as well. Now when I talk about flow, it is nothing but a data flow graph. So let me just give you an example that is there in front of your screen. So we talked about weights and inputs. So we provide these weights and inputs and we perform a matrix multiplication. So weight is one tensor, X input is one tensor, then we perform matrix multiplication. After that we add a bias, which we'll actually see it later in the session. You don't need to worry about this term. Then what we do, we add all of these. So what is this? This is nothing but the sigma function in the perceptron that we have seen. Then we pass it through an activation function, and the name of that activation function is ReLU or ReLU, or you can say it, and then our neuron will fire. So this is nothing but a flow, or you can say a data flow graph. Now let us understand a few code basics of TensorFlow. Now the TensorFlow programs actually consist of two parts. One is building a computational graph and another is running a computational graph. So we'll first understand how to build a computational graph. Now you can think of a computational graph as a network of nodes, and with each node known as an operation and running some function that can be as simple as addition or subtraction, or it can be as complex as, say, some multivariate equation. Now let me explain it to you with the code that is there in front of your screen. So the first thing you do, you import the TensorFlow library. Then what do, you define two nodes, and these nodes are constants. So we'll call that function, we'll call it as tf.constant, and we'll provide a value that is 3, and it is nothing but a float number of 32 bits. Similarly, we defined one more node, which is a constant, and it contains value 4. So these are nothing but your constant nodes. So this is basically what computational graph is. So basically we have built a computational graph, and in this graph each node takes 0 or more tensors as inputs and produces a tensor as an output. And one type of node is a constant that I've told you earlier as well. And these TensorFlow constants, it takes no inputs and it outputs a value which is stored internally. Now what I'll do, I'll actually execute this in my PyCharm. So for that I'll open it. So this is my PyCharm, guys, and I've already installed TensorFlow. So the first thing that I need to do is import the TensorFlow library. For that I'm going to type in here import TensorFlow as TF. So if you're familiar with the Python basics, you know what it means actually. So I'm importing TensorFlow library, and in order to call that, I'm going to use the word TF. So after that, I'm going to define my node 1 and node 2, which are constant nodes. So for that, I'm going to type in here node 1 equal to tf.constant, and then I'm going to define the constant value in this. So it'll be 3, and it'll be a float value of tf.float of 32-bit. All right. And now I'm going to define my second constant node. So I'll type in here node 2 tf.constant. I'll put 4 in here and 4. That's it. And so the tf.float 32 will be present implicitly. I don't need to do that again and again. So I have created a computational graph here. So what if I print it now? So let us see what will be the output. Node 1 comma node 2. Let's go ahead and run this and see what happens. If you notice here that printing the nodes does not output the values 3 and 4. You might be expecting that, right? That it should print 3 and 4. But instead they are nodes that when evaluated would produce 3 and 4 respectively. So to actually evaluate the nodes, what we need to do is we need to run this computational graph. So let me show you that. For that, I'm again going to open the slides. So since I've told you earlier as well, we need to actually run this computational graph within a session. And what is this session? Its session actually encapsulates the control and state of the TensorFlow runtime. Now the code that is there in front of your screen, what it will do, it will actually create a session object, and then it invokes its run method to run enough of the computational graph in order to evaluate node 1 and node 2. And how it does that? By running the computational graph in a session. So now let me show it to you practically how it happens. So again, I'm going to open my PyCharm.
This is my PyCharm, guys. So let me first comment this print statement, and now I'm going to run a session. So for that, I'm going to type in here ses equal to tf dot session, and now I'm going to print it. So for that, I'm going to type in print ses dot run, and what I want to run node 1 and node 2. So I'm going to type in here node 1 comma node 2. That's all. And now when I run this, it will actually give me the value 3 and 4. And yup, it does. It gives me the value 3 and 4. So what we did, we first built a computational graph. We first saw how to build basically a computational graph. And then we understood that these all are nodes. So in order to get their value, we need to evaluate those nodes, and how we can do that by running the computational graph inside a session. And when finally, when we run that session, we get the output 3 and 4, which is nothing but the values of those nodes. Fine, so I'll again open my slides. And the one thing that you must have noticed here is that it will always produce a constant result, right? So how to actually avoid that? So we saw how to run a computational graph as well. Now let me explain it to you with one more example. So this is one example in which we take three constant nodes A, B, and C, and we perform certain operations like multiplication, addition, and subtraction. And then we run the session, and then we finally close it. And this is the diagram how it looks like. So we have three constant nodes, C, B, A. A contains value 5, B contains 2, similarly C contains 3. So first we add C and B, then we add B and A. Then we get two other nodes, that is E and D. And then from that E and D, what we are going to do is we are going to subtract both of them, and then we get the final output. Now let me go ahead and execute this practically in my PyCharm. So this is my PyCharm again, guys. First thing I need to do is import TensorFlow as TF. Then we are going to define the three constant nodes. So first is A equals to TF dot constant, and the value that will be there in A will be 5. Then I'm going to define one more constant node, that will be B TF dot constant, and the value that will be there in it will be 2. And then I'm going to define the last constant node, and TF dot constant, the value that will be there is 3. Alright, so we have three constant nodes, and now we are going to perform certain operations on them. For that, I'm going to define one node, let be D, which will be equal to TF dot multiply. So the two nodes that we want to multiply, so that'll be A comma B. And then there'll be one more node in order to perform some operation, that is addition. So TF dot add C and B. And then we're going to define one more node, let be F, and inside that node we're going to perform the subtraction operation, TF dot subtract D and E. So we have built a computational graph. Now we need to run it, and you know the process of doing that. Ses is equals to TF dot session. Then we are going to define a variable, let it be outs, outs, whatever name that you want to give in, and just type in a ses dot run f. Let's see if that happens or not. And then we're going to print it. So for that, I'm going to type in here print out. Let's go ahead and run this and see what happens. So we have got the value 5, which is correct, because if you notice our presentation as well, let me open it for you. Over here we get the value 5, similar to our implementation in PyCharm as well. So this is how you can actually build a computational graph and run a computational graph. I've given you an example. Now guys, let us move forward, because these are all the constant nodes. What if I want to change the value that is there in the node? So for that, we don't use the constant nodes. For that, we use placeholders and variables. Let me explain it to you. First, I'll open my slides. So since these are all constant nodes, so we cannot perform any operation. Once we have provided a value, it will remain constant. So basically, a graph can be parameterized except external inputs as well. And what are these? These are nothing but your placeholders. And these placeholders is basically a promise to provide values later. So there's an example that is there in front of your screen. Over here, these three lines are a bit like a function or a lambda, in which we define two input parameters A and B, and then an operation possible on them. So we are actually performing addition. So we can evaluate this graph with multiple inputs by using feed_dict parameter. As you can see, we are doing it here. So we are actually passing all these values to our placeholders here. So these all values will be passed and accordingly we'll get the output. So let me show you practically how it happens. So I'm going to open my PyCharm once more. I'll remove all of this and yeah. So the first placeholder, I'm going to name it as A, tf dot placeholder, and what sort of a placeholder it'll be, so I'll consider it as float number of 32 bits. Similarly, I'm going to define one more variable as well, and I'm going to name it as B. Then I'm going to define an operation that I'm going to perform on them, so I'm just going to type in here adder underscore node equals to A plus B. And now our placeholders are currently empty. So as I told you earlier as well, placeholders are nothing but a promise in order to feed values later. So this is how we have built a computational graph. Now our next step is to start a session. So for that I'm going to type in a ses equals to tf dot session. Right. Since these placeholders are currently empty, and we know that these placeholders are nothing but a promise in order to provide them with certain values later. So let's go ahead and provide the values, or you can say a list of values. So I'm going to type in here print ses dot run adder underscore node, and then the values that I'm going to feed in. So basically I'm going to feed in a dictionary, a colon 3, a colon a list of integer values between 1 to 3, and one more will be b colon a list of integer values between 2 and 4. All right, so this is done. Now let us go ahead and execute this and see what happens. So we've got the output 3 and 7. So basically if you add 1 and 2 you get 3. Similarly you add 3 and 4 you get 7. It's pretty easy mathematics, but my main focus was to make sure that you understand what are placeholders. So I'm again going to open my slides and we'll see what's up next. So we understood what exactly are placeholders. Now it's the time to understand what are variables. So basically in deep learning we typically want a model that can take arbitrary inputs. Now in order to make the model trainable, we need to be able to modify the graph to get new outputs with the same input. And what helps us to do that? Variables basically allows us to add trainable parameters to our graph. So in order to declare variables, what we do is, you can refer the code that is there in front of your screen. So we have taken 2 variables and 1 placeholder, and the first variable has a value 0.3, the another variable has minus 0.3, and the placeholder obviously it will remain empty, and then later on we feed in some values to it. Then we create a linear model, or you can say some operation in which we are going to multiply this W with X, and then we are going to add a bias or a B value to it. Then what we need to do is we need to initialize all the variables in the TensorFlow program. So for that you must explicitly call a special operation, which is a tf.global variable initializer, and then just directly run the session. Now let us go ahead and execute this practically, guys. Let me remove all of this. Yeah. So our first variable will be a W, and we are going to call in tf.variable. And in that variable we are going to store a value which is 0.3, and it is of a float type 32-bit. So just type in here tf.float 32. Yeah. Then we are going to define one more variable, let it be B. So I'm going to type in here tf.variable, and the value of this variable will be minus of 0.3. Again, it is float type of 32-bit, so just type in that tf.float 32. Now I'm going to define a placeholder, that is x. X is equals to tf.placeholder, and it is again a float type 32-bit. And then some operation that we are going to perform, so I'm going to type in here linear underscore model equal to W multiplied by our X value, that is a placeholder, and then we want to add a bias to it or B value to it. All right. Now, as we have seen earlier as well, in order to initialize constants, we call tf.constant, and their value will never change. But by contrast, variables are not initialized when you call tf.variable. So to initialize all the variables in the TensorFlow program, what you need to do is you need to explicitly call a special operation. And how you're going to do it, just type in here init equal to tf.global underscore variables, underscore initializer. That's all. And then we're going to run a session. So you know the process. Ses is equals to tf dot session inet. Now let's print it, and before that what we need to do is we need to provide the x placeholder with some values. We're actually going to do that in the print statement itself. So I'm going to type it ses dot run what? Run a linear model. And the values that we are going to pass in x will be a dictionary again, and let me show you how you can do that. So x colon, and it'll be a list of values from 1, 2, 3, 4. Yeah, that's all. And we are going to run it now. So this is how we get the output. It's simple mathematics. What we have, the first value of w will be 0.3, and the first value of a b will be a minus 0.3, and the first value of x will be 1. So it'll be 3 minus 3, which is again 0. Similarly for other values as well, you can calculate it. It's absolutely correct. So what we have done, we have created a model, but we don't know how good it is yet. So let's see how we can actually evaluate that. For that, I'm again going to open my slides. So now in order to evaluate the model on the training data, we need a placeholder y, as you can see in front of your screen, to provide the desired values. And we need to write a loss function. So this placeholder y will actually be provided with the desired values for each set of inputs. And then we're going to calculate the loss function. And how are we going to do that? We're going to minus the actual output with the desired output, and then we're going to do the square of it. After that, we're going to sum all of these squared deltas, and then we're going to define one single scalar as loss. So this is how we are actually going to calculate the loss. And then after that, we need to provide the values to x and y placeholders. So what I'm going to do, I'm going to open my PyCharm, and then I'm going to show you how correct our model is on the basis of the values that we provide to y placeholder. So guys, this is my PyCharm again, and since here what I'm going to do is I'm going to define a placeholder first. Y is equals to tf dot placeholder tf.float 32. So I'm going to type in a tf.float 32 square delta. I've explained you all these things, but yeah, I'm going to tell it to you again as well. Don't worry about it. tf.square the actual output minus the desired output, and then I'm going to sum all of those losses, or you can say square deltas. tf.reduce underscore sum. So I'm going to type in here square deltas. Then finally print it. So I'm going to type in ses.run loss x colon 1, 2, 3, 4. 0, comma minus 1, comma minus 2, comma minus 3. And that's all, and we are good to go. Let's run it and see what will be the loss. So the loss is 23.66, which is very, very bad. Now our next step is to realize how to actually reduce this loss. So let's go ahead with that. I'm going to open my slides once more. So in order to minimize the error, now in order to reduce this loss, TensorFlow provides optimizers that slowly change each variable in order to minimize the loss function. And the simplest optimizer is gradient descent. In order to do that, we have to call the function called tf.gradients. So as you can see it in the code itself, so we have a tf.train.gradient descent optimizer, and this is nothing but the learning rate 0.01. Then train equals to optimizer dot minimize the loss. So we're going to call this optimizer, which is nothing but the gradient descent optimizer, in order to minimize the loss. And then we are going to run it. So let's see if that happens or not. So for that, again, I'm going to open my PyCharm. And over here, let me first comment this print statement. And now I'm going to type in here optimizer equals to tf dot train gradient descent optimizer, and the learning rate will be 0.01. Now I'm going to type in here train equal to optimizer dot minimize loss. And then now let's go ahead and run this. Ses dot run inet sess.run, and we're going to feed in values to our x and y placeholders. Train, comma, x will have values 1, 2, 3, 4, and y will have values 0, comma, -1, comma, -2, comma, -3. Print sess.run w, comma, p. Now let me first go ahead and comment these lines. Alright, so I've just made a mistake here. This is in uppercase W, and yeah. So now we are good to go, and let's run this and see what happens. So these are our final model parameters. So the value of a W will be around 0.999969, and the value of our B will be around 0.9999082. So this is how we actually build a model, and then we evaluate how good it is, and then we try to optimize it in the best way possible. So I've just given you a general overview of how things works in TensorFlow. So now is the time to actually implement the AND and OR gate that I was talking about at the beginning of the session. So for that, let me first remove all of this. Yeah. Now in order to implement AND gate, our training data should consist of the truth table for AND gate. And we know that truth table, and we know that if any of the input is low, then the output will be low, and if both the inputs are high, then the output will be high. One thing to note here, guys, is that the bias is implemented by adding an extra value of 1 to all the training examples. So yeah, enough with the explanation. Let's go ahead and code it. So I'm going to type in here t, comma, f equal to 1 point, comma, -1 point. And bias will always be 1. So I'm going to type in here bias is equals to 1.0. And now I'm going to provide the training data. So for that, I'm going to type in train underscore in equal to, if one input is true and the another input is also true, then we have bias. Then again, if one input is true, the other input is false, then also we have bias. Similarly, one input is false, another input is true, then we have bias. And then finally, when both the inputs are false or 0, then we have bias, right? This is our training data, and the train out will type in here as the output basically. Train underscore out will be equal to, so yeah, if both the inputs are true or both the inputs are 1, then the output is true. Oops, I forgot a comma everywhere. Let me just go ahead and do that. Yeah. So if both the inputs are true, the output will be true. If any of the input is false, the output will be false. So I'm just going to type in here false everywhere because there's only one condition in which we have the true output. Alright, so this is done now. Now as we know that TensorFlow works by building a model out of empty tensors, then plugging in known values and evaluating the model like we have done in the previous example. Since the training data that we have provided will remain constant, the only special TensorFlow object we have to worry about in this case is our 3x1 tensors of vectors. And now what we are going to do, we are going to define a variable and we are going to put in some random values in it. So I'm just going to type in tf.variable and generate the random function tf.random underscore normal 3, 1. Now what it is basically a variable. So its value may be changed on each evaluation of the model as we train, with all values initialized to normally distributed random numbers. Now that we have our training data and weight tensor, we have everything needed to build our model using TensorFlow. So what we need to do, we need to define an activation function. And we are going to define a step activation function or step function. So for that, what I'm going to write here is a function step. We're going to define our own step function, although you can use the predefined function as well. That totally depends on you. I'm going to type in here is greater equal to tf dot greater x comma 0. Then we're going to define one more variable as float tf dot to underscore float is underscore greater. Then we're going to define one more variable, a doubled equal to tf dot multiply as underscore float comma 2. Then return tf dot subtract doubled comma 1. So now this is how we have defined our step function. So with the step function defined, the output error and the mean squared error of our model can be calculated in one short line each. Let me show you how you can do that. So just type in here output equal to, call that function that is step, tf dot matrix multiplication matmul train underscore in comma w. Now for error, we're going to type in here error equals to tf dot subtract train underscore out comma output. And for mean squared error, I'm going to type in here MSC equal to tf dot reduce underscore mean tf dot square and then error. Now the evaluation of certain tensor functions can also update the values of variables like our tensor of weights w. So in our case, basically we're going to update the weights w. So first we calculate the desired adjustment based on error, then we add it to w. Now let me show you how we'll do that. So if you can recall, we have done that in the previous example as well, where we were updating the weights and biases. So now I'm going to type in here delta is equals to tf dot matmul, or you can say matrix multiplication, train underscore in comma error comma transpose underscore a equals to true. Then we're going to type in here train equal to tf dot assign w comma tf dot add w comma delta. So first matrix multiplication, and then we're going to add it all. The model has to be evaluated by TensorFlow session, which we have seen earlier as well. But before that, we also need to initialize all the variables. So first, let me just type in here ses equals to tf dot session. And then I'm going to type in here ses dot run tf dot initialize underscore all variables. So now what our next task is, in order to perform various iterations so that we get zero error. So what we're going to do, we're going to define a variable ERR and our target. So basically our ERR is nothing but our error, which can be equal to 1 or 0 because we are using binary output. So our error can be 1 and our target is to make it as 0, right? Now next what we're going to do, we're going to define epoch. Now you can consider right now epoch as nothing but the number of cycles, or you can say number of iterations that will be required in order to reach the desired output, or you can say in order to reduce the error to 0. So I'm just going to define that. So I'm going to type in here epoch, or you can give whatever variable name you want. And I'm going to type in here max underscore epoch equal to 0 comma 10. Which means that it'll start from the 0th epoch and our maximum value of epoch will be 10. Now I'm going to define while ERR is greater than target and epoch is less than maximum epoch. Increase the value of epoch y1. Then we're going to type in ERR ses.run mean squared error comma train, and let's just finally print it and see what happens. Print epoch mean squared error colon ERR. So basically what it'll print the cycles or epoch and the error with respect to that particular cycle. So let us go ahead and execute this and see what happens. Oops, I've typed the spelling of square wrong. Pardon me for that. So I'm just going to make it right now. SQUARE. All right, let's go ahead and execute it once more. So yeah, in 3 epochs, we got the value of mean squared error as 0. That means it took us 3 iterations in order to reduce the output to 0. So this is how you can actually implement a logic gate, or you can say this is how you can actually classify the high and low outputs of a particular logic gate using single layer perceptron. Similarly, you can do that for OR gate as well. Consider this as an assignment. Come up with a code that can actually classify the high and low outputs of an OR gate. What I'm going to do, I'm going to create a new Python file and I'm going to name it as MNIST, which is nothing but the data set on which we are going to perform the classification of handwritten digits. So we're going to execute a use case, and I've told you earlier as well, in this MNIST dataset we have handwritten digits from 0 to 9, and it has 55,000 training sets as well as 10,000 test sets. So let us go ahead with that. So first thing I'm going to do is download the dataset, but before that let me just import TensorFlow library as TF. And yeah, now let us download the dataset. So for that I'm going to type in from tensorflow.examples.tutorial.mnist import input underscore data. And now I'm going to type in here MNIST is equals to input underscore data dot read datasets. I'll type in here MNIST underscore data comma 1 underscore hot equals to true. Now here MNIST is nothing but a lightweight class which stores the training, validation and testing sets as numpy arrays. And when I talk about this 1 hot equals to true is nothing but 1 hot encoding. Now let me tell you what 1 hot encoding is. So for that let me just comment few lines. So 1 hot encoding means that if I'm classifying something as a 7, so if I classify that my digit is 7, so how am I going to represent that? So I'm going to type in here 0, 1, 2, 3, 4, 5, 6. 7th bit will be active, so I'm going to type in there 1, then 8 and then 9. Similarly, if I want to represent, say, that my digit is 2, so I'm going to type in 0, 1. On the second digit, I'm going to type in here as 1 and the rest all zeros. So I hope you got the concept of what exactly 1 hot encoding is. So it's like only one output is active at a time. That's all. So our next step is to start the session like we do every time. So I'm going to type in here ses equals to tf dot interactive session. So I'm just going to type in here interactive session. Yeah. And now we are going to build the computation graph by creating nodes for the input images and target output classes. So for that I'm going to define some placeholders. For that I'm going to type in x is equals to tf dot placeholder tf dot float 32 and the shape will be none comma 784. Now the input images x will consist of 2D tensors of floating point numbers. Here we assign it a shape of say none comma 784 as you can see. So where 784 is the dimensionality of single flattened 28 by 28 pixel MNIST image of handwritten digits. And what none indicates, it indicates that the first dimension corresponding to the batch size can be of any size. Means the first dimension can be of any size. We are not putting any restrictions on that. Now I'm going to define variable y, which will be nothing but our real labels, or you can say the desired output. Placeholder, and I'm going to type in here tf.float32, and I'm going to define the shape, which will be none comma 10 because we have 10 classes. And similarly, y is also a 2D array where each row is one hot 10-dimensional vector indicating which digit class the corresponding MNIST image belongs to. And now next step is to define weight and biases for our model like we have done in the previous example. So we could imagine treating these like additional inputs, but TensorFlow has even a better way to handle them, and what it is nothing but variables. So let us go ahead and do that. I'm going to type in here wtf.variable tf.zeros. I'm going to initialize it to zeros.
and the shape will be a 784, 10. So it's like 28 cross 28 pixels and 10 classes. Similarly, when I talk about bias, so it'll be tf dot variable, tf dot zeros, initialize it to zeros, and the shape will be 10. We pass the initial value for each parameter in the call to tf dot variable. Now over here, as we can see that we initialize both W and B as tensors full of zeros. And W is a 784 cross 10 matrix because we have 784 input features and 10 outputs. And when I talk about bias B, it is a 10-dimensional vector because we have 10 classes. And we have learned that before we can use variables in a session, we need to first initialize it. So we're going to type in here sys a dot run, and after that I'm going to type in tf dot global underscore variables underscore initializer. Alright, so we have initialized all the variables. So our next task is to predict the class and the loss function. So we can now implement our regression model. It takes only one line. We multiply the vectorized input image X by the weight matrix W and add the bias. So for that, I'm just going to type in here Y equal to tf dot matmul, that is nothing but matrix multiplication, X comma W plus B. All right. So now we can specify a loss function very easily. So the loss indicates how bad the model's prediction was on single example. We try to minimize that while training across all the examples. So now we can specify a loss function. Now loss indicates how bad the model's prediction was on a single example, and we try to minimize that while training across all the examples. Now here our loss function will be cross entropy, or you can say the difference between the actual output and the predicted output. So for that, what I'm going to do, I'm going to make use of softmax cross entropy function. So here the loss will be the difference between the target output and the actual output. So for that, what I'm going to do is I'm just going to type in here a variable name. I'm going to name it as cross entropy. And yeah, entropy equals to tf dot reduce underscore mean. And then just type in here, let me just enter the next line, tf dot nn dot softmax underscore cross entropy with logits. And now over here I'm going to type in first our target output, which will be labels equals to y, comma our actual output, so it'll be logits is equals to y. That's all. So over here, let me just give you a brief idea what is happening. So labels is equals to y means that this is our target output and this is the actual output. So it'll be, we'll name it as y underscore. And so what exactly is happening? It will calculate the difference between the target output and for the actual output for all the examples. Then it is going to sum all of them and then find out the mean. So this is what basically this cross entropy variable will do. Now that we have defined our model and training loss function, it is straightforward to train using TensorFlow. Now we need to train our model. So TensorFlow has a wide variety of built-in optimization algorithms, as I've told you earlier as well. And for this example, we'll use steepest gradient descent with a length of about 0.5 to descend the cross entropy. So basically, we're going to use a 0.5 learning rate, or you can say the step length. So for that, I'm going to type in here train underscore step equal to tf dot train dot gradient descent optimizer, and the step will be 0.5 and minimize the loss, so minimize cross entropy. That's it. So what this one line basically will do, it will minimize the cross entropy, which is nothing but the loss function that we have defined. Now in the next step, what we are going to do, we are going to load 100 training examples in each training iteration. So each time the training iteration happens, it'll take 100 examples. We then run the train underscore step operation, which is nothing but to reduce the error, using feed underscore dict, which is nothing but we are going to feed the real values to our placeholder y. Now next what we are going to do, we're going to load 100 training examples in each training iterations, which means that for each iteration we'll take 100 training examples and we'll run the train underscore step operation, which is nothing but the optimizer here. And after that we're going to use a feed underscore dict to replace the placeholder tensors x and y with the training examples. So basically x will contain the input images and y will contain the actual outputs, or you can say the desired outputs. For that I'm going to type in here for underscore in range
1000 batch equals to MNIST dot train dot next underscore batch 100 train underscore step dot run, and I'm going to feed in the values to x and y variable. Feed underscore dict equal to x colon batch 0 comma y colon batch 1. That's it. Now we need to evaluate our model. We need to figure out how well our model is doing, and for that I'm going to make use of tf.argmax function. Now this tf.argmax function, let me tell you how it works. First I'm going to type in here correct underscore prediction equals to tf.equal tf.argmax y underscore comma 1 comma tf.argmax y comma 1. So basically this tf.argmax y underscore comma 1 is a label our model thinks is most likely for each input. That means it is our predicted value. While tf.argmax y comma 1 is a true label. It is there in our dataset present already, and we know that it is true. So what we are doing, we are using tf.equal function to check if our actual prediction matches the desired prediction. So this is how it is working. So now what we're going to do, we're going to calculate the accuracy to determine what fraction are correct. We cast a floating point numbers and then take the mean and repeat. So now I'm going to define a variable for accuracy. So just going to type in accuracy equals to tf.reduce underscore mean, tf.cast correct underscore prediction, comma tf.float 32. And what we can do finally, we can evaluate our accuracy on the test data. And this should give us accuracy of about 90%. So let us see if that happens. I'm going to type in here print accuracy dot evaluate eval feed underscore dict equal to x colon MNIST dot test dot images comma y colon MNIST dot test dot labels. That's it, guys. And I've done a mistake here. Instead of y, it will be y underscore, because this is our predicted value, not the actual value. And y we have considered as actual value, and this y underscore will be our predicted value. So this is the mistake that I made. So yeah, now I think the code looks pretty fine to me, and we can go ahead and run this. Let us see what happens when we run this. So guys, it is complete now, and this is the accuracy of a model, which is 91.4%, and which is pretty bad when you talk about a data set like MNIST. But yeah, with a single layer, it is very, very good. So we have got an accuracy of around 92% on the MNIST data set, which means that whatever the test data sets were there, that is like 10,000 test images. So on those test images, whatever the prediction our model has made are 91.4% correct. So guys, let me just give you a quick recap of what all things we have discussed. So first we saw what exactly is deep learning and how it is different from the traditional machine learning. Then we understood the motivation behind deep learning, which is nothing but your brain cells, which are called neuron. Then we understood the importance of why we need artificial neurons. And then we took the example of artificial neuron, which is called a perceptron. And we looked at a couple of examples in which we implemented the AND gate. We performed image classification on the MNIST datasets, which is nothing but handwritten images between 0 to 9. And we also implemented a couple of examples in order to understand what are placeholders, variables, and constants. So now there are certain limitations of single layer perceptron. Let us understand that. So in order to understand that, we'll take an example. So we have an XOR gate here, and this is the truth table. So according to this truth table, if any one of the input is high, then the output is high. And if both the inputs are low, output is low. And if both the inputs are high, output is low. So how can you classify the high and the low outputs with a single line? Definitely you can't. If you see the points, so one point is here, one is here, here, and here, in which these 2 points are high outputs and these 2 are low. So how can you classify with a single line? Definitely you can't. So now what's the answer to this? What if we use multiple neurons?
So using multiple neurons, we can have two lines that can separate it. Now we can solve this problem if we have multiple neurons. So if we use two neurons, we can have two lines and that can actually separate the high outputs as well as the low outputs. So this is where we use multilayer perceptron with backpropagation. So what are multilayer perceptron? Multilayer perceptrons, they have the same structure like the single layer perceptron. The only difference is they have more than one hidden layer. So let me explain it to you with an example. So this is how a typical multilayer perceptron looks like. So we have input layer, we have two hidden layers, and we have one output layer as well. Now typically each of these input layers are connected to the next hidden layer. Each neuron is connected to the next neuron present in the adjacent layer. But the neurons of the same layer are not connected to each other. Now what happens, a set of inputs are passed to these input layers and the output of this input layer will be passed to the first hidden layer. Then after activation function of the first hidden layer, the output will be passed to the next hidden layer as the input, and similarly finally we get the output. Now you must be thinking how the model learns from here. So basically the model learns by updating the weights, and the algorithm that it uses is called backpropagation. So the backpropagation algorithm helps the model to learn and update the weights in order to increase the efficiency. So basically this process of from input layer to the output layer is called a feedforward process. And then when we backpropagate it in order to increase the efficiency or accuracy so that we can update the weights, that is called as backpropagation. We'll understand backpropagation in more detail. So what is backpropagation? Now let us understand this with an example. So we'll take the inputs as the leads generated from various sources. And my aim is to classify the leads on the basis of the priority. So there might be certain leads which won't make that much difference to me, whereas compared to the other leads. So in that case, I need to make sure the leads which are important gets the highest amount of weight. How am I going to do that? First, we'll see the output. Then accordingly, we'll calculate the error. And based on that error, we are going to update the weight. And this process is nothing but your backpropagation in a nutshell, I can say, right? Although the algorithm is pretty complex, but yeah, this is basically what happens. So in order to classify the leads on the basis of priorities, we need to provide the maximum weight to the most important lead. And how are we going to do that? We're going to compare the actual output and the desired output, and according to the difference, we're going to update the weights. So what is backpropagation? So backpropagation is nothing but a supervised learning algorithm for multi-layer perceptron. Now let us understand what exactly is this algorithm. Let us understand this with an example that is there in front of your screen. So these two are our input neurons, these two are our hidden neurons, and these two are our output neurons. Now our aim is to get 0.01 and 0.99 as our output. And at the same time, we have inputs as 0.05 and 0.10. Initially, we take the weights as we can see it here. So 0.15 W1, 0.20 W2. So these are the weights. Plus we have two biases as well. Now what we need to do is we need to make sure that we have weights in such a way that we get output as 0.01 and 0.99. But let us see if we get that same output when we provide these kind of weights. The net input for this particular H1 will be what? It'll be W1 into I1, that is the first input, plus W2 into I2 plus B1 into 1, which gives us the answer as 0.3775. Similarly, the output for H1 will be nothing but the activation function, the output after the activation function. And we are using here sigmoid function because our brain also uses a sigmoid functions. That's what we believe in. And at the same time, it is easily differentiable. And if you differentiate it twice, you get the same number. So the output of H1 will be 0.59 something. So let me go back. So the output of this particular H1 will be 0.59 something. Then we're going to calculate the output of H2 as well similarly. And we get the output as 0.5968884378. Next up, we are going to repeat the process for the output layer neurons as well. So for the output layer, the net input will be W5 into out of H1, W6 into out of H2 plus B2, that is the bias. So we get the output somewhere like this. And then the net output for out O1 will be after the activation function, which will be 0.751. Similarly, the output for O2 will be 0.77. Now, if you notice that this is not the desired output. Our desired output was 0.01 and 0.99. What we got instead, we got 0.75 and 0.77. So what we need to do, we need to update the weight. So for that, we're going to calculate the error. Now, error for output O1 is nothing but the sigma of 1 by 2 target minus output whole square. Target is nothing but your desired output and output is your actual output. So your error of output of O1 neuron will be 0.278. Similarly, for O2 will be 0.023. So the total error comes down to 0.29 something. Next up, we need to update the weight so as to decrease this error. Now what we're going to do, we're going to first calculate the change in total error with respect to any of the random weight. We'll take W5 for example, just to show you. So we're going to calculate the change in the total error when we change with respect to the weight W5. So we're going to apply a chain rule here. So using partial derivative, we're going to calculate E total by delta of out O1 into delta of out O1 by delta of net O1 and then delta of net O1 by delta of W5. As you can see it from this particular example as well. E total, change in E total with respect to out O1, change in out O1 with respect to net O1 and change in net O1 with respect to W5. We're going to multiply that and we're going to get this particular term. And let us see how we do that. So how much the total error change with respect to the output? E total by E out 1, we're going to calculate it. It came around 0.741. Similarly, we're going to calculate how much does the output O1 change with respect to the net output. And we get this. After that, we're going to calculate it for net output change with respect to W5 also. We got this. And then finally what we did, we put all these values together and we found out the change in the error with respect to the change in weight W5, which came to up around 0.082167041. Now is the time to update the weight. So how are we going to update the weight? First thing we need to do is we need to follow this formula. So W5 plus is nothing but the updated weight, which is equal to W5 minus the learning rate into delta of E total by delta of W5. So which came to around 0.35891648. Similarly, we can calculate the other weights as well. So we're going to repeat the same process and we're going to calculate the other weights as well. Then again, we're going to see how much is the loss. If still the loss prevails, then we're going to repeat the same backpropagation learning algorithm again for all the weights. So this process will keep on repeating. So this is how backpropagation actually works. So now what I'm going to do, I'm going to make use of the same MNIST dataset and I'm going to increase the efficiency of that dataset by 97 to 99% with the help of multi-layer perceptron. So guys, let us go ahead with that. So guys, as I've told you earlier as well, we are going to use the same MNIST dataset which we have used in the single layer perceptron. So I'm going to perform a classification using multi-layer convolutional networks. Now what are convolutional networks? Basically these networks are used in order to classify images. So basically what I'm doing is I'm just trying to show you that how we can increase the efficiency using the convolutional neural networks. I'm just giving you a general overview, or you can say a taste of how things work in convolutional neural networks. So we give an input image to this convolutional network. Then this input image is processed in the first convolutional layer using the filter weights. Now this result in 16 new images, one for each filter in the convolutional layer. The images are also downsampled, so the image resolution is decreased from 28 cross 28 to 14 cross 14. Now these 16 smaller images from the first convolutional layer are then processed in the second convolutional layer. We need filter weights for each of these 16 channels and we need filter weights for each output channel of this layer. Now there are total 36 output channels, so there are total of 16 cross 36 equal to around 576 filters in the second convolutional layer. Now the resulting images are downsampled again to 7 cross 7 pixels. The output of the second convolutional layer is 36 images of 7 cross 7 pixels each. Now these are then flattened to a single vector of length 7 cross 7 cross 36, which is 1764, which is used as the input to a fully connected layer with 128 neurons. And this feeds into another fully connected layer with 10 neurons, one for each of the classes, which is used to determine the class of the image, that is which number is depicted in the image. So whatever number that we provide in, so basically the output layer, or you can say the last layer or the fully connected layer with 10 neurons is used to determine the class or which digit is the input image of. Now the input image depicts the number 7 and the 4 copies of the images are shown here. So basically what happens, whatever filter we have in each layer, it will be present on the image pixels. So there'll be a dot product of the filter and the image pixel behind that. So we'll get a dot product there. We are going to repeat that same process in each of these layers and for each of these layers and for each of these images. And we are calculating the dot product. So I hope you get the point. So let me just show you that we can increase the efficiency. So I've already run the code and it will take time if I do it right now. So this is what the efficiency we ended up with. So it is 98.8%. So on the test sets, we had around 10,000 test samples, out of which we predicted 9,876 correctly. So which is pretty good actually, if you see. So because in the single layer perceptron example that we took, we were getting accuracy of around 92%. But here we are getting around 99%, which is actually very good. All right.
In this session, let's have a look at the top 8 deep learning frameworks which is very popular and widely used. This session is helpful for anyone who's considering to expand their knowledge about all the frameworks out there, or if you're just considering to build a career in deep learning. I have categorized the 8 frameworks in descending order of the rank based on various factors such as efficiency, community, and how easy it is to actually get started with each of these. Without further ado, let's dive into Chainer. It is the first one in this top 8 rundown, and I'm sure you guys are all curious about Chainer, right? Well, Chainer is a Python-based deep learning framework defined by run strategy. The first thing we look at is performance. Well, Chainer has got that sorted. It is known for its high performance capabilities in all of the domains. Well, with performance comes a slight prerequisite on how easy it is to actually get around and get the work done with the framework, right? Again, Chainer is intuitive and coding in it is really easy, guys. I would rate it about 6 on 10 at this point though. Now that you know it is intuitive, what's fancy about Chainer? Well, let me tell you, it provides really good dynamism and helps with understanding the flow of the code better. And this in turn works well because of the direct approach into good machine translation as well. Well, Chainer is widely used, but it is mainly used for speech recognition and sentiment analysis of all sorts. Okay, so now that Chainer is done, what do we have next on the list? Well, it's Microsoft's CNTK. However, it has a new name now, guys. It's called Microsoft Cognitive Toolkit. Well, that sounds fancy, right? Well, CNTK is actually fancy. As a framework, it is supported by interfaces such as command line, C++, and Python. It's said to provide really high scalability in terms of training a convolutional neural network for images, speech, or any textual based data. When working on multiple machines, the scalability is definitely better than Theano or say even TensorFlow to some extent. And when it comes to usage, it has to be handwriting recognition and speech recognition mainly. This is made easy because inventing a new complex layer types in CNTK is extremely straightforward. But you might be curious at this point about how so, right? Well, users will not have to implement anything in a low-level language, which is definitely worth noting. Well, now that that's done, next up we have generative adversarial networks. Well, that's a mouthful. However, not to worry guys, it's just one of the types of reinforcement learning. And now that we've established that, how does it scale? Again, on a scale of 1 to 10, it ranks at about 7 on how easy it is to actually train the models. And lastly, of course, Microsoft after 2012 has been making a lot of its technologies open source. This definitely adds to the number of contributors that are pouring in and expanding the community eventually. However, due to the lack of support on ARM architecture, the capability on mobile is fairly limited. Well, to fix this, Caffe came into the picture. Well, Caffe is another deep learning framework that is supported with interfaces like C, C++, Python, MATLAB, as well as the command line interface. Well, that's lovely. It is popularly used for vision recognition, guys. However, Caffe does not support fine granularity network layers like those found in TensorFlow or CNTK. I'm pretty sure you might be wondering why. Well, we will require a bit of low-level language code, which I am sure majority of us don't like, right? Well, again, it has to be open source, so if it's getting all the attention for its sheer speed and performance, I'm sure again you're wondering how. Well, Caffe's biggest bragging right is definitely its speed. More on this in just a second. Also, the presence of something called as the Caffe Model Zoo is really good. It is really simple, guys. It is basically a DeepNet repository which is already pre-trained and it is available to use immediately. Well, now let's get back to that speed thing. Well, we all love speed, right? Caffe just ups its game here because it can process over 60 million images on a daily basis with just one single NVIDIA K40 GPU. Well, that's about 1 millisecond per image for inference and 4 milliseconds per image for learning. And with more recent libraries, it is getting still faster. Well, this is definitely amazing. So this is definitely like icing on a cake, and whether it is modeling CNNs or solving image processing issues, this has to be the go-to library in my opinion. But given the architecture, the overall support and the language modeling capabilities, it lacks a little bit when compared to these other frameworks. So to fix this, what do? Well, let's bring in MXNet to the picture. The beauty of MXNet is that it provides the user the ability to code in a variety of programming languages ranging from Python, C++, R, Julia, and Scala to name a few. Well, there are more actually. Well, this means that you can train your deep learning models with whichever language you're comfortable with, and you don't have to learn anything new from scratch. Well, that's really good, right? Well, now we need to find out how MXNet actually stands out. Well, for starters, MXNet was specifically designed for high efficiency, high productivity, and a lot of flexibility, guys. MXNet supports long-term short-term memory, which is also called as LSTM, along with the support for both recurring neural nets and convolutional neural nets. Also, it's known for its capabilities in imaging, speech recognition, forecasting, as well as natural language processing. And lastly, Amazon employed MXNet as its go-to reference library for majority of its deep learning requirements. Well, we're looking at a lot of interfaces like C, C++, Python, and even MATLAB. Aren't we missing something that makes our lives that much simpler, guys? Well, yes, you might have guessed it right. I'm talking about Java. We have a framework which is exactly tailor-made for this, and it's deep learning for Java. Guys, the biggest highlight is that it provides parallel training through iterative reduce and microservice architecture adoption coupled with distributed CPUs and GPUs. Well, to be honest, I would be impressed by anything which involves a lot of CPUs and GPUs at the same time. Well, this framework is widely adopted as a commercial and industry-focused deep learning platform. Well, now that we have established that, what's the biggest advantage, you ask? Well, for starters, you can bring together the entire Java ecosystem to execute deep learning. And what makes it even better is that it can be administered on top of Hadoop and Spark to orchestrate multiple host threads. The framework shows matchless potential for image recognition, fraud detection, text mining, and parts of speech tagging and natural language processing as well, which in my opinion is definitely amazing. Well, deep learning for Java comes with a deep network support through RBM. RBM is nothing but restricted Boltzmann machine. Also DBN. DBN stands for Deep Belief Networks. Well, it's nothing but a layered graphical model in simple terms. And also the added support for convolutional neural networks, recurrent neural networks, and long-term short-term memory, which is also called as LSTM networks as well. Well, guys, you need to take a note that it is much more efficient in comparison to Python in multiple fields. When it comes to image recognition tasks using multiple GPUs, it is actually as fast as Caffe, which again impressed me a lot. Also, with Java as your core programming language, you should certainly opt for this deep learning framework if you're looking for a robust and effective method of deploying your neural network models to production. Well, now that we have sorted this out, we're just left with the top 3 frameworks for now. Well, I have saved the best for the last, so quickly let's take a look at our number 3 competitor, which is Keras. Well, what I really like about Keras is that for starters, it is well known for being minimalistic and you get the work done with Python. Well, Keras supports both convolutional and recurrent networks that are capable of running on top of either Theano or TensorFlow. Well, due to the fact that the TensorFlow interface is a tad bit challenging coupled with the fact that it is a low-level library that can intricate for new users, well, it makes it a bit tough, right? But Keras was built to provide a simplistic interface for the purpose of quick prototyping by constructing effective neural networks that can work with TensorFlow. And there we asked the question and we answered it. Also guys, Keras is a celebrity to be honest. It had over 4,800 contributors at launch and now it has over 250,000 active developers and it is still adding. Well, with every year, there is a 2 times growth on the overall development of the framework. And since it's getting all this good attention, it has certainly made a really good name among the majority of the startups. Well, we have 8 standout features which I believe deserved a mention in this session. Well, you're curious, right? So let's start out. Well, definitely starting out with the focus provided on user experience, followed by the large adoption in the industry, making everyone use the framework and build a vast community overall. And of course, the support to let use of multiple backends, develop and deploy on multiple platforms is a plus. Well, what surprised me is that it has a real good community when it comes to research as well. And lastly, of course, all the concepts are really easy to grasp, guys. Well guys, at this point, we have established that Keras is really good, right? But is it as good as PyTorch, which is the next framework I want you guys to check out? Well, we haven't looked at definitions for a while. So what is PyTorch? Well, PyTorch is a scientific computation package created by all the amazing people at Facebook. It is Lua powered and works with Python, which is definitely a win already, and we haven't even begun to discuss the framework. Well guys, it's majorly used by industry giants like Facebook obviously, Twitter and even Google to a certain extent. Well, PyTorch is giving you a really good time when it comes to using Facebook, right? You're wondering how? Well, let me tell you this. Consider that it's a weekend and you're partying with friends. You decide to click a lot of pictures and you want to put them on Facebook, right? But tagging everyone manually, I am not a fan of this and I'm sure you are not too. Well, remember those magical pop-ups which automatically detect faces? Well, thank PyTorch for that. However, as opposed to Torch, which is actually the predecessor of PyTorch, PyTorch runs on Python, which means that anyone with a basic understanding of Python can get started on building their own deep learning models. However, features such as automatic differentiation by the AutoGrad module and the support for dynamic computation graphs is what makes PyTorch stand out when it compares to all the other 7 frameworks, to be honest. Also, of late, PyTorch has seen a high level of adoption within the deep learning framework community and is considered to be quite the competitor to TensorFlow. Well, which is exactly what we are going to talk about, and TensorFlow definitely grabbed the #1 spot on this rundown of the framework. Well, TensorFlow is the brainchild of all the amazing people at Google. The most well-known use case of TensorFlow has definitely got to be Google Translate, right? It is coupled with the capabilities of natural language processing, text classification, speech recognition, image recognition, forecasting, and tagging. Well, wow, the list goes on and on for sure. Well, it is arguably one of the best frameworks right now, which is why it has been adopted by several giants at scale such as Airbus, Twitter, IBM, and mainly others due to the highly flexible system architecture. Also guys, TensorFlow is available on both desktop and mobile and also supports languages such as Python, C++, and R to create deep learning models along with the wrapper libraries. Well, now we know why TensorFlow is really good, right? Well, it comes with two tools which are widely used. Well, starting out with TensorBoard, it is used for effective data visualization of network modeling and performance. And secondly, TensorFlow Serving for rapid deployment of new algorithms or experiments while retaining the same server architecture and the APIs. Well, if you happen to be taking your first steps when it comes to deep learning, it is sort of a no-brainer that you should opt for TensorFlow given that it is Python based, it is supported by Google, and it comes loaded with documentations and walkthroughs to guide you. Well, that being said, let me wind up this session by asking you this. Which deep learning framework from this list would best suit your requirements? Well, the answer to that is dependent on you and definitely lies on a number of factors. However, if you're just looking to get started, then a Python-based deep learning framework like TensorFlow or Chainer, as I previously mentioned, should be your choice. But if you happen to be seasoned, you need to consider speed, resource requirement, and usage along with the coherence of the trained model before picking out the best deep learning framework there is. Well guys, we all love deep learning and this is one amazing community to be a part of.
Welcome to this TensorFlow tutorial on deep learning. In this tutorial, we'll be covering all the fundamentals of TensorFlow to implement a use case that is a Neville Mine Identifier, NMI. So let's begin, guys. Neville Mine Identifier is a pretty serious problem in which one needs to identify whether an obstacle is a rock or a mine on the basis of sonar signals bounced or reflected by it. So let's get into the details of this use case. Imagine you are hired by the US Navy and your task is to create a model that can differentiate between a rock and a mine. We will call this model as a Neville Mine Identifier, NMI. A Neville mine is a self-contained explosive device placed in water to damage or destroy surface ships or submarines. If you want a better picture, just consider the diagram that is there in front of your screen. So here we have 3 submarines, out of which one is broken down into small pieces when it passes through a Neville mine. The major use of these underwater mines or Neville mines began in World War I. Similarly, in World War II, nearly 700,000 Neville mines were laid, accounting for more ships sunk or damaged than any other weapon. So now you must have understood the importance of this use case. This model can actually save a lot of lives. Now let's look at the data set that we'll use to create this deep learning model. Here we'll be using the sonar dataset. This dataset contains sonar signals which includes 111 patterns bounced off a metal cylinder and 97 patterns bounced off a rock, both at various angles and conditions. Hence, every record in the dataset represents a pattern. Now let me show you the dataset. So there are total 61 columns in the dataset, in which the first 60 columns is a set of 16 numbers in the range from 0.0 to 1.0. And the last column of every record is a label which represents the name of the class. That is either a rock or a mine. Let me explain you with an example. If the pattern is defining a rock, then the last column would contain the letter R. Similarly, if the pattern represents a mine, then the last column would contain the letter M. So if you notice in the dataset as well, in the last column we have either R or M. So this is nothing but the class to which the pattern belongs to, whether it is a rock or a mine. So this data set contains both the patterns which can be analyzed for prediction and the actual outcomes. That is whether the pattern represents a rock or a mine. Hence, it can be used for training the TensorFlow model that we want to create. Now is the time to understand the flow to implement the Neville mine identifier. Now don't be scared of the fancy terms that I'll use here. You'll understand them all in the coming slides. For now, we'll understand the steps that will be involved in implementing the TensorFlow use case. So we'll begin by processing the data set that we have. We'll define features and labels. We'll divide the data set into two parts, training and testing. Then we'll train our model on the training data. We'll try to reduce the error. After that, we'll test our model on the test data and we'll calculate the accuracy. Here, our ultimate goal is to achieve the highest possible accuracy. So guys, let me quickly execute the TensorFlow model that I've already created for you. For that, I'll open my PyCharm. So this is my PyCharm, guys. Over here, I've already written the code in order to execute the use case. So I'll just go ahead and run this. So this is how the output looks like, where the deep learning model is getting trained. If you observe, with every iteration, the accuracy is increasing and the error is decreasing. So we'll stop it right here. So with this, we'll get back to our slides and understand the fundamentals of TensorFlow first before we get into the implementation details of this use case. In order to implement this use case, we'll be using TensorFlow, which is a Python library. In TensorFlow, data is represented in the form of tensors. So let's understand that first. TensorFlow programs use a tensor data structure to represent all data. You can think of a tensor as an n-dimensional array or list. Now consider the example that is there in front of your screen. So the first tensor has dimension 0. The next tensor has 2 dimensions because it has rows as well as columns, and the last tensor has dimension 3 because it has one more field. Now in TensorFlow system, tensors are described by a unit of dimensionality known as rank. So let's understand that. So a rank 2 tensor is what we typically think of as a matrix, and a rank 1 tensor is a vector. Now let us focus on the table that is there in front of your screen. So rank 0 is nothing but a scalar which has magnitude only. You can think of its example as 483, 689, numbers like that. Then when I talk about rank 1, it is a vector which has magnitude and direction both. And you have the example in front of your screen, 1.1, 2.2, 3.3. Similarly, when I talk about rank 2, it is nothing but matrix, tables of numbers. You can say rows and columns. And you have an example here as well. Similarly, when I talk about rank 3, you can see the example here. So this is how we actually define the rank of a tensor. Now let us move forward and understand various tensor data types. You can see in the table that there are multiple data types. There is integer type of 8 bits, 32 bits, etc. Similarly, even for float type. Then there is even string and boolean type. However, in TensorFlow, you don't need to specify the tensor data type. It will automatically assign the correct type. But if you want to save the reserved memory, for example, if you know you require only 32 bits, then there is no point in reserving 64 bits. So at that time, you can specify the tensor data type to be of 32 bits. So that way you can save some memory. So guys, now is the time to understand what is TensorFlow. TensorFlow is an open source software library released in 2015 by Google to make it easier for developers to design, develop, and train deep learning models on neural networks. Now TensorFlow works by first defining and describing our model in abstract. And then we are ready, we make it a reality in a session. Now don't worry guys, in the next slide I'll explain what exactly is session. This description of the model is what is known as your computation graph in TensorFlow. And remember guys, only tensors may be passed between the nodes in a computation graph. Now if you notice, TensorFlow is nothing but the combination of two words, tensor, which we saw in the previous slide, and flow, which is nothing but the tensors flowing through a computation graph. So guys, let us dig a bit deep and understand the TensorFlow code basics. The TensorFlow programs consist of two sections. One is building the computation graph. Here we just describe the computation. It doesn't compute anything, it doesn't hold any values, it just defines the operations specified in your code. When you execute it, the output will just be an abstract tensor. No actual calculations will run, only operations will be created. To actually see the result, we need to run the session. Generally, you build the graph first and then you launch the graph, right? This session allows us to execute the graph or a part of the graph. Let us understand this with an example. So this is how you build a computational graph. Here we have defined two constant nodes. Node 1 has a value of 3 and node 2 has value 4. Then what we do, we need to run it inside a session in order to execute the graph. Now let me go ahead and execute this practically in my PyCharm. This is my PyCharm again guys. First thing I need to do is import TensorFlow as TF. Then we'll define two constant nodes. Node 1 equal to tf.constant, and the value will be stored inside it will be 3.0. It is of tf.float 32 bits. Then we'll define one more node and let it be tf.constant again, and the value that will be stored will be 4.0. Next up, when we try to print these two nodes, let's see what happens. Let's go ahead and execute this. Now the output here is just an abstract tensor. No actual calculations are running, only operations are created. Now to execute this graph, let me tell you how you can do it. First, I'll comment this line. Now to execute this graph, we will run it inside a session, as I've told you earlier as well. So session places the graph operations onto devices such as CPUs or GPUs and provides methods to execute them. So I'll type in here ses is equals to tf.session. So this will basically launch the graph and create a session object. Next up, we will run the results. So for that, I'm going to type in here print ses.run, and we want the values of node 1 and node 2. So let us go ahead and type that, node 2. Yeah, this is fine now. And when we are finished with the session, we need to close it in order to free up the resources that were used. So that is also very easy. Just type in ses.close. That's all you need to do. Go ahead and execute this. So we have got the output as 3 and 4, which is absolutely correct. These are the values stored in the constant nodes 1 and node 2. There's one more way in order to launch the graph and close the graph apart from the one that I've shown you. So let me show you how you can do that. For that, what I'm going to do, I'm going to first comment this line, even this line. So for that, what I'm going to use the with statement of Python. So for that, I'll type in here with tf.session as ses output equal to ses.run node 1 comma node 2. Go ahead and print the output. So if you're not familiar with what this does, basically it will use a session for the block of code following the statement and then automatically close the session when done. The same way it works if you open a file with the with statement. So let us go ahead and execute this and we'll see what happens. So again, we have got the same output 3 and 4. So I've explained you a couple of ways in which you can start and stop a session. So guys, let me explain you this with one more example. For that, I'll open my slides once more. Here I have first defined a constant node A which has a value 5 in it. Then I've defined one more constant node which is B, and the value stored in that node is 6. After that, I've defined one more node, and this is nothing but the multiplication of A and B. So till now we have built our computation graph. Next up, we need to run it inside a session. So when we run the session, what will happen? The values that are stored in A and B will be multiplied. So let us see if that happens. Yep. So after running the session, we got the output as 30, which is nothing but the multiplication of A and B. So when you multiply 5 by 6, obviously you will get 30. Now guys, I'll open my PyCharm and execute this practically. Let me remove all of this. So first I'm going to define one constant node. The value that will be there will be 5.0. One more constant node. The value inside that node will be 6.0. Then C is nothing but the multiplication of the two nodes. So we have built our computational graph. Next up, we need to create a session object which will launch the graph. So ses is equal to tf.session. So guys, you can even use a with statement of Python in order to do that. But yeah, I'm comfortable with this, so I'll continue from here. And then what I need to do is just run the session, ses.run C. That's what I want to compute. And yeah, finally just close the session. ses.close. Go ahead and execute this. So we have got the output as 30, which is nothing but the multiplication of nodes A and B, which stores the value 5 and 6 respectively. Now I know multiplication of two numbers is not a big deal, but it is a good example for understanding how things work in TensorFlow. Now, what if I tell you that you can actually visualize a computation graph? Let me tell you how. For that, I'll open my slides. So for visualizing TensorFlow, we use TensorBoard. TensorBoard is a suite of web applications for understanding your TensorFlow graphs. For that, what we need to do, we need to first create the object of class for writing summaries. One such class is called FileWriter. So it has two arguments. The first argument, we need to just specify the path of the directory where we want the information to be stored. That will be used by TensorBoard in order to build the graph. After that, we need to run this particular command in the command line, and we'll see that TensorBoard will run as a local web app on port 6006. So I'll quickly open my PyCharm and I'll execute this practically. Let me close this. Yeah. So after that, I just need to create an object, file writer object, file writer equals to tf.summary.file writer, and I need to provide a path here. So I've already copied the path. I'll just paste it here. And once you have written the path, just type the name of the file. So I'll just type in here graph. And after that, I need to add ses.graph, which is used for creating a graph object. So just type in here ses.graph. All right. So now if I execute this, I'll see a directory here by the name of graph that will contain the information which will be used by TensorBoard in order to build the graph. Let us see if that happens or not. I'll run the code. And yeah, you can notice here that there's one more directory created that is called graph. Next up, we need to open a command line and execute one command. Let me show you how you can do that. So over here, first I'll move in the PyCharm directory. Yeah. And then I'm going to type in here TensorBoard --log dir equal to the path TensorFlow. Just go ahead and execute this. So it says that TensorBoard runs as a local web app at port 6006. Let us see how our graph looks like now. So this is how our graph looks like. It has two constant nodes here and one node for multiplication. So when I click on each of these nodes, there will be some information displayed about that node. So if you notice here, it is a float type. It also contains the value that is stored inside this particular constant node, which is 5. There are 0 inputs and 0 outputs. Similarly, for this constant node as well, it is a float type and it holds the value 6. Similarly, when I click on this particular node, we can see that it is again float type and it has two inputs, const and const_1. So these two inputs will be multiplied and will get the output. And now is the time to understand what are constants, placeholders and variables. So constant, as the name tells, that it will always produce a constant result. So I'll explain this with an example. So over here we have a couple of constant nodes. First node has values 3, another node has value 4. So when I execute this particular graph, I will always get the values 3 and 4, or you can say the values that are stored inside these two nodes. Now what if I want my graph to accept the external input? Now let me explain that with an example of our use case only. So here we want the features to be fed back to the graph that we cannot do with the help of constants. For that, what we need placeholders. Now a placeholder is nothing but a promise to provide a value later. Let us understand this with an example. So over here we have a couple of placeholders A and B of float 32 bits. And notice that we have initialized no values. Then we have one more tensor adder_node, which is nothing but the addition of two placeholders. Then we have first launched the session, and when we are running the session, we feed in the values of the two placeholders, as you can see here. So the value that will be fed back to the placeholder A is 1, 3. The value that will be fed back to the placeholder B will be 2, 4. Now let me execute this practically in my PyCharm. Let me remove all of this. All right. So I'll define a placeholder A, tf.placeholder, which is of float 32 bits. Similarly, B will be again a placeholder of tf.float 32 bits. Then we define one more node, adder_node, which is nothing but the addition of these two placeholders. Next up, we need to launch the graph. For that, I'll type here ses is equals to tf.session. And next up, we need to run the graph. Print ses.run and adder_node, and we need to feed the values of A and B as well. So for that I'll type in A 1, 3, B 2, 4. Now let us go ahead and execute this and see what happens. So here if you notice, I get the output as the sum of the two placeholders A and B. So the first value 1 will be assigned to the placeholder A and value 2 will be assigned to the placeholder B. So their sum will be 3. Similarly, A will be assigned to the value 3 and B will be assigned with value 4. Hence their sum will become 7. Now let's get back to our slides once more. Now the question here is how to modify the graph if I want new output for the same input. I mean, if I want my model to become trainable, I need some parameters that can change after every iteration so that the model output can be as close as possible to the actual output. For that, we need variables. Now, variables, as the name explains, the value of the variable will keep on changing. When you train a model, you use variables to hold and update parameters. Variables are in-memory buffers containing tensors. And remember, they must be explicitly initialized, unlike constants and placeholders. So let me explain you the code that is there in front of your screen. So here we have two variables, w and b, and I've initialized both of these variables with value 0.3 and minus 0.3. So if I train my model, the values of these two variables should change in order to reduce the output. Don't worry, you'll actually understand that when I explain you the loss function and optimizers. There you'll understand how we actually train our model and how actually variables are updated after every iteration. And in order to initialize the variables, we use tf.global_variables_initializer. This will add an operation to initialize the variables. Then we run ses.run init. This will run that operation. And remember, we only run it after launching the model. For now, let us go ahead and execute our first model. So this is our first model, guys. Over here we have imported the TensorFlow as TF. Then we have defined a couple of variables w and b, and we have initialized them with 0.3 and minus 0.3 values respectively. Then we have a placeholder x. After that we have defined one linear underscore model, which is nothing but w into x plus b. Then we have initialized the variable, launched the graph, and then we are running the session. And during that we are running the session and feeding the values of x. So this is basically what our model is. But we don't know how good it is yet. So obviously we cannot increase the efficiency without knowing the error. Let's understand the general flow of how we increase the efficiency. So first we create the model as you have seen in the previous slide. Then we calculate the loss. Loss is basically how far our model's output is from the actual output. Then we try to reduce the loss by updating the variables. Then again we check the loss and update the variables, and this process keeps on repeating until the loss becomes minimum. And now is the time to understand how we calculate loss. So in order to find out the loss, we should first define a placeholder, and we have named it as y, which will hold the desired output, or you can say the output that we already know. Then we will find the difference between the linear underscore model or the output of our model with that of the output that we already know, the placeholder y. Or you can say the difference between the model output and the actual output. Then we find the square of that particular difference, and then finally we sum all the squared errors that we have calculated in the above line. So we'll sum all of these squared differences. Then what we have done, we will run the session, calculate the loss, and we'll feed in the values of x and y. So I'll execute this practically. For that, I'll open my PyCharm. Let me remove all of this. So yeah, first we'll define a variable tf.variable with the initial value as 0.3, and it is tf.flow 32 bits. Then we will define one more variable, tf.variable minus 0.3, comma tf.float 32 bits. Then we'll define a placeholder that we will use in order to provide the inputs or to feed in the inputs. So let me throw in a comment here, inputs and outputs. And I can throw in one more comment here that says model parameters. Alrighty then. So now we'll define a placeholder x, which will actually hold the input values tf.placeholder. It will be of float type, 32 bits. Then we'll define one more placeholder y, which will actually hold the actual output of the model, which we already know. Placeholder tf.float 32 bits. Alright. And just between that, we'll define one more node, linear underscore model, which will give the output of this particular model, which we don't know. So that's the difference, guys. This y is a placeholder, and the values to this y will feed in when we are running the session. So that will be the actual output of the model. And this will be the output of the model, which will come after executing the model. So this will be nothing but w into x plus b. Fine. And now we are going to define the loss function. So I'll type in here squared underscore delta is equals to tf dot square linear underscore model minus y, which is nothing but the model output and the output that we already know. So linear underscore model is the output that we'll get through our model, and y is a placeholder which will have the output values that we will feed in.
Then we're going to define a loss function. So loss is equals to tf dot reduce underscore sum of all the squared delta. So we have defined a loss function here. Next up, what we need to do is initialize all the variables. For that, I'm going to type in here init is equals to tf dot global underscore variables underscore initializer. So this global variable initializer will add an operation to initialize a variable. Now we need to launch the graph. For that, we need to create a session object, and we know how to do it. Ses is equals to tf dot session. Yeah. And now we are going to write in here ses dot run init. So this will run the operation that we have defined when we were talking about global variable initializer. And after this, our variables are initialized. So now what we need to do is just run the session. Ses dot run, calculate the loss, feed in the values of x. So let it be 1, 2, 3, 4. And now the placeholder y, feed in the value of placeholder y. So we'll keep it as 0, comma, -1, comma, -2, comma, -3. Now let us go ahead and see how much is the loss. So the loss that we have calculated is 23.66. Let me just close this once. Now over here, if you notice, if I change the value of w and b, I can actually reduce my loss. Let me show you how I can do that. I'll take a pen. So instead of 0.3 and -0.3, if my w becomes -1 and my b becomes 1, then linear underscore model will become equal to y. That means the output of our model will actually become equal to the actual output, the output that we know. So let me tell you how it will happen. So our linear underscore model is w into x plus b. So we'll take the values of x one by one. So the first value of x is 1. So let me take that first. And the value of b is -1. So -1 into 1 plus 1 is equal to 0. So the value of our linear underscore model is 0. And over here also the value of y, that is our placeholder or the actual output, is also 0. Let us take the next value of x, which is nothing but 2. 1 -1 into 2 plus 1 is equal to what? -1, which is again equal to y. Similarly, -1 into 3 plus 1 is equal to -2, which is also equal to our placeholder y. Finally, if I take the last value of x, which is 4 plus 1, it will be equal to -3. So this is how, when we update the variables, we can actually reduce the loss. So here, if I keep the values of w and b as -1 and 1 respectively, the loss that I'll get will be 0. So this is how you can actually reduce the loss, by updating the variables. So when I was explaining variables, where I told you that in order to make the model trainable, we need to update the values of variables. So this is what I was talking about. So by changing the value of variables, we can actually reduce the loss. We can make the model output as close as possible to the actual output. Now, if I make this as -1.0 and this as 1.0, we should get 0 error. Let us see if that happens or not. So we have 0 loss. But over here, I have manually done it. I have manually updated the variables w and b. What if I want my model to do it on its own? What if I want the machine to learn the new values of w and b? That will minimize the loss. So at that time, we need optimizers. So for that, I'll open my slides once more. Let me remove all of this. Yeah, and keep this to its normal value, 0.3. It was plus 0.3, yeah, and this will be -0.3. Now I'll open my slides. So in order to increase the efficiency and minimize the loss and update the variables, we use optimizers. These optimizers modifies each variable according to the magnitude of the derivative of loss with respect to that variable. Now what does that mean? It means basically that an optimizer will check the magnitude of the derivative of loss. That means an optimizer will check the change in the loss with respect to the change in the variable. And if the loss is decreasing, then it will keep on changing the variable in that particular direction.
So here we'll use gradient descent optimizer. Let us understand this with an analogy. Suppose you are at the top of the mountain and your task is to reach the lake, which is present near the valley. And the catch here is that you are blindfolded. So how will you approach this task? One way of doing this is to observe the ground near you and move in the direction where the land tends to descend. Consider every step that you take as learning rate and the position as weight. The whole process is called as loss function. When you reach the lake, consider that point as global loss minimum. Now you can apply the same concept on our model as well. Where the ground tends to descend, similarly the optimizer checks in which direction should the variables be updated so as to decrease the loss, and will keep on updating the variables in that particular direction. So let's understand the math behind gradient descent optimizer. First we calculate the loss. How we do that? By summing all the square differences between the model output and the actual output and then dividing it by 2. So here our target output is nothing but the output that we know, and output is nothing but the model output. After that we calculate the change in the variable delta W. This is equal to the learning rate multiplied by the rate of change of loss with respect to that variable. After that, the new variable or the updated variable is equal to the sum of the change in the variable plus the old value of that particular variable. So it will be W plus delta W. Now let me simplify this equation for you. So over here when we are calculating delta Wj, which is equal to minus of learning rate into delta J by delta Wj, or you can say the rate of change of error with respect to that particular variable, we put in the values of J, then we find out the derivative and we get the equation as learning rate into summation of target I minus output I, that means the actual output minus the model output, into xj of I, which is nothing but your input. Fine guys, so we'll move forward and see how we can apply gradient descent in our model. Now in order to modify the variables in our model, we'll use the code that is there in front of your screen. Here we will first create an object of class tf.train.gradient-descent-optimizer, and it will implement the gradient descent algorithm. It takes one argument as the learning rate. The second part, this minimize, returns an operation that applies gradients. It will reduce the loss by updating the variables. Finally, just run the session and feed in the values of x and y, and then evaluate the variables w and b. So let me go to my PyCharm and execute this. Let me comment this line first. So after defining loss, we will optimize our model. We'll write in here optimizer equal to tf.train.gradient descent optimizer with a learning rate of 0.01. Learning rate is nothing but the steps in which you change your variable. Then what we do, we will write in here train is equal to optimizer.minimize loss. Alright. And after initializing the variable, we need to run the session. So for that I will use a for loop. So I'll type in here for I in range 1000 ses.run train, comma, feed in the values of x and y. So I'll just copy it from here and I'll paste it there. Alright. Then go ahead and evaluate the variables w and b. So we have got the new value of w as minus 0.9999969 and the new value of b as 0.999999082. Now if you can recall, when we were calculating it manually, we got the output for w as -1 and for b we got it as +1. And these two values are almost the same. So minus 0.9999 can be rounded off to -1 and 0.9999082 can be rounded off to +1. So this is how you actually build a model, then you calculate the loss, and then you train the model. So guys, this brings us to the most awaited topic of today's session, which is the implementation of NMI, that is our use case, which is Neville Mine Identifier. So guys, let me first tell you the steps that are involved in order to implement this use case. First, we need to process the data set that we have. We'll first read the data set, then we are going to define the features and labels. So what are labels? Labels are nothing but the class to which the pattern represents. In our case, it can be a rock or a mine. Then we need to encode the dependent variable. And here the dependent variable is nothing but your label. So we are going to encode those dependent variables. After that, we are going to divide the data set into two parts, one for training, another for testing. And by the end of this step, our data set is now ready. Next, we are going to use TensorFlow data structures for holding features, labels, etc. So here we'll be defining weights, biases, we'll have a couple of placeholders for inputs as well as for the desired output that we already know, and we'll also define one tensor that will be our model output. Then we are going to implement the model. We are going to write the logic in order to implement the model. Then what we are going to do, we are going to train the model on the training data that we have. So in this particular step, we have divided the data set into two parts, training and testing. We'll use that training data to train our model. Then we are going to calculate the error. That is how far your model output is from the actual output. And then we'll try to reduce this error. And when we reach to a point where the error becomes minimum, we are going to test our model on the test data. Or you can say we are going to make prediction on the test data. And that will give us the accuracy of our model. So this is how we are going to implement the use case. Now I'll open my PyCharm and execute this practically, guys. So guys, we'll first start with importing the necessary libraries. First, we'll import matplotlib, which is used for visualization, then TensorFlow, the NumPy, Pandas, and sklearn as well. So these are the libraries that we are going to use. So we need to import these libraries. Then we are going to read the data set. For that, we are going to use Pandas. So we're going to convert this data set into a data frame, a Pandas data frame, and we are going to give the path to where our file is stored or our data set is stored. Then we are going to define features and labels. So here, X will be our feature. So basically the first column till the 60th column will be our features, and the last column represents the label, as I've told you earlier as well. So the last column will be our label and it will be stored in Y. After that, we need to encode the dependent variable, which is nothing but our label. Now we'll perform label encoding first, and then we're going to perform one-hot encoding. So guys, I'll explain you one-hot encoding and label encoding with a pen. So suppose if I have labels like rock, then mine, then again rock, then one more mine. First we'll perform label encoding, in which I'll assign values to it. So suppose if I assign 0 to a rock and 1 to a mine, so I'll keep it that way for the rest of the rows as well. Alright, so now we'll perform one-hot encoding, in which we'll have two columns, one for mine and another for rock. So wherever the data represents a mine, it will be 1. So this basically represents a rock, so it will be 0. This row represents a mine, so it will be 1. This represents a rock, so it will be 0. Similarly, this represents a mine, so it will be 1. Now the second column, wherever the data represents a rock, we'll keep it as 1. So this represents a rock, we'll keep it as 1. This represents a mine, so let it be 0. This will again be 1 because it represents a rock. This represents a mine, so we'll keep it as 0. So this is how you perform one-hot encoding. So what is one-hot encoding? Basically, only one input will be active at one time. So basically, what is one-hot encoding? Only one input will be active. So let us move forward now. So this is the function that actually defines one-hot encoding. So this is where we have performed the one-hot encoding. Then what we are going to do, we are going to read the data set. So X is basically a feature and Y is one-hot encoded label. Then we are going to shuffle the data set. We need to shuffle the data set because the whole data set that we have, it is present in an order. For example, in the beginning we have mines and then we have rocks. So we need to shuffle it. So after doing that, we're going to split the data set into two parts, training and testing. How we're going to do that, you can see it over here. So we have defined the test size as 0.20, which means the 20% of the data set will be your testing data set. Now if you can go ahead and inspect the shape of the training and the testing data, although it's not necessary, but still if you want to go ahead and do it, you can do that as well. Then we are going to define the important parameters and variables to work with tensors. So first we are going to define learning rate. So we have seen what exactly learning rate is. Then we're going to define the epoch. Epoch basically means the total number of iterations that will be done in order to minimize the error. Then we're going to define a loss function, cost history. Then we have n_dim. So what is ndim? So basically ndim is nothing but the shape of your features which is stored in X. And that too, it will only include the columns, the number of columns. So then we'll print it, and you can still avoid this step if you don't want to print it, it's all fine. Then you define the number of classes. So since we have only two classes, that is mine and rock, we're going to keep it as 2. Then we're going to provide the model path, which will be nothing but the place where we want to store our model. So I've given the same path in which I'm currently working. So we'll see a couple of files created when we execute this model. Then we need to define the number of hidden layers, the number of neurons for each layer. So basically I've talked about hidden layers, neurons, multilayer perceptron, everything in detail in the previous tutorial. Then we have the number of neurons for hidden layer 1, 2, 3 and 4. So we're going to take 4 hidden layers. So this is nothing but an example of multi-layer perceptron.
So X is our placeholder in which we are going to feed in the input values, or you can say the data set. It is of float 32 bits. And then the shape of this particular tensor is none comma ndim. So ndim is what we have seen earlier. So if I write here none, which means it can be any value. Then we'll define a variable w, which will be initialized with zeros, and it will have shape n underscore dim, which we know what it is, and n underscore class, which is nothing but the class to which a pattern represents. So we have two classes here, so it'll be n underscore dim comma 2. Then we have one more variable b, we'll fill it with zeros, or we'll initialize it with zeros, and it'll have a shape of n underscore class, that is 2. Then we're going to define a placeholder y dash, which will be nothing but the output of our model that we already know. And its shape will be none comma n underscore class. None can be any value, and we know n underscore class is equal to 2 because we have only two classes, mine and a raw. So now we are going to define a model. We're going to name it as Multilayer Perceptron because it is an example of Multilayer Perceptron. So first we'll define the first hidden layer, in which it will be nothing but the matrix multiplication of your input and the weight, and then we're going to add it to the bias. Then we're going to pass it through a sigmoid activation function. Then the second hidden layer also the same thing will happen, and the input for the second hidden layer will be the output of the first hidden layer. So we're going to type in here layer underscore 1, and then we're going to define the weight, which will be h2. So matrix multiplication of that, and then add it to the bias. Similarly for hidden layer 3 as well. And in hidden layer 4, instead of using sigmoid activation function, we'll use ReLU activation function. And then finally comes the output layer, in which we're going to perform matrix multiplication, output of the previous hidden layer, and the weights, and then we're going to add biases to it. So now we need to define weights and biases for each layer. So h1 is the weight for the first hidden layer. So we're going to define that. It'll be a variable, and it'll be a truncated normal of n underscore dim and n underscore hidden underscore 1, which is nothing but the shape of this particular tensor or this particular variable. N underscore dim we know, and n underscore hidden underscore 1 is nothing but 60. Similarly for other weights as well. And the same goes for biases as well. Here we'll have shape which is equal to n underscore hidden underscore 1, hidden underscore 2, 3, and 4. And then finally the output bias will be equal to n underscore class, which will be nothing but 2 because we have only two classes. Then we need to initialize all the variable, which we have seen how to do that. After that, we're going to create a saver object in order to save our model. Then we're going to call the model that we have defined above. Then we're going to define the cost function and optimizer. Cost function is nothing but the loss function. So this is our loss function that we have defined here. So over here, if you notice, let me just show it to you. Yeah. So this is how we have defined a cost function. So we're going to use a softmax cross entropy, and logits y is nothing but your output, and labels y dash is nothing but your actual output, or you can say the output that we already know, and this is the model output. Then we're going to perform optimization. We're going to use gradient descent optimizer, and then will be the learning rate will be 0.03, which we have defined above, and then it will be minimizing the cost function or the loss. So this is how we'll optimize it. Then what we need to do, we need to create a session object that will launch the graph, and this will initialize all the variables. Then we need to calculate the cost and the accuracy for each epoch. How are we going to do that? We're going to use for loop for that. So first we'll define MSE underscore history and accurate history. We'll keep it empty. Then we're going to define for epoch in range training underscore epochs. Over here, first we'll run the training step. We're going to feed in the values of train underscore X and train underscore Y, which is nothing but the training data. Then we're going to run the cost function, or you can say the loss. And again, feed in the values of train underscore X and train underscore Y. Then what we're going to do, we're going to define cost history, which will be append the cost history comma cost. So whatever cost history we have, whatever cost we'll get it here, it will be appended and it will be here cost history. So we can see that for every epoch. That's why we are doing it. So it will be appending one by one. Then we're going to find out the correct prediction, which will be equal to tf.argmax y comma 1 and argmax y dash comma 1, which is nothing but the difference between the actual output and the model output. And after that, we're going to calculate the accuracy here. And then what we need to do, we'll define a parameter pred underscore y, which will be nothing but ses.run and the actual output, and feed in the test data in order to see how accurate our model is. Similarly, we're going to define MSE mean squared error, which will be nothing but the difference between the predicted value and the test value. Then we're going to launch the graph here, and we're going to find the MSE history.append. So this will actually keep on updating the MSE value for every epoch. Then we're going to find out the accuracy of the training data. So basically we'll be finding here the accuracy on the training data, not on the test data.
and we'll keep on appending so that for every epoch we can see that. Then we're going to print that value for every epoch. After that, we're going to define one more parameter, save underscore path, which will be saver.save ses comma model. So this will actually save the model in the model path. So now we're going to plot the graph of MSE and accuracy. MSE is nothing but the mean squared error, and accuracy will be there on your test data. And mean squared error, we know what it is. So we have calculated MSE here, if you can notice. Then what we need to do, we need to print the final accuracy. For that, we'll first find out the correct predictions made by our model. And then we're going to find out the accuracy. And finally, we're going to print it by running the session and feeding in the values of test data in X and Y. Finally, we need to print in the final mean squared error, which will be nothing but pred underscore y, ses.run y comma feed dict. So y is our actual output, and feed underscore dict is just we're feeding the test input. Then we're going to calculate MSE mean squared error, which is nothing but the difference between the predicted value and the actual value which is there in the test data, and then just go ahead and print this. So we'll now start training our model. So let us go ahead and run this. So in the beginning, if you notice, it has printed the shape, and then it is printing the test and the training data shape as well. And now it has started training our model. So you can notice the training accuracy that we are getting here. So it'll keep on repeating this process for 1,000 times, for 1,000 epochs basically. So 1,000 iterations. After that, our model will be trained. So guys, this is the accuracy that we have got on our test data. So this y-axis represents the accuracy, and the x-axis represents the number of epochs. So we have 1,000 epochs here. That means it's going to train it 1,000 times. So let me just close it now. And yeah, so we have got the test accuracy as 85%, and the average mean squared error is 24.4505. And our model is saved in this particular directory, which is my current working directory, guys. Now let me close this and open the project structure, and you can see a couple of files that have been created here. So guys, we have successfully trained our model and we have saved it as well. Now what we are going to do, we are going to restore this model. So basically we'll be providing some input to this particular model, and it will predict the outcome for us. So it will predict whether it is a rock or a mine. So the whole code remains the same. It's just that you need to provide the model path, which you have done when you were actually defining the model and training it. And then what you need to do is you need to again create one saver object, and after that finally you need to call this restore function in order to restore the model that we have. Over here you're going to provide two arguments. One is ses and another is nothing but your model underscore path, which we have given in the previous step. So guys, this is how it is, and we're going to provide the input from the data set only, which will be from row 93 till 101, but it won't include the 101th row. It will only be that till 100th row. Fine guys, so let us go ahead and run this. So guys, this is how the predicted values looks like. Over here, the original class was R. We predicted a value is 1, which means we have correctly predicted this particular class, and we have got the accuracy as 100%. Similarly, for other values as well. But if you notice over here, we have got the accuracy as 0 because we have predicted the wrong value of the class. Similarly, here as well, it is a mine, but we have predicted it as a rock. So that's why we have got accuracy as 0. So guys, this is how we actually train a model and we restore it. So this is all about Neville Mine Identifier. Today I'll be covering all the fundamentals of neural networks. After that, we'll be using that knowledge in order to solve a real life problem. So let's take a look at what we are going to implement in this session, and after that we'll be discussing the agenda. So this is the problem statement, guys. We need to figure out if the banknotes are real or fake. And for that, we'll be using artificial neural networks. And obviously, we need some sort of data in order to train our network. So let us see how the data set looks like. So over here, I've taken a screenshot of the data set with few of the rows. In it, data were extracted from images that were taken from genuine and forged banknote-like specimens. After that, wavelet transform tools were used to extract features from those images. And these are few features that I'm highlighting with my cursor. And the final column, or the last column, actually represents the label. So basically, label tells us to which class that pattern represents, whether that pattern represents a fake note or it represents a real note. Let us discuss these features and labels one by one. So the first feature or the first column is nothing but variance of a wavelet transformed image. The second column is about skewness. The third is curtices of wavelet transformed image. And finally, fourth one is entropy of the image.
After that, when I talk about label, which is nothing but my last column, over here, if the value is 1, that means the pattern represents a real node, whereas when value is 0, that means it represents a fake node. So guys, let's move forward and we'll see what are the various steps involved in order to implement this use case. So over here, we'll first begin by reading the data set that we have. We'll define features and labels. After that, we are going to encode the dependent variable. And what is a dependent variable? It is nothing but your label. Then we are going to divide the data set into 2 parts, one for training, another for testing. After that, we'll use TensorFlow data structures for holding features, labels, etc. And TensorFlow is nothing but a Python library that is used in order to implement deep learning models, or you can say neural networks. Then we'll write the code in order to implement the model. And once this is done, we will train our model on the training data. We'll calculate the error. Error is nothing but your difference between the model output and the actual output. And we'll try to reduce this error. And once this error becomes minimum, we'll make prediction on the test data and we'll calculate the final accuracy. So guys, let me quickly open my PyCharm and I'll show you how the output looks like. So this is my PyCharm, guys. Over here, I've already written the code in order to execute the use case. I'll go ahead and run this and I'll show you the output. So over here, as you can see, with every iteration, the accuracy is increasing. So let me just stop it right here. So what I'll do, I'll open my slides once more and we'll discuss the fundamentals of neural networks that are required in order to implement this use case. So we'll look at the agenda, what are the things we need to discuss. So this is the agenda here, guys. We'll start by first understanding why we need neural networks. Then we'll focus on what is the motivation behind neural networks and what exactly are neural networks. After that, we'll understand what is single layer perceptron and multi-layer perceptron. And then I'll tell you how to implement the use case that I was talking about in the beginning. And finally, we'll discuss various applications of neural networks. So we'll move forward and we'll understand why we need neural networks. So in order to understand why we need neural networks, we are going to compare the approach before and after neural networks. And we'll see what were the various problems that were there before neural networks. So earlier, conventional computers use an algorithmic approach. That is, the computer follows a set of instructions in order to solve a problem. And unless the specific steps that the computer needs to follow are known, the computer cannot solve the problem. So obviously we need a person who actually knows how to solve that problem, and he or she can provide the instructions to the computer as to how to solve that particular problem, right? So we first should know the answer to that problem, or we should know how to overcome that challenge or problem which is there in front of us. Then only we can provide instructions to the computer. So this restricts the problem solving capability of conventional computers to problems that we already understand and know how to solve. But what about those problems whose answer we have no clue of? So that's where our traditional approach was a failure. So that's why neural networks were introduced. Now let us see what was the scenario after neural networks. So neural networks basically process information in a similar way the human brain does. And these networks, they actually learn from examples. You cannot program them to perform a specific task. They will learn from their examples, from their experience. So you don't need to provide all the instructions to perform a specific task. And your network will learn on its own with its own experience. Alright, so this is what basically neural network does. So even if you don't know how to solve a problem, you can train your network in such a way that with experience, it can actually learn how to solve the problem. So that was a major reason why neural networks came into existence. So we'll move forward and we'll understand what is the motivation behind neural networks. So these neural networks are basically inspired by neurons, which are nothing but your brain cells. And the exact working of the human brain is still a mystery though. So as I've told you earlier as well, that neural networks work like human brain, and so the name. And similar to a newborn human baby, as he or she learns from his or her experience, we want a network to do that as well. But we want it to do very quickly. So here's a diagram of a neuron. Basically, a biological neuron receives input from other sources, combines them in some way, perform a generally non-linear operation on the result, and then outputs the final result. So here if you notice these dendrites will receive signals from the other neurons. Then what will happen, it will transfer it to the cell body. The cell body will perform some function. It can be summation, it can be multiplication. So after performing that summation on the set of inputs, via axon it is transferred to the next neuron. Now let's understand what exactly are artificial neural networks. It is basically a computing system that is designed to simulate the way the human brain analyzes and processes the information. Artificial neural networks has self-learning capabilities that enable it to produce better results as more data becomes available. So if you train your network on more data, it will be more accurate. So these neural networks, they actually learn by example. And you can configure your neural network for specific applications. It can be pattern recognition or it can be data classification, anything like that, all right? So because of neural networks, we see a lot of new technology has evolved. From translating web pages to other languages, to having a virtual assistant to order groceries online, to conversing with chatbots. All of these things are possible because of neural networks. So in a nutshell, if I need to tell you, artificial neural network is nothing but a network of various artificial neurons. Alright, so let me show you the importance of neural network with two scenarios, before and after neural network. So over here we have a machine and we have trained this machine on 4 types of dogs, as you can see where I'm highlighting with my cursor. And once the training is done, we provide a random image to this particular machine which has a dog. But this dog is not like the other dogs on which we have trained our system on. So without neural networks, our machine cannot identify that dog in the picture, as you can see it over here. Basically, our machine will be confused. It cannot figure out where the dog is. Now, when I talk about neural networks, even if we have not trained our machine on this specific dog, but still it can identify certain features of the dogs that we have trained on, and it can match those features with the dog that is there in this particular image, and it can identify that dog. So this happens all because of neural networks. So this is just an example to show you how important are neural networks. Now I know you all must be thinking how neural networks work. So for that, we'll move forward and understand how it actually works. So over here, I'll begin by first explaining a single artificial neuron that is called as perceptron. So this is an example of a perceptron. Over here, we have multiple inputs, x1, x2, dash, 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 till xn. And we have corresponding weights as well, w1 for x1, w2 for x2, similarly wn for xn. Then what happens, we calculated the weighted sum of these inputs. And after doing that, we pass it through an activation function. This activation function is nothing but it provides a threshold value. So above that value, my neuron will fire, else it won't fire. So this is basically an artificial neuron. So when I talk about a neural network, it involves a lot of these artificial neurons with their own activation function and their processing element. Now we'll move forward and we'll actually understand various modes of this perceptron or single artificial neuron. So there are 2 modes in a perceptron. One is training, another is using mode. In training mode, the neuron can be trained to fire for particular input patterns, which means that we'll actually train our neuron to fire on certain set of inputs and to not fire on the other set of inputs. That's what basically training mode is. When I talk about using mode, it means that when a taught input pattern is detected at the input, its associated output becomes the current output, which means that once the training is done and we provide an input on which the neuron has been trained on, so it will detect the input and will provide the associated output. So that's what basically using mode is. So first you need to train it, then only you can use your perceptron or your network. So these were the 2 modes, guys. Next up, we'll understand what are the various activation functions available. So these are the 3 activation functions, although there are many more, but I've listed down 3. Step function. So over here, the moment your input is greater than this particular value, your neuron will fire, else it won't. Similarly for sigmoid and sine function as well. So these are 3 activation functions. There are many more that I've told you earlier as well. So yeah, these are the 3 majorly used activation functions. Next up, what we are going to do, we are going to understand how a neuron learns from its experience. So I'll give you a very good analogy in order to understand that. And later on, when we talk about neural networks, or you can say multiple neurons in a network, I'll explain you the math behind it. I'll explain you the math behind learning, how it actually happens. So right now, I'll explain you with an analogy. And guys, trust me, that analogy is pretty interesting. So I know all of you must have guessed it. So these are 2 beer mugs, and all of you who love beer can actually relate to this analogy a lot. And I know most of you actually love beers, so that's why I've chosen this particular analogy, so that all of you can relate to it. All right, jokes apart. So fine, guys. So there's a beer festival happening near your house, and you want to badly go there. But your decision actually depends on 3 factors. First is how is the weather, whether it is good or bad. Second is your wife or husband is going with you or not. And the third one is any public transport is available. So on these 3 factors, your decision will depend whether you will go or not. So we'll consider these 3 factors as inputs to our perceptron, and we'll consider our decision of going or not going to the beer festival as our output. So let us move forward with that. And we'll see what are the various inputs that I'm talking about. So the first input is how is the weather. We'll consider it as x1. So when weather is good, it'll be 1, and when it is bad, it'll be 0. Similarly, your wife is going with you or not, so that'll be your x2. If she is going, then it's 1. If she's not going, then it's 0. Similarly, for public transport, if it is available, then it is 1, else it is 0. So these are the 3 inputs that I'm talking about. Let's see the output. So output will be 1 when you're going to the beer festival, and output will be 0 when you want to relax at home. You want to have beer at home only. You don't want to go outside. So these are the 2 outputs, whether you're going or you're not going. Now what a human brain does. Over here, okay, fine. I need to go to the beer festival. But there are 3 things that I need to consider. But will I give importance to all these factors equally? Definitely not. There'll be certain factors which will be of higher priority for me. I'll focus on those factors more. Whereas few factors won't affect that much to me. Alright, so let's prioritize our inputs or factors. So here our most important factor is weather. So if weather is good, I love beer so much that I don't care even if my wife is going with me or not, or if there is a public transport available. So I love beer that much that if weather is good, then definitely I'm going there. That means when X1 is high, output will be definitely high. So how we do that, how we actually prioritize our factors, or how we actually give importance more to a particular input and less to another input in a perceptron or in a neuron. So we do that by using weights. So we assign high weights to the more important factors or more important inputs, and we assign low weights to those particular inputs which are not that important for us. So let's assign weights, guys. So weight W1 is associated with input X1, W2 with X2, and similarly W3 with X3. Now, as I've told you earlier as well, that weather is a very important factor, so I'll assign a pretty high weight to weather and I'll keep it as 6. Similarly, W2 and W3 are not that important, so I'll keep it as 2, 2. After that, I've defined a threshold value as 5, which means that when the weighted sum of my input is greater than 5, then only my neuron will fire, or you can say then only I'll be going to the beer festival. Alright, so I'll use my pen and we'll see what happens when weather is good. So when weather is good, our X1 is 1, our weight is 6, we'll multiply it with 6. Then, if my wife decides that she is going to stay at home and she will probably be busy with cooking and she doesn't want to drink beer with me, so she's not coming. So that input becomes 0. 0 into 2 will actually make no difference because it will be 0 only. Then again, there is no public transport available also. Then also this will be 0 into 2. So what output I get here? I get here as 6. And notice the threshold value, it is 5. So definitely 6 is greater than 5. That means my output will be 1. Or you can say my neuron will fire, or I'll actually go to the beer festival. So even if these 2 inputs are 0 for me, that means my wife is not willing to go with me and there is no public transport available, but weather is good, which has very high weight value and it actually matters a lot to me. So if that is high, it doesn't really matter whether the 2 inputs are high or not. I will definitely go to the beer festival. Alright, now I'll explain you a different scenario. So over here our threshold was 5. But what if I change this threshold to 3? So in that scenario, even if my weather is not good, I'll give it a 0. So 0 into 6. But my wife and public transport both are available. Alright, so 1 into 2 plus 1 into 2, which is equal to 4. And it is definitely greater than 3. Then also my output will be 1. That means I will definitely go to the beer festival even if weather is bad. And my neuron will fire. So these are the 2 scenarios that I have discussed with you. Alright, so there can be many other ways in which you can actually assign weight to your problem or to your learning algorithm. So these are the 2 ways in which you can assign weights and prioritize your inputs or factors on which your output will depend. So obviously in real life, all the inputs or all the factors are not as important for you. So you actually prioritize them. And how you do that in perceptron, you provide high weight to it. This is just an analogy so that you can relate to a perceptron to a real life. We'll actually discuss the math behind it later in the session as to how a network or a neuron learns. Alright, so how the weights are actually updated and how the output is changing, that all those things we'll be discussing later in the session. But my aim is to make you understand that you can actually relate to a real life problem with that of a perceptron. Alright, and in real life problems are not that easy. They are very, very complex problems that we actually face. So in order to solve those problems, a single neuron is definitely not enough. So we need networks of neurons. And that's where artificial neural network, or you can say multi-layer perceptron, comes into the picture. Now let us discuss that.
Multilayer Perceptron or Artificial Neural Network. So this is how an artificial neural network actually looks like. So over here we have multiple neurons present in different layers. The first layer is always your input layer. This is where you actually feed in all of your inputs. Then we have the first hidden layer, then we have second hidden layer, and then we have the output layer. Although the number of hidden layers depend on your application, on what are you working, what is your problem. So that actually determines how many hidden layers you'll have. So let me explain you what is actually happening here. So you provide in some input to the first layer, which is nothing but your input layer. You provide inputs to these neurons. All right. And after some function, the output of these neurons will become the input to the next layer, which is nothing but your hidden layer 1. Then these hidden layers also have various neurons. These neurons will have different activation functions. So they'll perform their own function on the inputs that it receives from the previous layer. And then the output of this layer will be the input to the next hidden layer, which is hidden layer 2. Similarly, the output of this hidden layer will be the input to the output layer. And finally, we get the output. So this is how basically an artificial neural network looks like. Now let me explain you this with an example. So over here, I'll take an example of image recognition using neural networks. So over here, what happens, we feed in a lot of images to our input layer. Now this input layer will actually detect the patterns of local contrast and then will feed that to the next layer, which is hidden layer 1. So in this hidden layer 1, the face features will be recognized. We'll recognize eyes, nose, ears, things like that. And then that will be again fed as input to the next hidden layer. And in this hidden layer, we'll assemble those features and we'll try to make a face. And then we'll get the output, that is the face will be recognized properly. So if you notice here, with every layer, we are trying to get a more abstract version or the generalized version of the input. So this is how basically an artificial neural network, how it works. All right. And there's a lot of training and learning which is involved that I'll show you now. Training a neural network. So how we actually train a neural network. So basically the most common algorithm for training a network is called backpropagation. So what happens in backpropagation, after the weighted sum of inputs and passing through an activation function and getting the output, we compare that output with the actual output that we already know. We figure out how much is the difference. We calculate the error. And based on that error, what we do, we propagate backwards. And we'll see what happens when we change the weight. Will the error decrease or will it increase? And if it increases, when it increases, by increasing the value of the variables or by decreasing the value of variables. So we kind of calculate all those things and we update our variables in such a way that our error becomes minimum. And it takes a lot of iterations. Trust me guys, it takes a lot of iterations. We get output a lot of times and then we compare it with the model, with the actual output. Then again we propagate backwards, we change the variables, then again we calculate the output, we compare it again with the desired output of the actual output. Then again we propagate backwards. So this process keeps on repeating until we get the minimum value. All right. So there's an example that is there in front of your screen. Don't be scared of the terms that I used. I'll actually explain you with an example. So this is the example over here. We have 0, 1 and 2 as inputs and our desired output or the output that we already know is 0, 1 and 4. All right. So over here we can actually figure out that desired output is nothing but twice of your input. But I'm training a computer to do that, right? The computer is not a human. So what happens, I actually initialize my weight, I keep the value as 3. So the model output will be 3 into 0 is 0, 3 into 1 is 3, 3 into 2 is 6. Now obviously it is not equal to your desired output, so we check the error. Now the error that we have got here is 0, 1 and 2, which is nothing but your difference. So 0 minus 0 is 0, 3 minus 2 is 1, 6 minus 4 is 2. Now this is called an absolute error. After squaring this error, we get square error, which is nothing but 0, 1 and 4. All right. So now what we need to do, we need to update the variables. We have seen that the output that we got is actually different from the desired output. So we need to update the value of the weight. So instead of 3, our computer makes it as 4. After making the value as 4, we get the model output as 0, 4 and 8. And then we saw that the error has actually increased. Instead of decreasing, the error has increased. So after updating the variable, the error has increased. So you can see that square error is now 0, 4 and 16 and earlier it was 0, 1 and 4. That means we cannot increase the weight value right now. But if we decrease that, make it as 2, we get the output which is actually equal to desired output. But is it always the case that we need to only decrease the weight? Definitely not. So in this particular scenario, whenever I'm increasing the weight, error is increasing, and when I'm decreasing the weight, error is decreasing. But as I've told you earlier as well, this is not the case every time. Sometimes you need to increase the weight as well. So how we determine that? All right, fine guys, this is how basically a computer decides whether it has to increase the weight or decrease the weight. So what happens here, this is a graph of square error versus weight.
So over here what happens, suppose your square error is somewhere here and your computer, it starts increasing the weight in order to reduce the square error. And it notices that whenever it increases the weight, square error is actually decreasing. So it'll keep on increasing until the square error reaches a minimum value. And after that, when it tries to still increase the weight, the square error will increase. So at that time, our network will recognize that whenever it is increasing the weight after this point, error is increasing. So therefore, it will stop right there, and that will be our weight value. Similarly, there can be one more scenario. Suppose if we increase the weight, but then also the square error is increasing. So at that time, we cannot increase the weight. At that time, computer will realize, okay, fine, whenever I'm increasing the weight, the square error is increasing. So it'll go in the opposite direction. So it'll start decreasing the weight and it'll keep on doing that until the square error becomes minimum. And the moment it decreases more, the square error again increases. So our network will know that whenever it decreases the weight value, the square error is increasing. So that point will be our final weight value. So guys, this is what basically backpropagation in a nutshell is. Fine, so we'll move forward, and now is the correct time to understand how to implement the use case that I was talking about at the beginning. That is how to determine whether a node is fake or real. So for that, I'll open my PyCharm. This is my PyCharm again, guys. Let me just close this. All right. So this is the code that I've written in order to implement the use case. So over here, what we do, we import the first important libraries which are required. Matplotlib is used for visualization. TensorFlow we know in order to implement the neural networks. NumPy for arrays, pandas for reading the data set, similarly sklearn for label encoding as well as for shuffling, and also to split the data set into training and testing parts. So we'll begin by first reading the data set, as I've told you earlier as well when I was explaining the steps. So what I'll do, I'll use pandas in order to read the CSV file which has the data set. After that, I'll define features and labels. So X will be my feature and Y will contain my label. So basically X includes all the columns apart from the last column, which is the fifth one. And because the indexing starts from 0, that's why we have written 0 till 4th. So it won't include the 4th column. All right. And so our last column will actually be our label. Then what we need to do, we need to encode the dependent variable. So the dependent variable, as I've told you earlier as well, is nothing but your label. So I've discussed encoding in TensorFlow tutorial. You can go through it and you can actually get to know why and how we do that. Then what we have done, we have read the data set. Then what we need to do is to split our data set into training and testing. And these are all optional steps. You can print the shape of your training and test data. If you don't want to do it, it's still fine. Then we have defined learning rate. So learning rate is actually the steps in which the weights will be updated. All right. So that is what basically learning rate is. Then when we talk about epochs, means iterations. Then we have defined course history. That will be an empty NumPy array, and its shape will be 1, and it will include the float type objects. Then we have defined ndim, which is nothing but your x shape of axis 1, which means your column. Then we'll print that. After that, we have defined the number of classes. So there can be only 2 classes, whether the node can be fake or it can be real. And this model path I've given in order to save my model. So I've just given a path where I need to save it. So I'll just save it here only in the current working directory. Now is the time to actually define our neural network. So we'll first make sure that we have defined the important parameters like hidden layers, number of neurons in hidden layers. So I'll take 10 neurons in every hidden layer and I'm taking 4 layers like that. Then X will be my placeholder, and the shape of this particular placeholder is none, comma n underscore dim. N underscore dim value, I'll get it from here, and none can be any value. I'll define one variable W and I'll initialize it with zeros, and this will be the shape of my weight. Similarly for bias as well, this will be the particular shape, and there will be one more placeholder y dash, which will actually be used in order to provide us with the actual output of the model. There'll be one model output and there'll be one actual output, which we use in order to calculate the difference, right? So we'll feed in the actual values of the labels in this particular placeholder y dash. And now we'll define the model. So over here we have named the function as Multilayer Perceptron, and in it we'll first define the first layer. So the first hidden layer, and we are going to name it as layer underscore 1, which will be nothing but the matrix multiplication of x and weights of h1, that is the hidden layer 1, and that will be added to your biases b1. After that, we'll pass it through a sigmoid activation function. Similarly, in layer 2 as well, matrix multiplication of layer 1 and weights of h2. So if you can notice, layer 1 was the network layer just before the layer 2, right? So the output of this layer 1 will become input to the layer 2. And that's why we have written layer underscore 1. It will be multiplied by weights h2, and then we'll add it with the bias. Similarly, for this particular hidden layer as well, and this particular layer as well. But over here, we are going to use the ReLU activation function instead of sigmoid. Then we are going to define the weights and biases. So this is how we basically define weights. So weights H1 will be a variable which will be a truncated normal with the shape of n underscore dim and n underscore hidden underscore 1. So these are nothing but your shapes. All right. And after that, what we have done, we have defined biases as well. Then we need to initialize all the variables. So all these things actually I've discussed in brief when I was talking about TensorFlow. So you can go through TensorFlow tutorial at any point of time if you have any question. We have discussed everything there. Since in TensorFlow, we need to initialize the variables before we use it. So that's how we do it. We first initialize it and then we need to run it. That's when your variables will be initialized. After that, we are going to create a saver object. And then finally, I'm going to call my model. And then comes the part where the training happens. Cost function. Cost function is nothing but you can say an error that will be calculated between the actual output and the model output. All right, so y is nothing but our model output and y dash is nothing but the actual output or the output that we already know. All right, and then we are going to use a gradient descent optimizer to reduce the error. Then we are going to create a session object as well. And finally, what we are going to do, we are going to run the session. So this is how we basically do that. For every epoch, we will be calculating the change in the error as well as the accuracy that comes after every epoch on the training data. After we have calculated the accuracy on the training data, we are going to plot it for every epoch how the accuracy is. And after plotting that, we are going to print the final accuracy which will be on our test data. So using the same model, we'll make prediction on the test data. And after that, we are going to print the final accuracy and the mean squared error. So let's go ahead and execute this, guys. All right, so training is done. And this is the graph we have got for accuracy versus epoch. This is accuracy, y-axis represents accuracy, whereas this is epochs. We have taken 100 epochs and our accuracy has reached somewhere around 99%. So with every epoch, it is actually increasing. Apart from a couple of instances, it is actually keep on increasing. So the more data you train your model on, it will be more accurate. Let me just close it. So now the model has also been saved where I wanted it to be. This is my final test accuracy and this is the mean squared error. All right, so these are the files that will appear once you save your model. These are the 4 files that I've highlighted. Now what we need to do is restore this particular model. And I've explained this in detail how to restore a model that you have already saved. So over here what I'll do, I'll take some random range. I've taken it actually from 754 to 768. So all the values in the row of 754 and 768 will be fed to our model and our model will make prediction on that. So let us go ahead and run this. So when I'm restoring my model, it seems that my model is 100% accurate for the values that I've fed in. So whatever values that I have actually given as input to my model, it has correctly identified its class, whether it's a fake node or a real node. Because 0 stands for fake node and 1 stands for real node, okay? So original class is nothing but which is there in my data set, so it is 0 already. And what prediction my model has made is 0. That means it is fake. So accuracy becomes 100%. Similarly for other values as well. Fine guys, so this is how we basically implement the use case that we saw in the beginning. So I'll quickly discuss few applications of neural networks. So in the slide you can notice that I've listed down only 2 applications, although there are many more. So neural networks in medicine. Artificial neural networks are currently a very hot research area in medicine, and it is believed that they will receive extensive application to biomedical systems in the next few years. And currently the research is mostly on modeling parts of human body and recognizing diseases from various scans. For example, it can be cardiograms, CAT scans, ultrasonic scans, etc. And currently the research is going mostly on 2 major areas. First is modeling and diagnosing the cardiovascular system. So neural networks are used experimentally to model the human cardiovascular system. Diagnosis can be achieved by building a model of the cardiovascular system of an individual and comparing it with the real-time physiological measurements taken from the patient. And trust me guys, if this routine is carried out regularly, potential harmful medical conditions can be detected at an early stage and thus make the process of combating disease much easier. Apart from that, it is currently being used in electronic noses as well. Electronic noses have several potential applications in telemedicine. Now let me just give you an introduction to telemedicine. Telemedicine is the practice of medicine over long distance via a communication link. So what the electronic noses will do, they would identify odors in the remote surgical environment. These identified odors would then be electronically transmitted to another site where an door generation system would recreate them. Because the sense of the smell can be an important sense to the surgeon, telesmell would enhance telepresent surgery. So these are the two ways in which you can use it in medicine. You can use it in business as well, guys. So business is basically a diverted field with several general areas of specialization such as accounting or financial analysis. Almost any neural network application would fit into one business area or financial analysis. Now there is some potential for using neural networks for business purposes, including resource allocation and scheduling. I've listed down two major areas where it can be used. One is marketing. So there is a marketing application which has been integrated with a neural network system. The airline marketing tactician is a computer system made of various intelligent technologies, including expert systems. A feedforward neural network is integrated with the AMT, which is nothing but airline marketing tactician, and was trained using backpropagation to assist the marketing control of airline seat allocation. So it has wide applications in marketing as well. Now the second area is credit evaluation. Now I'll give you an example here. The HNC company has developed several neural network applications, and one of them is the credit scoring system, which increases the profitability of existing model up to 27%. So these are few applications that I'm telling you guys. Neural network is actually the future. People are talking about neural networks everywhere, and especially after the introduction of GPUs and the amount of data that we have now, neural network is actually spreading like plague right now.
In this video, I'll introduce you the idea of gradient descent, which underlies not only how neural network works and learn, but how a lot of other machine learning works as well, and what those hidden layers of neurons end up actually looking for. So just to remind you guys that our goal here is the recognition of the handwritten digits, and these digits are rendered on a 28 by 28 pixel grid, each pixel with some grayscale value between 0 and 1. Those are what determine the activations of the 784 neurons in the input layer, and these activation for each neuron is in the following layers is based on a weighted sum of the activations in the previous layer plus some special number called the bias. Then you compute that sum with some other function like the sigmoid or a ReLU function. And we also discussed how a perceptron works and behaves like a function. Obviously, the perceptron isn't a complete model of human decision making. But what the example illustrates is how a perceptron can weigh up different kinds of evidence in order to make decisions. And it should seem plausible that a complex network of perceptron could make quite subtle decisions. In this network, the first column of perceptron is making very simple decisions by weighing the input evidence. What about the perceptrons in the second layer? Each of those perceptron is making a decision by weighing up the results from the first layer of the decision making. In this way, a perceptron in the second layer can make a decision at a more complex and more abstract level than the perceptron in the first layer. In total, given that somewhat arbitrary choice of the two hidden layers with 16 neurons, the network has about 13,000 weights and biases that we can adjust, and these values that determine what exactly the network actually does. So here we are going to learn how the network learns. What we want is an algorithm where you can show this network a series of training data which comes in the form of different images of handwritten digits along with labels for what they are supposed to be, and it will adjust those 13,000 weights and biases so as to improve its performance on the training data. Hopefully this layer structure will mean that what it learns generalizes to images beyond that training data as well. Now we'll use the MNIST dataset here, which contains tens of thousands of scanned images of handwritten digits, together with their correct classification. The MNIST names comes from the fact that it is a modified subset of two datasets collected by NIST, which is the United States National Institute of Standards and Technology. The data comes in two parts. The first part contains 60,000 images to be used as training data. These images are scanned handwritten samples from 250 people. Now the second part of the MNIST dataset is 10,000 images to be used as the test data. Again, these are 28 by 28 grayscale images. What we'd like is an algorithm which lets us find weights and biases so that the output from the network approximates to the desired output of all the training inputs. Now, to quantify how we'll be achieving this goal, we define here a cost function, which is sometimes referred to as a loss or an objective function. Here, the W denotes the collection of all the weights in the network, P denotes all the biases, N is the total number of training inputs. For us, it is 60K, and A is the vector of outputs from the network when X is the input. and the sum is over all the training inputs, which is the x. Of course, the output depends on the values of x, w, and b, which are the inputs, weights, and biases. Now the cost becomes small, that is the function c tends to 0 precisely when y of x is approximately equal to the output for all the training inputs x. So our training algorithm has done a good job if it can find the weights and biases so that the cost is equal to 0. By contrast, it's not doing so well when we say that the cost is large. So the aim of our training algorithm will be to minimize the cost as a function of the weights and biases. And in other words, we want to find a set of weights and biases which makes the cost as small as possible. We'll do that using an algorithm known as the gradient descent. We are just going to initialize all those weights and bias totally randomly. What we do is we define a cost function as a way of telling the computer what is good and what is bad. To do this, we need to add up the squares of the differences between each of the given outputs, which are the given activations, and the value you want them to have. And this is what we call the cost of a single training example. This sum is small when the network confidently classifies the image correctly. Now, the aim of our training algorithm will be to minimize the cost as a function of weights and biases. So then what we do is consider the average cost of all these tens and thousands of training examples. The way it's defined depends upon the network's behavior over all the tens of thousands of the pieces of the training data. That's a lot to think about. How do you find an input that minimizes the value of this function? For the most part, making changes to the weights and biases won't cause any change at all in the number of training images classified correctly. That makes it difficult to figure out how to change the weights and biases to get improved performance. If we instead use a smooth cost function like the quadratic cost, it turns out to be easy to figure out how to make small changes in weights and biases so as to get an improvement in the cost. So for now, we are going to imagine that we have been simply given a function of many variables, and what we want is to minimize that function. Those of you from the calculus background will know that you can sometimes figure out that minimum explicitly. A more flexible tactic is to start from any old input and figure out in which direction you should step out to make the output low. Specifically, if you can figure out the slope of a function where you are, then if you are shifting towards left, then the slope is positive, and if you are shifting towards right, the slope can be negative. It will be the reverse. So if we do this repeatedly at each point, checking the next slope and taking the appropriate step, we're going to approach some local minimum of the function. But that's not always feasible for really complicated functions. Now, really complicated functions can have a lot of minimas. There is a beautiful analogy which suggests an algorithm which works pretty well. We start by thinking of our function as a kind of a valley. What we do is we imagine a ball rolling down the slope of the valley, and our everyday experience tells us that the ball will eventually roll to the bottom of the valley. Perhaps we can use this idea as a way to find the minimum of the function. Now, people familiar with multivariable calculus will know that the gradient of a function gives you the direction of the steepest ascent. Basically, which direction should you step to increase the function most quickly, naturally enough. Taking the negative of that gradient gives you the direction to step that decreases the function most quickly. The algorithm for computing this gradient efficiently, which is the heart of how a neural network learns, is also known as backpropagation. So this process of repeatedly nudging an input of a function by some multiple of the negative gradient is known as the gradient descent. You'll see in our network an adjustment to one of the weights might have a much greater impact on the cost function than the adjustment to other weights. So if we take a particular cost function, suppose 6 by 4 x squared plus 2 by 4 y squared. So this is just a simple example. Now what we do is compute its gradient at some particular point. Then what you can say is that the changes to the first variable, which is 6 by 4 x squared, has 3 times the importance as the changes to the second variable. The gradient of the cost function is one more layer of complexity that still tells us what nudges to all these weights and biases cause the fastest change to the value of the cost function. So when you initialize the network with random weights and biases and adjust them many times based on this gradient descent process, how well does it actually perform on images that it's never seen before? Now, if you play around with this hidden layer structure and make a couple of tweaks, you can get the accuracy up. Now, I just think there's something incredible about any network doing this well on images that it's never seen before, given that we never specifically told it what patterns to look for. Now here we tackle backpropagation, which is the core algorithm behind how a neural network learns. Now what is backpropagation? It is the actual algorithm which makes all the learning possible in a neural network. Basically, it's an algorithm for computing the complicated gradient. The magnitude of each component here is telling us how sensitive the cost function is to the weights and bias. Now let's say you compute a negative gradient and the component associated with the weight on this edge here comes out to be 4.5, while the component associated with the other edge comes out to be 0.1. The way you will interpret that is the cost of the function is 45 times more sensitive to changes in that of the first weight. So if you do a change in the first connection, that would have an effect on the cost, which is 45 times the change you made on the second connection. The cost involves arranging a certain cost, for example, over all the tens and thousands of training examples. For now, we're going to focus our attention on one single example. So let's take an example of the digit 5. What effects should this one training example have on how the weights and biases gets adjusted? Let's say we are at a point where the network is not well trained, so the activations in the output are going to be pretty random. Now, we can't directly change those activations. We only have the influence on the weights and biases. But it is helpful to keep a track of which adjustment we wish should take place to that output layer, and since we wanted to classify the image as a 5, we want the 6th value to get nudged up while all the others to get nudged down. Moreover, the size of these nudges should be proportional to how far each current value is from its target value. For example, the increase to that number 5 neuron activation is, in a sense, more important than the decrease to the number 7 neuron, which is already pretty close to the 0 mark. So there are 3 different parameters that can team up together to help increase the activation. You can increase the bias, you can increase the weights, and you can change the activation from the previous layer. Now, of course, we cannot influence those activations. We only have the control over the weights and biases. But just as with the last layer, it is helpful to keep a note of what those desired changes are. Now these changes are being made only for the digit 5. We also want all the other neurons in the last layer to become less active, and each of those other output neurons has its own thoughts about what should happen to the second last layer. So the desire of this digit 5 neuron is added together with the desires of all the other output neurons for what should happen to the second to last layer. Again, in proportion to the corresponding weights and in proportion to how much each of those neurons needs to change. This right here is where the idea of propagating backwards comes in. Now, once you have the idea of all the nudges you want to make to the second to last layer, you can recursively apply the same process to the relevant weights and biases that determine those values, repeating the same process through and moving backwards the network. Now remember that this is all just how a single training example wishes to change each of those weights and biases. This network can only classify a 5 as it is changing its value to classify 5 better. So what you do now is go through the same backpropagation routine for every other training example, recording how each one of them would change the weights and biases, and you average together those weights and the desired changes. Now this collection here of the average changes to each weight and biases is proportional to the negative gradient of the cost function. It takes the computer an extremely long time to add up the influence of every single training example, every single gradient descent step. So guys, I hope you got an idea of what exactly a gradient descent is, how it works, the various parameters involved in the working of the gradient descent, and how backpropagation handles all the changes to be made to the weights and biases, which ultimately tells us how the neural network is learning and modifying itself to have a better accuracy.
Today we'll be focusing on recurrent neural networks. So without any further ado, let us move forward and have a look at the agenda for today. So we'll begin by understanding why can't we use feedforward networks for various problems. We'll focus on various issues with feedforward networks. After that, we'll understand how recurrent neural networks solve those issues, and we'll understand how exactly it works. Then we'll focus on various issues with recurrent neural networks, namely vanishing and exploding gradient. After that, we'll understand how LSTMs, that is long short-term memory units, solves this problem. And finally, we'll be looking at an LSTM use case. So guys, let's begin. We'll understand why can't we use feedforward networks. Now let us take an example of a feedforward network that is used for image classification. So we have trained this particular network for classifying various images of animals.
Now if we feed in an image of a dog, it will identify that image and will provide a relevant label to that particular image. Similarly, if we feed in an image of an elephant, it will provide a relevant label to that particular image as well. Now if you notice, the new output that we have got, that is classifying an elephant, has no relation with the previous output, that is of a dog. Or you can say that the output at time t is independent of output at time t minus 1. As we can see that there is no relation between the new output and the previous output. So we can say that in feedforward networks, outputs are independent to each other. Now there are a few scenarios where we actually need the previous output to get the new output. Let us discuss one such scenario. Now what happens when you read a book? You'll understand that book only on the understanding of your previous words. Alright, so if I use a feedforward network and try to predict the next word in a sentence, I can't do that. Why can't I do that? Because my output will actually depend on the previous outputs. But in the feedforward network, my new output is independent of the previous outputs. That is, output at t plus 1 has no relation with output at t minus 2, t minus 1 and at t. So basically, we cannot use feedforward networks for predicting the next word in a sentence. Similarly, you can think of many other examples where we need the previous output, some information from the previous output, so as to infer the new output. This is just one small example. There are many other examples that you can think of. So we'll move forward and understand how we can solve this particular problem. So over here, what we have done, we have input at t minus 1. We'll feed it to our network. Then we'll get the output at t minus 1. Then at the next timestamp, that is at time t, we have input at time t that will be given to our network along with the information from the previous timestamp, that is t minus 1, and that will help us to get the output at t. Similarly, at output for t plus 1, we have two inputs. One is a new input that we give. Another is the information coming from the previous timestamp, that is t, in order to get the output at time t plus 1. Similarly, it can go on. So over here, I have just written a generalized way to represent it. There's a loop where the information from the previous timestamp is flowing. And this is how we can solve this particular challenge. Now let us understand what exactly are recurrent neural networks. So for understanding recurrent neural network, I'll take an analogy. Suppose your gym trainer has made a schedule for you. The exercises are repeated after every third day. Now this is the order of your exercises. First day you'll be doing shoulder, second day you'll be doing biceps, third day you'll be doing cardio. And all these exercises are repeated in a proper order. Now what happens when we use a feedforward network for predicting the exercise today? So we'll provide in the inputs such as day of the week, month of the year and health status. Alright, and we need to train our model or our network on the exercises that we have done in the past. After that, there'll be a complex voting procedure involved that will predict the exercise for us. And that procedure won't be that accurate. So whatever output we'll get won't be as accurate as we want it to be. Now what if I change my inputs and I make my inputs as what exercise I've done yesterday? So if I've done shoulder, then definitely today I'll be doing biceps. Similarly, if I've done biceps yesterday, today I'll be doing cardio. Similarly, if I've done cardio yesterday, today I'll be doing shoulder. Now there can be one scenario where you are unable to go to gym for one day. Due to some personal reasons, you could not go to the gym. Now what will happen at that time? We'll go one timestamp back and we'll feed in what exercise that happened day before yesterday. So if the exercise that happened day before yesterday was shoulder, then yesterday there were biceps exercises. Alright, similarly biceps happened day before yesterday, then yesterday would have been cardio exercises. Similarly, if cardio would have happened day before yesterday, yesterday would have been shoulder exercises. Alright, and this prediction, the prediction for the exercise that happened yesterday will be fed back to our network, and these predictions will be used as inputs in order to predict what exercise will happen today. Similarly, if you have missed your gym say for 2 days, 3 days or 1 week, so you need to roll back. You need to go to the last day when you went to the gym. You need to figure out what exercise you did on that day, feed that as an input, and then only you'll be getting the relevant output as to what exercise will happen today. Now what I'll do, I'll convert these things into a vector. Now what is a vector? Vector is nothing but a list of numbers. Alright, so this is the new information guys along with the information from the prediction at the previous timestamp. So we need both of these in order to get the prediction at time t. Imagine if I have done shoulder exercises yesterday. So this will be 1, this will be 0, and this will be 0. Now the prediction that will happen will be biceps exercise because if I have done shoulder yesterday, today it will be biceps. So my output will be 0, 1 and 0. And this is how vectors work guys. So I hope you have understood this guys. Now this is how a neural network looks like guys. We have new information along with the information from the previous timestamp. The output that we have got in the previous timestamp will use certain information from that, will feed into our network as inputs, and then that will help us to get the new output. Similarly, this new output that we have got will take some information from that, feed in as an input to our network along with the new information to get the new prediction, and this process keeps on repeating. Now, let me show you the math behind the recurrent neural networks. So this is the structure of a recurrent neural network, guys. Let me explain you what happens here. Now consider at time t equals to 0, we have input x naught and we need to figure out what is h naught. So according to this equation, h of 0 is equal to wi weight matrix multiplied by our input x of 0 plus wr into h of 0 minus 1, which is h of minus 1, and time can never be negative, so this particular equation cannot be applied here, plus a bias. So wi into x of 0 plus bh passes through a function g of h to get h of 0 over here. After that, I want to calculate y naught. So for y naught, I'll multiply h of 0 with the weight matrix wi and I'll add a bias to it and pass it through a function g of y to get y naught. Now in the next timestamp, that is at time t equals to 1, things become a bit tricky. Now let me explain you what happens here. So at time t equals to 1, I have input x1. I need to figure out what is h1. So for that, I'll use this equation. So I'll multiply wi, that is a weight matrix, by the input x1 plus wr into h of 1 minus 1, which is 0. H of 0, we know what we got from here. So wr into h of 0 plus the bias, pass it through a function g of h to get the output as h1. Now this h1 we'll use to get y1. We'll multiply h1 with wi plus a bias and we'll pass it through a function g of y to get y1. Similarly, in the next timestamp, that is at time t equals to 2, we have input x2. We need to figure out what will be h2. So we'll multiply the weight matrix wi with x of 2 plus wr into h of 1 that we have got here plus b of h and pass it through a function g of h to get h of 2. From h of 2, we'll calculate y of 2, wi into h of 2 plus by, that is the bias, pass it through a function g of y to get y2. And this is how recurrent neural network works, guys. Now you must be thinking how to train a recurrent neural network. So a recurrent neural network uses backpropagation algorithm for training. But backpropagation happens for every timestamp. That is why it is commonly called as backpropagation through time. And I've discussed backpropagation in detail in artificial neural network tutorial, so you can go through that. Over here, I won't be discussing backpropagation in detail. I'll just give you a brief introduction of what it is. Now with backpropagation, there are certain issues, namely vanishing and exploding gradients. Let us see those one by one. So in vanishing gradient, what happens? When you use backpropagation, you tend to calculate the error, which is nothing but the actual output that you already know minus the model output, the output that you got through your model, and the square of that. So you figure out the error. With that error, what do? You tend to find out the change in error with respect to change in weight or any variable. So we'll call it weight here. So change of error with respect to weight multiplied by learning rate will give you the change in weight. Then you need to add that change in weight to the old weight to get the new weight. All right. So obviously what we are trying to do, we are trying to reduce the error. So for that, we need to figure out what will be the change in error if my variables are changed, right? So that way we can get the change in the variable and add it to our old variable to get the new variable. Now over here, what can happen if the value dE by dW, that is a gradient, or you can say the rate of change of error with respect to our variable weight, becomes very small than 1, like it is 0.00 something. So if you multiply that with the learning rate, which is definitely smaller than 1, then you get the change of weight, which is negligible. All right. So there might be certain examples where you are trying to predict, say, a next word in a sentence, and that sentence is pretty long. For example, if I say I went to France dash dash dash, I went to France, then there are certain words, then I say few of them speak dash. Now I need to predict speak, what will come after speak. So for that, I need to go back in time and check what was the context, which will be very complex. And due to that, there will be a lot of iterations. And because of that, this error, this change in weight will become very small, very small. So the new weight that we'll get will be actually almost equal to your old weight. So there won't be any updation of weight that will be happening. And that is nothing but your vanishing gradient. All right, I'll repeat it once more. So what happens in backpropagation, you first calculate the error. This error is nothing but the difference between the actual output and the model output and the square of that. With that error, we figure out what will be the change in error when we change a particular variable, say weight. So dE by dW multiplied with learning rate to get the change in the variable or change in the weight. Now we'll add that change in the weight to our old weight to get the new weight. This is what backpropagation is, guys. All right, I'm just giving you a small introduction to backpropagation.
Now consider a scenario where you need to predict the next word in a sentence. And your sentence is something like this. I have been to France. Then there are a lot of words. After that, few people speak. And then you need to predict what comes after speak. Now if I need to do that, I need to go back and understand the context. What is it talking about? And that is nothing but your long-term dependencies. So what happens during long-term dependencies, if this dE by dW becomes very small, then when you multiply it with n, which is again smaller than 1, you get delta W, which will be very, very small. That will be negligible. So the new weight that you'll get here will be almost equal to your old weight. So I hope you're getting my point. So this new weight, so there will be no updation of weights, guys. This new weight will definitely will always be almost equal to our old weight. So there won't be any learning here. So that is nothing but your vanishing gradient problem. Similarly, when I talk about exploding gradient, it is just the opposite of vanishing gradient. So what happens when your gradient or dE by dW becomes very large, becomes greater than 1, all right? And you have some long-term dependencies. So at that time, your d by dw will keep on increasing, delta w will become large, and because of that, your weights, the new weight that will come, will be very different from your old weight. So these two are the problems with backpropagation. Now let us see how to solve these problems. Now exploding gradients can be solved with the help of truncated BTD, backpropagation through time. So instead of starting backpropagation at the last timestamp, we can choose a smaller timestamp like 10. Or we can clip the gradients at a threshold. So there can be a threshold value where we can, clip the gradients. And we can adjust the learning rate as well. Now for vanishing gradient, we can use a ReLU activation function. We have discussed ReLU activation function in Artificial Neural Network tutorial, guys. Similarly, we can also use LSTM and GRUs. In this tutorial, we'll be discussing LSTMs, that are long short-term memory units. Now let us understand what exactly are LSTMs. So guys, we saw what are the two limitations with the recurrent neural networks. Now we'll understand how we can solve that with the help of LSTMs. Now what are LSTMs? Long short-term memory networks, usually called as LSTMs, are nothing but a special kind of recurrent neural network. And these recurrent neural networks are capable of learning long-term dependencies. Now what are long-term dependencies? I've discussed that in the previous slide, but I'll just explain it to you here as well. Now, what happens sometimes we only need to look at the recent information to perform the present task. Now, let me give you an example. Consider a language model trying to predict the next word based on the previous ones. If we are trying to predict the last word in the sentence, say, the clouds are in the sky. So we don't need any further context. It's pretty obvious that the next word is going to be sky. Now, in such cases where the gap between the relevant information and the place that it's needed is small, RNNs can learn to use the past information. And at that time, there won't be such problems like vanishing and exploding gradient. But there are few cases where we need more context. Consider trying to predict the last word in the text, I grew up in France. Then there are some words. After that comes, I speak fluent French. Now, recent information suggests that the next word is probably the name of a language. But if we want to narrow down which language, we need the context of France from further back. And it's entirely possible for the gap between the relevant information and the point where it is needed to become very large. And this is nothing but long-term dependencies. And the LSTMs are capable of handling such long-term dependencies. Now, LSTMs also have a chain-like structure like recurrent neural networks. Now, all the recurrent neural networks have the form of a chain of repeating modules of neural networks. Now, in standard RNNs, the repeating module will have a very simple structure such as a single tanh layer that you can see. Now, this tanh layer is nothing but a squashing function. Now, what I mean by squashing function is to convert my values between -1 and 1. All right, that's why we use tanh. And this is an example of an RNN. Now we'll understand what exactly are LSTMs. Now this is a structure of an LSTM. Or if you notice, LSTM also have a chain-like structure, but the repeating module has different structures. Instead of having a single neural network layer, there are 4 interacting in a very special way. Now the key to LSTM is the cell state. Now this particular line that I'm highlighting, this is what is called the cell state. The horizontal line running through the top of the diagram. So this is nothing but your cell state. Now you can consider the cell state as a kind of a conveyor belt. It runs straight down the entire chain with only some minor linear interactions. Now what I'll do, I'll give you a walkthrough of LSTM step by step, alright? So we'll start with the first step. Alright guys, so the first step in our LSTM is to decide what information we are going to throw away from the cell state. And you know what is the cell state, right? I've discussed in the previous slide. Now this decision is made by the sigmoid layer.
So the layer that I'm highlighting with my cursor, it is a sigmoid layer called the forget gate layer. It looks at ht minus 1, that is the information from the previous timestamp, and xt, which is the new input, and outputs a number between 0 and 1 for each number in the cell state ct minus 1, which is coming from the previous timestamp. 1 represents completely keep this, while a 0 represents completely get rid of this. Now if we go back to our example of a language model trying to predict the next word based on all the previous ones, in such a problem, the cell state might include the gender of the present subject so that the correct pronouns can be used. When we see a new subject, we want to forget the gender of the old subject, right? We want to use the gender of the new subject. So we'll forget the gender of the previous subject here. This is just an example to explain you what is happening here. Now let me explain you the equations which I've written here. So ft will be combining with the cell state later on, that I'll tell you. So currently ft will be nothing but the weight matrix multiplied by ht minus 1 and xt and plus the bias, and this equation is passed through a sigmoid layer. All right, and we get an output that is 0 and 1. 0 means completely get rid of this, and 1 means completely keep this. All right, so this is what basically is happening in the first step. Now let us see what happens in the next step. So the next step is to decide what information we are going to store. In the previous step, we decided what information we are going to keep, but here we are going to decide what information we are going to store here. All right, what new information we are going to store in the cell state. Now this has two parts. First, a sigmoid layer, this is called a sigmoid layer, and which is also known as an input gate layer, decide which values we'll update. All right, so what values we need to update. Then there's also a tan layer that creates a vector of the candidate values c bar of t minus 1 that will be added to the state later on. All right, so let me explain it to you in a simpler terms. So whatever input that we are getting from the previous timestamp and the new input, it will be passed through a sigmoid function which will give us I of t. All right, and this I of t will be multiplied by ct, which is nothing but the input coming from the previous timestamp and the new input with that is passed through a tan that will result in ct. And this will be later added on to our cell state. And the next step will combine these two to update the states. Now let me explain the equations. So I of t will be what? Weight matrix, and then we have ht minus 1 comma xt multiplied by the weight matrix plus the bias, pass it through a sigmoid function, we get I of t. C bar of t will get by passing a weight matrix ht minus 1 xt plus bias through a tan squashing function, and we'll get C bar of t. All right, so as I've told you earlier as well, in the next step we'll combine these two to update the state. Let us see how we do that. So now is the time to update the old cell state ct minus 1 with the new cell state ct. All right, and the previous steps we have already decided what to do. We just need to actually do it. So what we'll do, we'll multiply the old cell state ct minus 1 with ft that we got in the first step, forgetting the things that we decided to forget earlier in the first step, if you can recall. Then what we do, we add it to it and ct, then we add it by the term that will come after multiplication of it and c bar t, and this new candidate value scaled by how much we decided to update each state value. All right, so in the case of the language model that we were discussing, this is where we would actually drop the information about the old subject gender and add the new information as we decided in the previous steps. So I hope you are able to follow me, guys. All right, so let us move forward and we'll see what is the next step. Now our last step is to decide what we are going to output, and this output will depend on a cell state, but it will be a filtered version. Now finally what we need to do is we need to decide what we are going to output, and this output will be based on our cell state. First we need to pass ht minus 1 and xt through a sigmoid activation function so that we get an output that is OT. Alright, and this OT will be in turn multiplied by the cell state after passing it through a tan squashing function or an activation function. And why we do that? Just to push the values between -1 and 1. So after multiplying OT, that is this value, and a tan CT, we'll get the output H2, which will be our new output, and that will only output the part that we decided to. Whatever we have decided in the previous steps, it will only output that value. All right. Now I'll take the example of that language model again. Since it just saw a subject, it might want to output information relevant to a verb, and in case that's what is coming next. For example, it might output whether the subject is singular or plural, so that we know what form of a verb should be conjugated into. All right, and you can see from the the equations as well. Again, we have a sigmoid function. Then that whatever output we get from there, we multiply it with tan ct to get the new output. All right, guys. So this is basically LSTMs in a nutshell. So in the first step, we decided what we need to forget. In the next step, we decided what are we going to add to our cell state, what new information we are going to add to our cell state, and we were taking an example of the gender throughout this whole process. All right. And in the third step, what we do, we actually combined it to get the new cell state. Now in the fourth step, what we did, we finally got the output that we want. And how we did that? Just by passing ht minus 1 and xt through a sigmoid function, multiplying it with the tan h ct, the tan h new cell state, and we get the new output. Fine, guys. So this is what basically LSTM is, guys. Now we'll look at a use case where we'll be using LSTM to predict the next word in a sentence. All right, let me show you how we are going to do that. So this is what we are trying to do in our use case, guys. We'll feed our LSTM with correct sequences from the text of 3 symbols. For example, had a general and a label, that is council in this particular example. Eventually, our network will learn to predict the next symbol correctly. So obviously, we need to train it on something. Let us see what we are going to train it on. So we'll be training our LSTM to predict the next word using a sample short story that you can see over here. All right, so it has basically 112 unique symbols. So even comma and full stop are considered as symbols. All right, so this is what we are going to train it on. So technically, we know that LSTMs can only understand real numbers. All right, so what we need to do is we need to convert these unique symbols into a unique integer value based on the frequency of occurrence, and like that we'll create a dictionary. For example, we have had here that will have value 20, A will have value 6, general will have value 33. All right, and then what happens, our LSTM will create a 112 element vector that will contain the probability of each of these words or each of these unique integer values. All right, so since 0.6 has the highest probability in this particular vector, it will pick the index value of 0.6, then it will see what symbol is attached to that particular integer value. So 37 is attached to council. So this will be our prediction, which is absolutely correct, as a label is also council according to our training data. All right, so this is what we are going to do in our use case. So guys, this is what we'll be doing in our today's use case. Now I'll quickly open my PyCharm and I'll show you how you can implement it using Python. We'll be using TensorFlow, which is a popular Python library for implementing deep neural networks or neural networks in general. All right, so I'll quickly open my PyCharm now. So guys, this is my PyCharm, and over here I've already written the code in order to execute the use case that we have. So first we need to do is import the libraries. NumPy for arrays, TensorFlow, we know TensorFlow.contrib. From that we need to import RNN, then random collections and time. All right, so this particular block of code is used to evaluate the time taken for the training. After that we have log underscore path, and this log underscore path is basically telling us the path where the graph will be stored. All right, so there will be a graph that will be created, and then that graph will be launched. Then only our RNN model will be executed. Then that's how TensorFlow works, guys. So that graph will be created in this particular path. All right, and we are using summary writer, so that will actually create the log file that will be used in order to display the graph using TensorBoard. All right, so then we have defined training underscore file, which will have our story on which we'll train our model on. Then what we need to do is read this file. So how are we going to do that? First is read line by line whatever content that we have in our file. Then we are going to strip it. That means we are going to remove the first and the last white space. Then again we are splitting it just to remove all the white spaces that are there. After that we're creating an array, and then we are reshaping it. Now during the reshape, if you notice, this -1 value tells us the compatibility. All right, so when you're reshaping it, you need to make sure that we are providing in the correct parameters to reshape it. So you can convert a 3x2 matrix to a 2x3 matrix, right? So just to make sure that it is compatible enough, we add this -1 and it will be done automatically. All right, then return content. After that, what we are doing, we are feeding in the training data that we have, training underscore file. We are feeding in our story and calling the function read underscore data. Then what we are doing, we are creating a dictionary. What is a dictionary? We all know key value pairs based on the frequency of occurrences of each symbol. All right, so from here collections.counter words.most common. So most common words with their frequency of occurrence, there will be a dictionary created. And after that, we'll call this dict function, and this dict function will feed in word, and which is equal to length of dictionary. That means whatever the length of that particular dictionary is, how many times it is repeated. So we'll have the frequency as well as a symbol. That will be our key value pair, and we are reversing it as well. Then what we are doing, we are calling it build underscore data set, and we're feeding in our training data there. This is our vocabulary size, which is nothing but the length of your dictionary. And then we have defined various parameters such as learning rate, iterations or epochs. Then we have display step and underscore input. Now learning rate, we all know what it is. the steps in which our variables are updated. Training underscore iterations is nothing but your epochs, the total number of iterations. So we have given 50,000 iterations here. Then we have display underscore step, that is 1,000, which is basically your batch size. So batch size is what? After every 1,000 epochs, you'll see the output. All right. So it'll be processing it in batches of 1,000 iterations. Then we have n underscore input as 3. Now the number of units in the RNN cell will keep it as 512. Then we need to define X and Y. So X will be our placeholder that will have the input values, and Y will have all the labels, all right, vocab size. So X is a placeholder where we'll be feeding in our input dictionary. Similarly, Y is also one more placeholder, and it'll have a shape of none, comma, vocab size. Vocab size we have defined earlier, as you can see, which is nothing but the length of your dictionary. Then we are defining weights as well as biases. After that, we have defined our model. All right, so this is how we are going to define it. We'll create a function RNN when we'll have X weights and biases. And after that, we are calling in RNN.multi-RNN cell function. And this is basically to create a 2-layer LSTM, and each layer has n underscore hidden units. After that, what we are doing, we are generating the predictions. But once we have generated the prediction, there are n underscore input outputs, but we only want the last output. All right, so for that, we have written this particular line. And then finally, we are making a prediction. We are calling this RNN function, feeding in X weights and biases. After that, we are calculating the loss and then we are optimizing it. For calculating the loss, we are using reduce underscore mean, softmax cross entropy. And this will give us basically the probability of each symbol, and then we are optimizing it using RMS prop optimizer. All right, and this gives actually a better accuracy than Adam optimizer, and that's the reason why we are using it. Then we are going to calculate the accuracy, and after that we are going to initialize the variables that we have used. As we have seen in TensorFlow that we need to initialize all the variables, unlike constants and placeholders in TensorFlow. All right, and once we are done with that, we are feeding in our values, then calculating the accuracy, how accurate it is, and then when optimization is done, we are calculating the elapsed time as well. So that will give us how much time it took in order to train our model. Then this is just to run the tensor board on local host 6006. And this particular block of code is used in order to handle the exceptions. So exceptions can be like whatever word that we are putting in might not be there in our dictionary or might not be there in our training data. So those exceptions will be handled here, and if it is not there in our dictionary, then it will print word not in a dictionary. All right, so fine guys, let's input some values and we'll have some fun with this model. All right, so the first thing that I'm gonna feed in is had a general. So whenever I feed in these three values, had a general, there'll be a story that will be generated by feeding back the predicted output as the next symbol in the inputs. All right, so when I feed in had a general, so it will predict the correct output as council, and this council will be fed back as a part of the new input, and our new input will be a general council. So it will be a general council. All right, so these three words will become our new input to predict the new output, which is 2. All right, and so on. So surprisingly, LSTM actually creates a story that somehow makes sense. So let's just read it. Had a general council to consider what measures they could take to outwit their common enemy, the cat. By this means, we should always know when she was about and could easily. All right, so somehow it actually makes sense when you feed in that. So what will happen when you feed in these three inputs? It will predict the next word, that is council. After that, it will take council and it will feed back as an input along with a general. So a general council will be your next input to predict 2. Similarly, in the next iteration, it will take general council 2 and predict consider for us. And this will keep on repeating.
Today we'll be discussing about convolutional neural networks. So without any further ado, let us move forward and have a look at the agenda for today. So we'll begin by understanding how a computer reads an image. Then we'll see why can't we use fully connected networks for image recognition. After that, we'll understand what exactly is convolutional neural network and how it works. And finally, we'll be looking at a use case. So let's begin, guys. We'll understand how exactly a computer reads an image. So this is an image of New York skyline. I personally love this picture. So when a human will see this image, he'll first notice there are a lot of buildings in different colors and stuff like that. But how a computer will read this image? So basically there will be 3 channels. One will be red, another will be green, and finally we have blue channel, which is popularly known as RGB. So each of these channels will have their own respective pixel values, as you can see it over here. So when I say that image size is B cross A cross 3, it means that there are B rows, A columns and 3 channels. All right. So if somebody tells you that the size of an image is 28 cross 28 cross 3 pixels, it means that it has 28 rows, 28 columns, and 3 channels. So this is how a computer sees an image. And this is for colored images. For black and white images, we have only 2 channels. So let's move forward and we'll see why can't we use fully connected networks for image classification. So consider an image which has 28 cross 28 cross 3 pixels. So when I feed in this image to a fully connected network like this, then the total number of weights required in the first hidden layer will be 2352. You can just go ahead and multiply it yourself. All right. But in real life, the images are not that small. All right. So whatever images that we have, they are definitely above 200 cross 200 cross 3 pixels. So if I take an image which has 200 cross 200 cross 3 pixels and I feed it to a fully connected network, so at that time, the number of weights required at the first hidden layer itself will be 120,000 guys. So we need to deal with such huge amount of parameters, and obviously we require more number of neurons. So that can eventually lead to overfitting. So that's why we cannot use fully connected network for image classification. Now let's see why we need convolutional neural networks. So basically, in convolutional neural network, a neuron in the layer will only be connected to a small region of the layer before it. So if you consider this particular neuron which I'm highlighting right now is only connected to 3 other neurons. Unlike the fully connected network where this particular neuron will be connected to all these 5 neurons. Because of this, we need to handle less amount of weights, and in turn, we need less number of neurons as well. So let us understand what exactly is convolutional neural network. So convolutional neural networks are special type of feed-forward artificial neural networks, which is inspired from visual cortex. So visual cortex is nothing but a small region in our brain which is present somewhere here where you can see the bulb. And basically what happened, there was an experiment conducted and people got to know that visual cortex is small regions of cells that are sensitive to specific regions of visual field. So what I mean by that is, for example, some neurons in the visual cortex fires when exposed to vertical edges. Some will fire when exposed to horizontal edges. Some will fire when exposed to diagonal edges. And that is nothing but the motivation behind convolutional neural network. So now let us understand how exactly a convolutional neural network works. So generally a convolutional neural network has 3 layers: convolution layer, ReLU layer, pooling layer, and fully connected layer. We'll understand each of these layers one by one. We'll take an example of a classifier that can classify an image of an X as well as an O. So with this example, we'll be understanding all these 4 layers. So let's begin, guys. Now there are certain trickier cases. So what I mean by that is X can be represented in these 4 forms as well, right? So these are nothing but the deformed images of X. Similarly for O as well. So these are deformed images. So even I want to classify these images either X or O. All right, because even this is X, this is X, this is X, this is X. But all these are deformed images, but they are in turn X, right? So I want my classifier to classify them as X. So basically that's what I want. So if you can notice here, this is a proper image of an X, and which is actually equal to this particular X, which is a deformed image. Same goes for this O as well. So now what we are going to do is, we know that a computer understands an image using numbers at each pixel. So what we'll do, whatever the white pixels that we have, we are going to assign a value -1 to it, and whatever black pixels we have, we are going to assign a value 1 to it. When we use normal techniques to compare these two images, one is a proper image of X and another is a deformed image of X, we got to know that a computer is not able to classify the deformed image of X correctly. Why? Because it is comparing it with the proper image of X, right? So when you go ahead and add the pixel values of both of these images, you get something like this. So basically our computer is not able to recognize whether it is an X or not. Now what we do with the help of CNN, we take small patches of our image. So these patches or these pieces are known as nothing but features or filters. So what we do, by finding rough feature matches in roughly the same positions in two images, CNN gets a lot better at seeing the similarity between the whole image matching schemes. What I mean by that is, we have these filters, right? We have these filters that you can see. So consider this first filter. This is exactly equal to the feature or the part of the image in the deformed image as well. So this is our proper image and this is our deformed image, all right? So this particular feature or this particular part of the image is actually equal to this particular part of the image. Same goes for this particular feature or filter as well. And similarly, we have this filter as well, which is actually equal to this particular part of the deformed image, all right? So let's move forward and we'll see what all features that we'll be taking in our example. So we'll be considering these 3 features or filters. This is a diagonal filter, this is again a diagonal filter, and this is nothing but a small X. So we'll take these 3 filters and we'll move forward. So what we are going to do is we are going to compare these features, the small pieces of the bigger image. We are going to put it on the input image, and if it matches, then the image will be classified correctly. Now we'll begin, guys. The first layer is convolution layer. So these are the beginning 2 steps of this particular layer. First, we need to line up the feature in the image and then multiply image by the corresponding feature pixel. Now let me explain you with an example. So this is our first diagonal feature that we'll take. we are going to put this particular feature on our image of X, all right, and we are going to multiply the corresponding pixel value. So 1 will be multiplied with 1, we'll get 1 and we'll put it in another matrix. Similarly, we are going to move forward and we're going to multiply -1 with -1. We're going to multiply -1 with -1, as you can see. Similarly, we multiply this as well, -1 into -1, then again -1 into -1. So we are going to complete this whole process when we are going to finish up this matrix. All right, and once we are done finishing up the multiplication of all the corresponding pixels in the feature as well as in the image, we need to follow two more steps. We need to add them up and divide by the total number of the pixels in the feature. So what I mean by that is, after the multiplication of the corresponding pixel values, what we do, we add all these values, we divide it by the total number of pixels, and we get some value, right? And then now our next step is to create a map and put the value of the filter at that particular place. We saw that after multiplying the pixel value of a feature with the corresponding pixel value with that of our image, we get the output, which is 1. So we place 1 here. Similarly, we are going to move this filter throughout the image. Next up, we are going to move this filter here. After that, we are going to move it here, 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 everywhere on the image. We are going to move it and we are going to follow the same process. All right, so yeah, this is one more example where I've moved my filter in between, and after doing that, I've got the output something like this, 1, 1, -1 and all. So over here, if you notice, I've got a couple of times -1 as well, due to which my output that comes is 0.55, right? So I'm going to place 0.55 here. Similarly, after moving the pixel, after moving the filter throughout the image, I got this particular matrix. All right, and this is for one particular feature. After performing the same process for the other two filters as well, I've got these two values. So we have these three values after passing through the convolution layer. Let me give you a quick recap of what happens in convolution layer. So basically we have taken three features, all right, and one by one we'll take one feature, move it through the entire image, and when we are moving it, at that time we are multiplying the pixel value of the image with that of the corresponding pixel value of the filter, adding them up, dividing by the total number of pixels to get the output. So when we do that for all the filters, we got these three outputs, all right? So let's move forward and we'll see what happens in ReLU layer. So this is ReLU layer, guys, and people who have gone through the previous tutorial actually know what it is. So let me just give you a quick introduction of ReLU layer. So ReLU is nothing but an activation function, all right? So what I mean by that is, it will only activate a node if the input is above a certain quantity. While the input is below 0, the output is also 0, all right? And when the input rises above the certain threshold, it has a linear relationship with the dependent variable. Now I'll explain you with an example. We have a graph of ReLU function here. So my function says that when f of x is equal to 0 if x is less than 0, and it is equal to x when x is greater than 0, all right? So whatever values that I have which are below 0 will actually in turn become 0, and whatever values that are above 0, our function value will also be equal to that particular value. So f of x will be equal to x if it is greater than or equal to 0, and it will be 0 if it is less than 0. So if I have x value as -3, so definitely it is less than 0, so f of x becomes 0. Similarly, if I have -5x value, then again it is less than 0, so my f of x value becomes 0. But when I consider 3 as my x value, then my f of x becomes equal to x, which is nothing but 3. So over here I'll have 3. Again, if I take my x value as 5, then obviously it is greater than or equal to 0. Then my f of x becomes equal to x, so my f of x value becomes 5. So this is how a ReLU function works. So why are we using ReLU function here is we want to remove all the negative values from our output that we got through the convolution layer. So we'll only take the first output that we got by moving one feature throughout the image. So this is the output that we have got for only one filter. All right, so over here I'm going to remove all negative values. So over here you can see that it was -0.11 before, and I've converted that to 0. Similarly, I'm going to repeat the whole process for the entire matrix, and once I'm done with that, I get this particular value. Now remember, this is only for the output that we got through one feature. All right, so when we were doing convolution at that time, we were using three features, right? So this is the output only for one filter. After doing it for the output of the other two filters as well, we have got these two values more. So totally we have these three values after passing through ReLU activation function. Next up, we'll see what exactly is pooling layer. So in pooling layer, what we do, we take a window size of 2 and we move it across the entire matrix that we have got after passing through ReLU layer. And we take only the maximum value from there so that we can shrink the image. So what we are actually doing is we are reducing the size of our image. So let me explain you with an example. So this is basically one output that we have got after passing through ReLU layer. And over here we have taken a window size of 2 cross 2. So when we keep this window at this particular position, we see that 1 is the highest value. So we are going to keep 1 here. And we are going to repeat the same process for this particular window as well. So over here the maximum value is 0.33, so 0.33 will come. So if you notice here, earlier we had 7 cross 7 matrix, and now we have reduced that to 4 cross 4 matrix. So after doing that for the entire image, we have got this as our output. This output we have got after moving our window throughout the image that we have got after passing through ReLU layer, right? And when we repeat this process for all the 3 outputs that we have got after the ReLU layer, then we get this particular output after pooling layer, right? So basically we have shrinked our image to a 4 cross 4 matrix. Now comes the tricky part. So where we are going to do now is stack up all these layers. So we have discussed convolution layer, ReLU layer, and pooling layer. So I'll just give you a brief recap of what all things we have discussed. In convolution layer, what we did, we took 3 features, and then after that, one by one, we moved each filter throughout the image. And when we were moving it, we were continuously multiplying the image pixel value with that of the corresponding filter pixel value, and then we were dividing it by the total number of pixels. All right. With that, we got 3 output after passing through the convolution layer. Then those 3 output we passed through a ReLU layer where we have removed the negative value. All right. And after removing negative value, again, we have got the 3 outputs. Then those 3 outputs we passed through pooling layer. So basically we're trying to shrink our image. And what we did, we took a window size of 2 cross 2, moved it through all the 3 outputs that we have got through ReLU layer. And after doing that, we were only taking the maximum value, pixel value in that particular window. And then we were putting it in a different matrix so that we get a shrinked image. And after passing it through pooling layer, we have got a 4 cross 4 matrix. And since we took 3 features in the beginning, so therefore we have got 3 outputs after passing through pooling layer. All right. Next up, we are going to stack up all the layers. All right. So let's do that. So after passing through convolution, ReLU, and pooling, we have got this 4 cross 4 matrix. This was our input image. Now when we add one more layer of convolution, ReLU, and pooling, we have shrinked our image from 4 cross 4 to 2 cross 2, as you can notice here. Now we are going to use fully connected layer. Now what happens in fully connected layer? The actual classification happens here, guys, okay? So what we are doing here is we are going to take the shrinked images and put it into a single list. So basically this is what we have got after passing through 2 layers of convolution, ReLU, and pooling. And this is what we have got. So basically we are converting into a single list or a vector. How we do that? We take the first value 1, then we take 0.55, then we take 0.55, then we take 1 again. Then we take 1, then we take 0.55, 0.55, 0.55. Then we again take 0.55, 1, 1, and 0.55. So this is nothing but a vector, or you can say a list. If you notice here that there are certain values in my list which is high for X, and similarly if I repeat the entire process that we have discussed for O, there will be certain different values which will be high. So for X we have first, fourth, 5th, 10th, and 11th element vector values are high. For O we have 2nd, 3rd, 9th, and 12th element vector which are high. So basically we know now if we have an input image which has 1st, 4th, 5th, 10th, and 11th element vector values high, we know that we can classify it as X. Similarly, if our input image has a list which has the 2nd, 3rd, 9th, and 12th element vector values high, then we can classify it as 0. Now let me explain you with an example. So after the training is done, after doing the entire process for both X and O, you know that our model is trained now. Okay, so we have given a new input image, and that input image passes through all the layers. And once it has passed through all the layers, we have got this 12 element vector. Now it has 0.9, 0.65, all these values, right? Now how do we classify it, whether it is an X or O? So what we do, we'll compare this with a list of X and O. Right, so we have got the list in the previous slide. If you notice, we have got 2 different lists for X and O. We are going to compare this new input image list that we have got with that of X and O. Right, so first let us compare that with X. Now, as I've told you earlier as well, for X, there are certain values which will be high, which is nothing but 1st, 4th, 5th, 10th, and 11th value, right? So I'm going to sum 1st, 4th, 5th, 10th, and 11th value, and I've got 5. 1 plus 1 plus 1 plus 1 and plus 1. So 5 times 1, I've got 5. And now I'm going to sum the corresponding values of my input image vector as well. So the first value is 0.9, then the 4th value is 0.87, 5th value is 0.96, 10th value is 0.89, and the 11th value is 0.94. So after doing the sum of these values, I've got 4.56. When I divide this by 5, I got 0.91, right? Now this is for X. Now when I do the same process for O, so in O, if you notice, I have 2nd, 3rd, 9th, and 12th element vector values as high. So when I sum these values, I get 4. And when I do the sum of the corresponding values in my input image, I've got 2.07. When I divide that by 4, I got 0.51. And so now we notice that 0.91 is a higher value compared to 0.51. So when we have compared our input image with the values of X, we got a higher value than the value that we have got after comparing the input image with the values of 4. So the input image is classified as X. Alright, so now let us move towards our use case. So this is our use case, guys. So over here what we are going to do is we are going to train our model on different types of dogs and cat images, and once the training is done we are going to provide it an input and it will classify whether the input is of a dog or a cat. Now let me tell you the steps involved in it. So what we are going to do in the beginning is obviously first we need to download the data set. After that we are going to write a function to encode the labels. Labels are nothing but the dependent variable that we are trying to predict. So in our training data and testing data, obviously we know the labels, right? So on that basis only we can train our model. So we are going to encode those labels. After that we'll resize the image to 50 cross 50 pixel and we are going to read it as a grayscale image. Then we are going to split the data 24,000 images for training and 50 for testing. Once this is done, we are going to reshape the data appropriately for TensorFlow. Now TensorFlow, I think everyone knows about TensorFlow. TensorFlow is nothing but a Python library for implementing deep learning models. Then we are going to build the model, calculate the loss. It is nothing but categorical cross entropy. Then we are going to reduce the loss by using RBM optimizer with a learning rate set to 0.001. Then we are going to train the deep neural network for 10 epochs, and finally we are going to make predictions. Alright, so I'll just quickly open my PyCharm and I'll show you the code, how it looks like. So this is the code that I've written in order to implement the use case. In the beginning, I need to import the libraries that I require. And once it is done, what I'm doing, I'm defining my training data and the testing data. So train and test one contains both my training data as well as testing data respectively. Then I've taken my image size as 50 and learning rate I've defined here. And I've given a name to my model. You can give whatever name you want. Alright, so first thing that we saw, we need to encode the dependent variable. That's what we are doing here. We are encoding our dependent variable. So whenever the label is cat, then it will be converted to an array of 1, 0, and when it is dog, it will be converted to an array of 0, 1. So why we are actually encoding the label? Because our code cannot understand the categorical variable. So we need to encode it, right? Next, what I'm doing is I'm resizing my image to 50 cross 50 and I am converting it to a grayscale image, right? And once this is done, I'm going to split my data set into training and testing parts. So yeah, we are basically splitting the data set into two parts for training and testing. And here we are defining a model. So you can I can just go ahead and throw in a comment here. Building the model. Yeah. So this is where we are building the model. So basically what we have done here is we have resized our image to 50 cross 50 cross 1 matrix, and that is the size of the input that we are using, right? This input that I'm talking about. Then what we have done, a convolution layer we have defined with 32 filters and a stride of 5 with an activation function, a ReLU. And after that we have added a pooling layer, max pool layer. Okay. Again, what we have done, we have repeated the same process, but over here we are taking 64 filters and 5 stride, passing it through a ReLU activation function, and after that we have a pooling layer, max pool layer. Then we have repeated the same process for 128 filters. After that we have repeated for 64 filters, then for 32 filters, and after that we are using a fully connected layer with 1024 neurons. And finally we are using the dropout layer with key probability of 0.8 to finish our model. So this is where our model is actually finished. And then what we are doing is we are using the RBM optimizer to optimize our model. So basically whatever the loss that we have, we are trying to reduce it. And this is basically for your tensor board. So we are creating some log files, and then with that log file, tensor board will create pretty fancy graphs for us that helps us to visualize the entire model. And then what we are doing is we are trying to fit the model. And we have defined epochs as 10. That is the number of iterations that will happen will be 10. And yeah, so this is pretty much it. Model name we have given. Then input is x underscore test to check the accuracy. Similarly, the target will be y underscore test. The labels associated with that test data will be y underscore test, and which we have encoded basically. So this is how we are going to actually calculate the accuracy, and we'll try to reduce the loss as much as possible in 10 epochs. So till now our model is complete. We are done with it. Next, what I'm doing is I'm feeding in some random input from the test data, and I'm validating whether my model is predicting it correct or not. All right. So I've already trained the model because it takes a lot of time, and yeah, I cannot do it here. So I've already trained the model, and you can see that the loss that came after the 10th epoch is 0.2973, and the accuracy is somewhere around 88%, which is pretty good, guys. And yeah, and I've done the prediction on the test data as well. So let me just show it to you that. So this is the prediction that it has done on few of the images in the test data. So yeah, it is a cat predicted as cat, cat predicted as cat, 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 and dogs as well. There are certain dogs as well.
Welcome to today's tutorial session based on the autoencoders. Now, in this session, you will have a deeper insight into the working of autoencoders that will help you build a strong fundamental knowledge about the topic. So let's move forward and look at the agenda of today's session. So we will begin with the fundamental query that why do we need autoencoders? Next, we will start with the introduction to what are autoencoders and the various components of these. Then we will move on to the various properties of autoencoders. Next, we will see how the training is done and discuss the architecture of autoencoders. Moving on, we will have a detailed discussion about the various types of autoencoders such as convolution autoencoders, sparse autoencoders, deep autoencoders, and contractive autoencoders. And we shall also see how do they work along with a short demo. Now finally, we will have a look at all the applications of autoencoders. So let's get started. Data compression is a big topic that's used in computer vision, computer networks, and many more. Now the point of data compression is to convert our input into a smaller representation that we recreate to a degree of quality. The smaller representation is what would be passed around, and when anyone needed the original, they would reconstruct it from the smaller representation. Now, autoencoders are unsupervised neural networks that use machine learning to do this compression for us. The aim of an autoencoder is to learn a compressed, distributed representation for the given data, typically for the purpose of dimensionality reduction. Now, for that, we already have principal component analysis. Then why do we need autoencoders? So an autoencoder can learn nonlinear transformations unlike PCA with a nonlinear activation function and multiple layers. Now it doesn't have to learn dense layers, so it can use convolutional layers to learn too, which could be better for video, image, and series data. Now it may be more efficient in terms of model parameters to learn several layers with an autoencoder rather than learn one huge transformation with PCA. An autoencoder also gives a representation as the output of each layer, and having multiple representations of different dimensions is always useful. So an autoencoder could let you make use of pre-trained layers from another model to apply transfer learning to prime the encoder or the decoder. Despite the fact that the practical applications of autoencoders were pretty rare some time back, today data denoising and dimensionality reduction for data visualization are considered as two main interesting practical applications of autoencoders. Now, with appropriate dimensionality and sparsity constraints, autoencoders can learn data projections that are more interesting than PCA or other basic techniques. It also provides a more accurate output when compared to PCA. Now, autoencoders are simple learning networks that aim to transform inputs into outputs with the minimum possible error. This means that we want the output to be as close to input as possible. An autoencoder neural network is basically an unsupervised machine learning algorithm that applies backpropagation, setting the target values to be equal to the inputs. So let's have a look at some of the key features about autoencoders. So it is an unsupervised machine learning algorithm that is similar to PCA, but minimizes the same objective function. An autoencoder is a neural network whose target output is its input. Autoencoders, although is quite similar to PCA, but they are more flexible when compared to the other. Autoencoders can represent both linear and nonlinear transformation in encoding, but PCA can only perform linear transformation. So now let's have a look at the components of autoencoders. So there are basically three main layers. The first one is the encoder, then code and decoder. The first component, that is the encoder, is the part of the network that compresses the input into a latent space representation. The encoder layer encodes the input image as a compressed representation in a reduced dimension. Now the compressed image typically looks garbled, nothing like the original image. The next component represents the latent space. Now, code is the part of the network that represents the compressed input fed to the decoder. The third component is the decoder. Now, this layer basically decodes the encoded image back to the original dimension. The decoded image is a lossy reconstruction of the original image. Now, it reconstructs the input from the latent space representation. So now let's talk about some of the properties of autoencoders. They are only able to compress data similar to what they have been trained on. An autoencoder which has been trained on human faces would not be performing well with images of modern buildings. This improvises the difference between the autoencoders and MP3 kind of compression algorithms, which only hold assumptions about sound in general, but not about specific types of sounds. Autoencoders are lossy, which means that the decompressed outputs will be degraded compared to the original inputs, just like what you see in JPEG or MP3. Now, if you have appropriate training data, it is easy to train specialized instances of the algorithm that will perform well on a specific type of input. Now, it doesn't require any new engineering. Additionally, in almost all contexts where the term autoencoder is used, the compression and decompression functions are implemented with neural networks. So now let's have a look at the training of an autoencoder. Now there are 4 hyperparameters that we need to set before training them. The first one is the code size. The code size represents the number of nodes in the middle layer. Smaller size results in more compression. The second parameter is the number of layers. Now the autoencoder can be as deep as we want it to be. We can have 2 or more layers in both the encoder and decoder without considering the input and the output. Next is the loss function. So we either use mean squared error or binary cross entropy. Now if the input values are in the range 0 to 1, then we typically use cross entropy, otherwise we use the mean squared error. Next is the number of nodes per layer. So the number of nodes per layer decreases with each subsequent layer of the encoder and increases back in the decoder. Also, the decoder is symmetric to the encoder in terms of layer structure, but this is not necessary and we have total control over these parameters. Now let's have a look at the architecture of an autoencoder and have a deeper insight about the hidden layers. So in an autoencoder, we add a couple of layers in between the input and the output, and the sizes of these layers are smaller than the input layer. Let's say the input vector has a dimensionality of n, which means that the output will also have a dimensionality of n. Now we make the input go through a layer of size p where the value of p is less than n, and we ask it to reconstruct the input. Now the autoencoder receives unlabeled input, which is then encoded to reconstruct the input. One important part of the autoencoders is the bottleneck. Now, the bottleneck approach is a beautifully elegant approach to a representation learning, specifically for deciding which aspects of observed data are relevant information and what aspects can be thrown away. It does this by balancing 2 criteria, that is the compactness of representation measured as the compressibility, number of bits needed to store the representation, and the second one, information the representation retains about some behaviorally relevant variables. Now it assumes we know what the behaviorally relevant variables are and how they are related to observed data, or at least we have to have data to learn or approximate the joint distribution between observed and relevant variables. Now let's have a detailed description about the encoder. The encoder is a neural network. Its input is a data point X, its output is a hidden representation Z, and it has weights and biases theta. Now to be concrete, let's say X is a 28 by 28 pixel photo of a handwritten number. The encoder encodes the data, which is 784 dimensional, into a latent representation space Z, which is much less than 784 dimensions. Now this is typically referred to as a bottleneck because the encoder must learn an efficient compression of the data into this lower dimensional space. Next is the decoder. The decoder is another neural net. Its input is the representation Z. It outputs the parameters to the probability distribution of the data and has weights and biases as phi. Running with a handwritten digit example, let's say the photos are black and white and represent each pixel as 0 or 1. Now the probability distribution of a single pixel can be then represented using a Bernoulli distribution. The decoder gets as input the latent representation of a digit Z and outputs 784 Bernoulli parameters, one for each of the 784 pixels in the image. The decoder decodes the real valued numbers in Z into 784 real valued numbers between 0 and 1. Information is lost because it goes from a smaller to a larger dimensionality. Now, how do we find out how much information is lost? The loss function equation helps us find the value. Now, this measure tells us how effectively the decoder has learned to reconstruct an input image X given its latent representation Z. The loss function of the variational autoencoder is the negative log likelihood with a regularizer. Because there are no global representations that are shared by all data points, we can decompose the loss function into only terms that depend on a single data point. So in the loss function, the first term is the reconstruction loss, or expected negative log likelihood of the ith data point. The expectation is taken with respect to the encoder's distribution over the representations. This term encourages the decoder to learn to reconstruct the data. Now, if the decoder's output does not reconstruct the data well, it will incur a large cost in the loss function. The second term is a regularizer that we throw in. This is the callback labeler divergence between the encoder's distribution. Now, this divergence measures how much information is lost when using Q to represent P. It is one measure of how close Q is to P. If the encoder outputs representations Z that are different than those from a standard normal distribution, it will receive a penalty in the loss. This regularizer term means keep the representation Z of each digit sufficiently diverse. If we didn't include the regularizer, the encoder could learn to cheat and give each data point a representation in a different region of Euclidean space. So now let's move on and have a look at the different types of autoencoders. The convolution operator allows filtering an input signal in order to extract some parts of its content. Autoencoders in their traditional formulation do not take into account the fact that a signal can be seen as a sum of other signals. Convolution autoencoders use the convolution operator to exploit this observation. Basically, they learn to encode the input in a set of simple signals and then try to reconstruct the input from them, modify the geometry or the reflectance of the image. Now, the encoder consists of three convolutional layers. The number of features changes from 1, the input data, to 16 for the first convolutional layer, then from 16 to 32 for the second layer, and finally from 32 to 64 for the final convolutional layer. Now, while transacting from one convolutional layer to another, the shape undergoes an image compression. So the decoder consists of three deconvolution layers arranged in sequence. For each deconvolution operation, we reduce the number of features to obtain an image that must be the same size as the original image. So in addition to reducing the number of features, deconvolution involves a shape transformation of the images. A convolution is the general continuous case defined as the integral of the product of two functions after one is reversed and shifted. As a result, a convolution produces a new function and it is a commutative operation. Now, in the 2D discrete space, the convolution operation is defined as the following equation. And in the image domain where the signals are finite, this formula becomes as such, where O of ij is the output pixel in position ij, and 2k plus 1 is the side of a square, that is the odd convolutional filter. F is the convolutional filter and I is the input image. Now, this operation is done for every location of the input image that completely overlaps with the convolutional filter. Now, let's see the use cases of convolution autoencoders. The first one is image reconstruction. Now, the convolution autoencoders learn to remove noise from a picture or reconstruct the missing parts. So, the input noisy version becomes the clean output version. The network also fills the gap in the image. Next is image colorization. Now, convolution autoencoders maps circles and squares from an image to the same image but with red and blue respectively. Purple is formed sometimes because of blend of colors where network hesitates between circle or square. Next up are some of the advanced applications such as fully image colorization, latent space clustering, and generating higher resolution images. Moving on to the next type of autoencoders. Sparse autoencoders offer us an alternative method for introducing an information bottleneck without requiring a reduction in the number of nodes at our hidden layers. Rather, we will construct our loss functions such that we penalize activations within a layer. So for any given observation, we will encourage our network to learn an encoding and decoding, which only relies on activating a small number of neurons. Now, this is a different approach towards regularization, as we normally regularize the weights of a network, not the activations. Now, there are two main ways by which we can impose this sparsity constraint. Both involve measuring the hidden layer activations for each training batch and adding some term to the loss function in order to penalize excessive activations. The first one is the L1 regularization. Now we can add a term to our loss function that penalizes the absolute value of the vector of activations A in layer H for observation I, now scaled by a tuning parameter lambda. The next one is the KL divergence. In essence, KL divergence is a measure of the difference between two probability distributions. We can define a sparsity parameter rho, which denotes the average activation of a neuron over a collection of samples. This expectation can be calculated in the following equation. Now, the KL divergence between two Bernoulli distributions can be written as such. Now, this loss term is visualized below for an ideal distribution of rho equals to 0.2, corresponding with the minimum penalty at this point. The next one is the deep autoencoders. Now, the extension of the simple autoencoder is basically the deep autoencoders. Now, the only difference to its simpler counterpart is number of hidden layers. The additional hidden layers enable the autoencoder to learn mathematically more complex underlying patterns in the data. The first layer of the deep autoencoder may learn first-order features in the raw input. The second layer may learn second-order features corresponding to patterns in the appearance of first-order features. Deeper layers of the deep autoencoder tend to learn even higher-order features. To put everything together, we need additional layers to be able to handle more complex data, such as the data we use in collaborative filtering. So let's have a look at some of the use cases of deep autoencoders. The first one is image search. Deep autoencoders are capable of compressing images into 30 number vectors. Image search therefore becomes a matter of uploading an image, which the search engine will then compress to 30 numbers and compare that vector to all the others in its index. Vectors containing similar numbers will be returned for the search query and translated into their matching image. A more general case of image compression is data compression, and deep autoencoders are useful for semantic hashing. Next up is the topic modeling and information retrieval. So deep autoencoders are useful in topic modeling or statistically modeling abstract topics that are distributed across a collection of documents. In brief, each document in a collection is converted to a bag of words, and those word counts are scaled to decimals between 0 and 1, which may be thought of as the probability of a word occurring in the document. For example, one document could be the question and others could be the answers. Now, a match the software would make using vector space measurements. The next type of autoencoders is the contractive autoencoders. One would expect that for very similar inputs, the learned encoding would also be very similar. We can explicitly train our model in order for this to be the case by requiring that the derivative of the hidden layer activations are small with respect to the input. In other words, for small changes to the input, we should still maintain a very similar encoded state. Now, this is quite similar to a denoising autoencoder in the sense that these small perturbations to the input are essentially considered noise, and that we would like our model to be robust against noise. Now, we can accomplish this by constructing a loss term which penalizes large derivatives of our hidden layer activations with respect to the input training examples, essentially penalizing instances where a small change in the input leads to a large change in the encoding space. Now, in fancier mathematical terms, we can craft our regularization loss term as the squared Frobenius norm of the Jacobian matrix J for the hidden layer activations with respect to the input observations. A Frobenius norm is essentially an L2 norm for a matrix, and the Jacobian matrix simply represents all first-order partial derivatives of a vector-valued function. Now, for m observations and n hidden layer nodes, we can calculate the values using the following equations. So now that we know the various types of autoencoders, let's have a look at how it actually works. So let's see the code that provides us with a reconstructed image. So this is the code for autoencoder that generates a similar output as the input with reduced dimensions. The packages that are needed to be pre-installed are NumPy, Keras, and Matplotlib. So first we define the size of our encoded representations. The encoded representation of the input is declared as encoded, while the lossy reconstruction of the input is declared as decoded. The input is then mapped to its encoded representation in order to create the decoder model. Next, we have to prepare our input data and normalize all the values between 0 and 1. The 28 by 28 images will be then flattened into vectors of size 784. Now, once the data is trained and tested, the autoencoder is trained. It will take certain values from the test set, encode and decode them. Now, for the visualization of the reconstructed inputs and the encoded representations, it is done with the help of Matplotlib library. So let's see what happens when we execute this code. So now we can see that the data is being trained and tested, and this will take a few minutes to complete. Now, once we are done with the training of the data, we will have an original image and a reconstructed image as our output. Our output will look like this. So the first row shows the original input image and the second row shows the reconstructed image with reduced dimensions. So now we have seen how an autoencoder actually works and how it provides us a reconstructed image. So now let's move on to some of the applications of autoencoders. Now, autoencoders are used for converting any black and white picture into a colored image. Depending on what is in the picture, it is possible to tell what the color should be. For example, the leaves of trees are generally green, the sky is blue, and the clouds are white. So all that is needed to be done is to make a computer be able to do this, and that is where autoencoders step in. The next application is the feature variation. It basically extracts only the required features of an image and generates the output by removing any noise or unnecessary interruption. Now, using autoencoders, we receive the same image as the input but with reduced dimensions. It helps in providing the similar image along with a reduced pixel value. Now, during the training, the autoencoder learns to extract important features from input images and ignores the image noises because the labels have no noises. The input seen by the autoencoder is not the raw input but a stochastically corrupted version. Now, autoencoders are also used for removing watermarks from images or to remove any object while filming a video or a movie. So now we have reached the end of today's session, and I hope you have a clear idea about what are autoencoders and how do they actually work. In the era of machine learning and deep learning, dimensionality reduction, classification, filtering, and regression play a very important role in feature selection and extraction. Now we have a number of algorithms that can perform these functions. But what if we have just one single algorithm that can perform all of these together? In today's session, we will learn about such an algorithm known as the restricted Boltzmann machines algorithm, and we will see how do they actually work. So let's move on and have a look at today's agenda. So first we will begin with a short history about restricted Boltzmann machines. Then we will move on and have a look at the difference between autoencoders and RBMs. Next up, we will see what are restricted Boltzmann machines and how do they actually work. In the next section, we will see one energy-based model and probabilistic model of RBM. Moving on, we will have a look at the training of restricted Boltzmann machines. In the final section, we will see one example of restricted Boltzmann machine using collaborative filtering. So let's begin the session. Now, restricted Boltzmann machine is an undirected graphical model that plays a major role in deep learning framework nowadays. Now, it was introduced as Harmonium initially, and it gained big popularity in recent years in the context of the Netflix prize, where RBMs achieved state-of-the-art performance in collaborative filtering and have beaten most of the competition. Many hidden layers can be learned efficiently by composing restricted Boltzmann machines using the feature activations of one as the training data for the next. These are basically the neural networks that belong to so-called energy-based models, and it is an algorithm which is used for dimensionality reduction, classification, regression, collaborative filtering, feature learning, and topic modeling. Now let's see how are autoencoders and RBMs different from each other. So autoencoders are a simple three-layer neural networks where output units are directly connected back to input units. Typically, number of hidden units is much less than number of visible ones. RBM also shares a similar idea, but it uses stochastic approach. Instead of deterministic, it uses stochastic units with particular distribution. Now you will notice that RBMs have two biases. This is one aspect that distinguishes them from other autoencoders. Now the hidden bias helps the RBM provide the activations on the forward pass, while the visible layers biases help the RBM learn the reconstructions on the backward pass. Restricted Boltzmann machines are shallow. They basically have two-layer neural nets that constitute the building blocks of deep belief networks. Now the first layer of the RBM is called the visible or input layer, and the second is the hidden layer. Each circle here represents a neuron-like unit called a node, and nodes are simply where calculations take place. Now the nodes are connected to each other across layers, but no two nodes of the same layer are linked, which means that there is no intra-layer communication. Now this is the restriction in a restricted Boltzmann machine. Each node is a locus of computation that processes input and begins by making stochastic decisions about whether to transmit the input or not. Now each visible node takes a low-level feature from an item in the dataset to be learned. For example, from a dataset of grayscale images, each visible node would receive one pixel value for each pixel in one image. Now let's follow that single pixel value x through the two-layered net. At node 1 of the hidden layer, x is multiplied by a weight and added to a so-called bias. The result of those two operations is fed into an activation function which produces the node's output or the strength of the signal passing through it given input x. Now let's look at how several inputs would combine at one hidden node. Each x is basically multiplied by a separate weight. The products are summed, added to a bias, and again the result is passed through an activation function to produce the node's output. Now each hidden node receives the four inputs multiplied by their respective weights. The sum of those products is again added to a bias, and the result is passed through the activation algorithm, producing one output for each hidden node. Now in the reconstruction phase, the activations of hidden layer become the input in a backward pass. Now they are multiplied by the same weights, one per internode edge, just as x was weight adjusted on the forward pass. The sum of those products is added to a visible layer bias at each visible node, and the output of those operations is a reconstruction, that is, an approximation of the original input. Now, because the weights of the RBM are randomly initialized, the difference between the reconstructions and the original input is often large. Now, let's move on and have a look at the energy-based model. Now, energy is a term that may not be associated with deep learning in the first place. Rather, energy is a quantitative property of physics. Yet, some deep learning architectures use the idea of energy as a metric for measurement of the model's quality. Now, one purpose of deep learning models is to encode dependencies between variables. The capturing of dependencies happen through associating of a scalar energy to each configuration of the variables, which serves as a measure of compatibility. Now, a high energy means a bad compatibility. An energy-based model always tries to minimize a predefined energy function. Now, the energy function for the RBMs is defined using the following equation. We can see that the value of the energy function depends on the configurations of visible states, hidden states, weights, and biases. The training of RBM consists in finding of parameters for given input values so that the energy reaches a minimum. Now let's have a look at the probabilistic model. RBMs are basically probabilistic. As opposed to assigning discrete values, the model assigns probabilities. Now at each point in time, the RBM is in a certain state. Now the state refers to the values of neurons in the visible and hidden layers V and H. Now the probability that a certain state of V and H can be observed is given by the following joint distribution. Here Z is called the partition function, that is the summation over all possible pairs of visible and hidden vectors. Now this is the point where restricted Boltzmann machines meet physics for the second time. The joint distribution is known in physics as the Boltzmann distribution, which gives the probability that a particle can be observed in the state with the energy E. As in physics, we assign a probability to observe a state of V and H that depends on the overall energy of the model. Unfortunately, it is very difficult to calculate the joint probability due to the huge number of possible combinations of V and H in the partition function Z. Much easier is the calculation of the conditional probabilities of state H given the state V and conditional probabilities of state V given the state H, which is represented using the following equation. Now the image datasets have unique probability distributions for their pixel values depending on the kind of images in the set. Pixel values are distributed differently depending on whether the dataset includes MNIST's handwritten numerals or the headshots found in labeled faces in the wild. Now let's have a look at the training of restricted Boltzmann machines. Now the training of RBM differs from the training of a regular neural networks via stochastic gradient descent. Now the two main training steps include Gibbs sampling and contrastive divergence. Now the first part of the training is called Gibbs sampling. Given an input vector V, we are using the following equation for prediction of the hidden values H. Now knowing the hidden values, we use the next equation for prediction of new input values V. This process is repeated a number of times, and after each iteration, we obtain another input which is recreated from the original input value. Now the update of the weight matrix happens during the contrastive divergence step. Now both the vectors are used to calculate the activation probabilities for the hidden values. Now the difference between the outer products of those probabilities with input vectors results in the updated matrix, which is represented using the following equation. Now using the updated matrix, the new weights can be calculated with gradient ascent, which is given by the next equation. Now let's have a look at the steps involved in the process of training to prediction in RBM. So the first step is to train the network on the data of all users. In the next step, take the training data of a specific user during the inference time. Now use this data to obtain the activations of hidden neurons in step 3. In step 4, use the hidden neuron values to get the activations of input neurons. Now finally, the new values of input neurons show the rating the user would give. So now that we have seen how a restricted Boltzmann machine works, so let's move on and have a look at the example of RBM using collaborative filtering. Now let's assume some people were asked to rate a set of movies on a scale of 1 to 5 stars. In classical factor analysis, each movie could be explained in terms of a set of latent factors. For example, movies like Harry Potter and Fast and the Furious might have strong associations with a latent factor of fantasy and action. On the other hand, users who like Toy Story and Wall-E might have strong associations with latent Pixar factor. Now, RBMs are used to analyze and find out these underlying hidden factors based on user preferences and corresponding collaborative movie tastes of all users. Now let's consider the following example where a user likes Lord of the Rings and Harry Potter but does not like The Matrix, Fight Club and Titanic. The Hobbit has not been seen yet, so it gets a -1 rating. Given these inputs, the Boltzmann machine may identify 3 hidden factors: drama, fantasy and science fiction, which correspond to the movie genres. Now in this example, only the hidden neuron that represents the genre fantasy becomes activate. Given the movie ratings, the restricted Boltzmann machine recognized correctly that the user likes fantasy the most. Now after the training phase, the goal is to predict a binary rating for the movies that had not been seen yet. Given the training data of a specific user, the network is able to identify the latent factors based on the user's preference. Now the latent factors are represented by hidden neurons, so we can use all our previous equations and sample from Bernoulli distribution to find out which of the visible neurons will become active. Now that's exactly how an RBM would help you identify which movie genre would the user prefer.
Creating accurate machine learning models capable of localizing and identifying multiple objects in a single image remained a core challenge in computer vision. But with recent advancement in deep learning and deep learning-based computer vision models, object detection applications are easier to develop than ever before. Welcome you to this session on object detection using TensorFlow. So before moving forward, let's have a quick look at the agenda of this session. So first of all, I'll be starting with explaining you guys what is exactly object detection. Then we'll have a look at the object detection workflow, how exactly it works, and the various industrial use cases of object detection. Then we'll understand what is TensorFlow, and I'll end this video with two demos. The first one being the TensorFlow object detection, where we can detect objects using our own input images, and the second demo is based on the live object detection, where we'll detect objects in real time. So without wasting any time, let's go ahead and start. Now, object detection allows for the recognition, detection, and the localization of multiple objects within an image. It provides us a much better understanding of an image as a whole as opposed to just visual recognition. In addition, with current approaches focusing on full end-to-end pipelines, performance has also improved significantly, enabling real-time use cases. Object detection is the process of finding instances of real-world objects such as faces, bicycles, and buildings in images or videos. Now, object detection algorithms typically use extracted features and learning algorithms to recognize instances of an object category. It is commonly used in applications such as image retrieval, security, surveillance, and advanced driver assistance system, which is known as ADAS. Now let's have a look at a few of the object detection applications. Now the first use case is the facial recognition. Now popular applications include face detection and people counting. Have you ever noticed how Facebook detects your face when you upload a photo? That is due to their facial recognition algorithm. Now this is a simple example of object detection that we can see in our daily life. Even the DSLR cameras and our phone cameras also detect the faces. Object detection can also be used for people counting. It is used for analyzing store performance or crowd statistics during festivals, where people tend to get lost easily. Now these tend to be more difficult as people move out of the frame quickly, and also because people are non-rigid objects. Object detection is also used in industrial process to identify products. Finding a specific object through visual inspection is a basic task that is involved in multiple industrial processes like sorting, inventory management, machining, quality management, packaging, and much more. Inventory management can be very tricky as items are hard to track in real time. Something is always added, removed, and moved every day. Systems can perform automatic object counting and localization that will allow you to improve inventory accuracy. Now, this is one of the most recent, and I should say one of the most exciting use cases of object detection, which is the self-driving car. It is a vehicle that is capable of sensing its environment and navigating without human input. Now, how is it done? Now, it combines a variety of techniques to perceive the surroundings, including the radar, laser light, GPS, and also computer vision. Now, here is where the object detection comes in place. So the moment it senses a person on the road on its way, the car automatically stops. Advanced control system interprets sensory information to identify appropriate navigation paths as well as obstacles. Now our final use case is the most important one, which is the security. Now it is used in the banking industry as well as the phone industry, or I should say the technological industry a lot. So it is used in the banking industry to identify fraud, the forgery of notes or the currency, and also theft. Now, one of the most important use of object detection is the facial recognition used in the smartphones nowadays, which is popularly known as face unlock. Now that we have understood what are the various industrial use cases of object detection, let's have a look at the object detection workflow. Now, typically there are 3 steps involved in object detection workflow. First of all, we have the training data, which we input and create our model. Now this model is created using the visual features which are extracted from the images or the digits or whatever be your input of the training data. Now these are evaluated and it's determined whether which objects are present in the proposal based on the visual features. Now upon extracting these features, we have a classification model created. Now after that, we have the testing data. In our final post-processing step, we use the testing data and we extract all the features. And then we move on to our model to see which all features are matching which type of class. And finally, after the computation is done, we finally get our result. Now, there is an important trade-off being made here, which is between the number of regions versus the computational complexity. We'll learn more about these later in this video. Now, in object detection frameworks, people typically use pre-trained image classification models to extract visual features, as these tend to generalize fairly well. The goal of feature extraction is to reduce a variable-sized image to a fixed set of visual features. Image classification models are typically constructed using strong visual feature extraction methods, whether they are based on traditional computer vision approaches such as the filter-based approach, the histogram methods, or the deep learning methods. They all have the exact same objective, extracting features from the input image that are representative for the task at hand and use these features to determine the class of the image. Now that we have understood the basic workflow of an object detection algorithm, now let's see how object detection can be performed in TensorFlow. So first of all, we provide our input data, which is a set of images, and using TensorFlow, we train our model. Now this model is trained using deep learning, and the main objective of this model is to extract the features. Now these are visual features which are based on edge detection, the HAR features, the facial recognition, and many more. Now when these features are extracted and then the model is created, to test this model, we provide our test data, which is again a set of images in our case. And using this model, we get our final output in which we have the objects detected in an image. Now, the images are converted into a NumPy array in the TensorFlow object detection so that the computation can be made easy. We also use the TF record, which is the TensorFlow record, which contains the record of the image along with the tags, such as you can see here, we have the person tag, we have the dog tag, and the horse tag. Now these tags are just labels which are provided in the input data. Now let's go ahead and start our demo and see how we can perform object detection using TensorFlow. Now to begin with, you want to make sure that you have TensorFlow installed with all of its dependencies like the tensor board, Python, matplotlib, we have the Cocoa API and the protobuf. Now I'll explain you guys what all steps are needed. So for CPU TensorFlow, you can just do pip install TensorFlow, but of course the GPU version of the TensorFlow is much faster at processing, so it is ideal. Now next we need to do is to clone the GitHub repository of TensorFlow. So for that, just go to GitHub and type TensorFlow, which is the official GitHub repository of TensorFlow. And inside that we have the models section. Just go to this models. You can either clone this TensorFlow model or download it as per your wish. So I have already downloaded the TensorFlow model. Now the TensorFlow object detection model uses protobuf to configure model and the training parameters. Before the framework can be used, the protobuf libraries must be compiled. Now to download protobuf, all you need to do is go to Google/protobuf in GitHub, and here you will have all the different versions of protobuf. So according to your OS, which is Linux, Mac OS, or the Windows OS, or if you are using only the Python, you can download the required protobuf. So once you have downloaded TensorFlow and protobuf, create a folder in just C, which is known as TensorFlow, and in this you'll have the models master. Extract this and rename it as models and extract the protobuf. Now inside protobuf, you have the bin folder. Now all you need to do is go to this bin folder. So let me just open the command prompt. Here I am using the Anaconda prompt, but you can use the command prompt as well. So once you have downloaded and renamed the models master as models, go back to the GitHub repository, and inside models you have the research, and inside research there is the object detection model which we are interested in. So let's go to the object detection model here. Now as you can see, this TensorFlow object detection API gives an accurate machine learning model description of how the objects are detected, and here you have the steps for the setup. So in the installation, as you can see, we have the prerequisites or the dependencies, which are the protobuf, Python, Pillow. You can install all of these using the pip or the conda command. Okay, so to download the protobuf on Ubuntu, you can do the sudo apt-get install. Then you can use the Cython, the contextlib, the Jupyter, and the matplotlib. Alternatively, you can also use the pip and the conda commands. And next, what you need to do is, once you have downloaded and extracted the protobuf, you need to copy this command. Now then you need to go into the TensorFlow, then you need to go into the models, and then inside that you need to go into the research. Now once you are inside the research, what you need to do is copy this command and paste it and run this command here. So what it'll do is, I'll explain here, is that it'll take all the object. If you go inside the models, research, and inside if you go to the object detection, you can see there's a folder named protos. So once you have compiled that code, all the proto files are then converted into the Python files. Now in order to have a better understanding of what the different supported components are, inside the protos folder, which contains the functional definition, especially the train, the eval, the SST, the faster RCNN, and the processing protos, which are important while training a model, all these proto files are present here. What you need to do is that run that command and all the protos file will be converted into Python executable files. Now after that, what we need to do is Cocoa API installation. Now let's understand what is Cocoa. Now Cocoa refers for common objects in context. It is a large image dataset designed for object detection, segmentation, person key points detection, stuff segmentation, and caption generation. Now this package provides MATLAB, Python, and Luna APIs that assist in loading, parsing, and visualizing the annotations in Cocoa. As you can see, we have 330K images, in which we have more than 200K labeled images. We have 1.5 million objects instances, 80 object categories, we have 91 stuff categories, 5 captions per image, and we have 250 people with these key points. Now, when you have downloaded the models, inside models, research, and inside the object detection, you need to go to the G3 doc, in which we have the TensorFlow detection model zoo. Now here we have all the list of models which are trained on the Cocoa dataset. So as you can see, we have the SST MobileNet version 1, we have the SST MobileNet version 1 PPN Cocoa, Depth Cocoa, we have the SST Inception, we have faster RCNN, we have different mask RCNN Inception. Now an important thing to consider here while selecting a model is that it depends on your system which model you should use. Suppose if your system is low on GPU but has higher RAM, you can go for a model which has a higher speed and a higher MAP point. Now this value should always be high if you're looking for a more accurate prediction in your images. So once all your dependencies are downloaded and you have installed TensorFlow and protobuf, let's go ahead and see how we can do the coding. Now inside the object detection folder, there is an object detection tutorial. Now first of all, what we need to do is import all the libraries, the NumPy, the OS, the SYS star file. We are importing TensorFlow as well. We are importing the collections and the various imports which are needed. Then we need to append the path of the object detection folder. And finally, if the version of TensorFlow is less than 1.4, we need to upgrade it as the latest tutorial supports the TensorFlow object 1.4 and above. So let's run this block by block. So first of all, let's load all the libraries. Now next what we are going to do is import the object detection module, some of the labels, which are the label map util, which will be later used to provide the labels to the input images, and based on that our model will be created. Now next what we are going to do is we are going to select which model to download. So for example, here we are using the SST MobileNet version 1 Cocoa 2017. So if you go back to the list of the models, you can select any of the given models here. But make sure your system should support the required amount of RAM and it should have the required amount of GPU to support the models which you are selecting. So for this tutorial, I'm using a model which will give me the results faster. So all you need to do is provide the model name, the model file, and the download base from where it should download. Now, as I mentioned earlier, that TensorFlow works on the graph principle, which is the data flow graph. So what we are going to do is give the path to the detection graph, which we are going to use here, which will be supported by this model. And then we are going to give the path to the labels. Now, to download the models, we have this code which will take the URL and which will download this file and produce the frozen inference graph of that model, which is the SSD Coco MobileNet. So once this has been done, we are going to load the graph, which is the frozen inference graph, into the memory. So here we are using the tf.graph method and tf.graphdef to define the graph which we are going to use. Next, what we need to do is load all the labels and the categories and the category index from our data set. So the data set is Coco. So once we have loaded all the labels and the categories, now is the time to convert all the images to a NumPy array. So this code, which is definition here of the load image into NumPy array, which we will use later in this code, what it does is takes the images and converts it into a NumPy array, so it will be easier for TensorFlow to process it. Now here we are going to provide the images for testing purposes. So as you can see, we have the test image folder here, and inside that you can input all your images, whichever you want to test upon this model. So for example, I have taken the range from 1 to 8. It will take all the images named image 1 to image 7. So let's load this. Now this function, what it does is run the inference for a single image. Now for a single image, first of all, it detects all the boxes, the detection mask, and provides a certain box on the object it detects. And finally, we have the for loop, the main for loop, in which we'll take the images from the test image path and open them, and one by one we'll take all the images and do the inference for a single image one by one. So as you can see, we are using the load image into NumPy array. We are using the np.expand. Now we'll expand the dimensions since the model expects images to have the shape, which can be 1, 2, 3 based upon the categories. And you can see the output will get the detection boxes, the detection classes, and the detection score. And finally, we are using the matplotlib to show us the image. So let's run this. We'll get our output here. So this might take time depending upon the processor which you are using or the system which you are using. So since we have taken the model which will take the least amount of time, this shouldn't take much time. But then again, TensorFlow is heavy and the tensors are multidimensional arrays, as I explained, which do all the heavy computation. So guys, here we have the results. So as you can see, let's begin from the start. As you can see, it identified the dog as a 94%. It has provided a box, the label, and the score, which is the detection score, how much it is similar to all the images which have been inputted in the Coco dataset. So as you can see here, we have the person, the various percentage, we have kite, here we have a tie detected. It can detect objects in such a heavy background. As you can see, the person are so much camouflaged in the background, but still it has managed to score that person. As you can see here, it has detected an airplane, person, kite. Now you can use your own images. All you need to do is copy that images into the test image folder and use the naming convention provided here as the image 1, image 2. So now let's go ahead to our second demo, which is the live object detection. Now in this demo, we will use the OpenCV. So let me show how we can do the coding here. So first of all you need to do is copy all the code and paste it into another Python file. So once you have pasted, the major changes which are involved in the live detection of the images is that we are going to use OpenCV. So first of all, we need to import CV2 here, as you can see, and we have defined an object CAP that will capture. So we are going to use CV2.videoCapture. Here you can change the model which you want to download, because if you have a higher GPU and the refresh rate of the images is also high, you should take a model that has an equal balance among the speed and also the accuracy of the image detected. So all this will remain same, and I'll show you what all changes we need to make. So what you need to do is, for image path in test images, as you can see, we do not need this code because our images will be not coming from the test image folder, as it will be coming from our webcam. So you need to remove these codes, and instead of that, you need to do is input these line of code, which is while true, return, and we'll use image np as that's the exact name which is being used here by the TensorFlow code. And we are going to use gap.read. So what it'll do is it'll take the input of the video which is coming through the webcam, and then we need to remove these two lines as well, which is the plt.figure and the plt.image_show, because we are not using matplotlib anymore and we'll be using the OpenCV. So we'll do cv2.imshow, and this is the name of the window which will come up. And for instance, we are resizing it, the image to 800 is to 600. Now we need to provide this code as well. Now what we'll do, it is the wait key option of 25 seconds. And if we press Q or for 25 seconds, the screen is black, it will automatically destroy all the windows and break out of the loop. So here you do not need to run this code, which is the path to the test image, because it's not needed. You do not need to convert the images into the NumPy array, because all the images coming through the OpenCV is already in an array format or a structured format. So let me just open another console for you. So first of all, we'll import all the necessary libraries, the CV2, we have the TensorFlow. We are going to import the label APIs and the label frameworks which are used here. Now we have already downloaded this model. What you can do is again run this code, but that won't help either. Next, you need to load the frozen inference graph. After that, we need to load all the labels. And finally, we need to run our final code block, which is the object detection, which will call all the definitions which I have provided earlier. So guys, as you can see here, it has opened up a window of 800 cross 600. And as you can see, it has successfully detected the TV as 92% of TV, and keyboard also has been detected at 90%. So as you can see, it is also detecting the bottle which we have provided here as 92%. It is also detecting the cup as well. So what about the phone? Let's see if it detects it as a cell phone or not. Let me just keep it in the frame. As you can see, it has detected cell phone. Now the refresh rate of this particular model is slow because we needed the result fast. But if you have a higher GPU system and the CPU is good, you can use more advanced model with a higher refresh rate. So as you can see here, it has detected clock, the watch as clock. And the moment it receives any part of human body in the frame, as you can see, if my hand is there, it will detect it as a person. Okay. You can see it is detecting the TV, the cup. It will also detect the phone as well, the cell phone. So as you can see here, it is also detecting the chairs. So as you can see, it has also detected my chair as well. So guys, as you can see, it has also detected me as a person. That is good to know.
In today's session, we will learn how to create a chatbot using TensorFlow. Now, before we get into the details of chatbot, let's first find out why do we need them. Now, the first chatbot was named Eliza that blurted out canned lines for certain keywords using programmed scripts. Many users developed an affinity towards her even after knowing that the program simply followed a script. Since then, chatbots have advanced beyond scripts and rules. The new generation chatbots can encourage human-like conversations with the help of artificial intelligence. Now, it all started with one question: can machines think? The concept of chatbots came into existence to check whether the machines could fool users and make them think that they are actually talking to humans and not robots. On the other hand, with the success rate of chatbots, different companies started using the machines for having conversations with their customers about everything, which made their work simpler and reduced the need of manpower. So now that we know the importance of chatbots, let's have a deeper insight about what are these and how do they work. The evolution of artificial intelligence has seen its peak in the recent times, and chatbots are a faint splash on a huge wave of progress. A chatbot is an assistant or an automated system that communicates with us through text messages. It integrates into websites, applications, or instant messengers and helps entrepreneurs get closer to customers. Now let's have a look at the number of steps involved in the working of a chatbot. Now the first step is to convert the user's text or speech into structured data in order to find the related answers. Some of the natural language processing steps include sentiment analysis, tokenization, normalization, and dependency parsing. Now, chatbots process the text presented to them by the user before responding according to a complex series of algorithms that interprets and identifies what the user said, then infers what they mean and determine a series of appropriate responses based on this information. Any system or application that relies upon a machine's ability to parse human speech is likely to struggle with the complexities inherent in elements of speech, such as metaphors and similes. Now, despite these considerable limitations, chatbots are becoming increasingly sophisticated, responsive, and more human like. Now, it provides a real time customer experience along with universal content accessibility. It is believed that chatbots will take over almost 85% of all customer service interactions by 2020. Now, training a chatbot happens at much faster and larger scale than teaching a human. Humans customer service representatives are given manuals, while the customer support chatbot is fed with thousands of conversation logs, and from those logs, the chatbot is able to understand what type of question requires what type of answers. Now, the working of all these steps together provides us the required chatbot which responds to the users or customers and makes them believe that they are talking to humans and not robots. So, we have talked about the steps involved in the working of a chatbot, but there are certain things that need to be kept in mind while creating one. The 5 important key points that should be considered for a chatbot to work perfectly or more like a human includes the volume of conversations, consistency of the agents, training the agents, length of conversations, and complexity of the incoming and outgoing questions. So far, we have talked about how the chatbots work and how they are used to initiate conversations with users or customers. Now, let's take a look at some of the applications of chatbot in our everyday life. Ordering our favorite food has become much easier now. We can take help from the online assistant and select our option for delivery. A few quick steps through Messenger and your pizza will be delivered at your doorstep. If you're looking for the perfect house or a society, the chatbot will also work as your personal assistant to find that perfect house for you in your desired locations without much hard work. Now, we all have booked flight tickets online, but with the help of a chatbot, the work has become even more simple. All you have to do is provide your destination, and it will find you the flights suitable for your journey, and you can book your tickets with just one click. Not just that, it can also help you in selecting the dress you want or the shirt that will fit you. They can help you in finding the right product based on your preferences. The chatbots are not only helpful in case of food delivery or booking flight tickets, they provide a great assistance in case of emergency as well. It provides you with all the information that you would need during a medical emergency, such as nearest hospitals, working hours, medicine delivery, and a lot more. Now let's discuss the layers of chatbot in details. The first layer is the natural language processing layer. Now it is the ability of a computer program to understand human language as it is spoken, and it is a component of artificial intelligence. Now the machine interprets the important elements of the human language sentence, such as those that might correspond to specific features in a data set, and returns an answer. Now there are two main components of NLP. The first one is the natural language understanding. It maps the given input in natural language into useful representations and analyzes different aspects of the language. The second component, natural language generation, is the process of producing meaningful phrases and sentences in the form of natural language from some internal representation. Now, this involves text planning, sentence planning, and text realization. The next layer is the neural networks. It is an information processing paradigm that is inspired by the way brain processes information. Now, neural depicts neurons, and network is the connection between them. It has the remarkable ability to derive meaning from complicated or imprecise data and can be used to extract patterns and detect trends that are too complex to be noticed by either humans or other computer techniques. Now, the next layer is deep learning. It is a subset of machine learning and artificial intelligence that has networks capable of learning unsupervised form of data that is unstructured or unlabeled. It is a subfield of machine learning concerned with algorithms inspired by the structure and function of the brain called the artificial neural networks. Now, in traditional machine learning techniques, most of the applied features need to be identified by a domain expert in order to reduce the complexity of the data and make patterns more visible to learning algorithms to work. The biggest advantage of deep learning algorithms is that they try to learn high-level features from data in an incremental manner. Now, this eliminates the need of domain expertise and hardcore feature extraction. Now, another important layer is TensorFlow. Machine learning is a complex discipline, but implementing machine learning models is far less daunting and difficult than it used to be, thanks to machine learning frameworks such as Google's TensorFlow that ease the process of acquiring data, training models, serving predictions, and refining future results. It is an open source library for numerical computation and large scale machine learning. TensorFlow bundles together a slew of machine learning and deep learning models and algorithms that makes them useful by way of a common metaphor. So now let's see how all these layers combine together and set the workflow of chatbots. The first step is to determine the role of your bot and set goals. Be specific about what you want your bot to do and then evaluate and pick a channel. The next step is to create the conversational architecture. It basically organizes the content and finds the best way toward the bot's answers. The dialog flow goes into the detail to implement the bot. Now, one of the most important resources you will need to assemble is a collection of question variations reflecting the different ways your customer can ask for something. Now, the next step is to pick a platform and a development approach. The chatbot needs to determine the intent of the sentence and extract data from the sentence. Next is the implementation of the dialog flow and to engineer the natural language understanding. If you have a platform based on machine learning, you will provide it with example sentences for each possible intent. So now in the final step, you have to perform internal testing and revise your use case detection. Now to ensure a successful outcome of your chatbot deployment, view the creation as an iterative process. Now, because of the nature of human language and the infinite possible expressions of every question or intent, the goal of 100% accuracy is an unattainable one, even for a human being. So let's have a look at the code that will make our chatbot talk to us. So here we have a set of reflections that trains the chatbot to reply in a particular manner. Now in the multifunction called class, we generate the session ID for any string in order to join or split the sentences, which is then matched with the trained data set for similar answers. So once we are done normalizing, now we will substitute words in the string according to the specified reflections. Now after this, the client statements will be substituted into responses so that the chatbot can answer according to a particular query. Once we are done with this, now it's time to generate a response to the user input. The user would be expecting an accurate answer from the chatbot. Now once the mapping of the words and the strings are done, the chatbot is ready to hold a conversation with a human being and reply to all the queries. So now let's see how the demo of our chatbot works. So let me start by responding to its question and then see how it responds to my queries. So we can see that the chatbot will not provide a 100% accurate response or exactly the way we want it to reply, but it must understand the question and provide a satisfying response. Now we can see that our chatbot is up and running and it is able to hold a conversation with us. With the help of all the layers involved in the working of our chatbot, such as NLP, neural networks, deep learning, and TensorFlow. So I hope you all understood how all these layers work together in machine learning and helps in building a robot that can almost talk like a human being.
Now, deep learning is a hot buzzword nowadays and has firmly put down its root in a vast multitude of industries that are investing in fields like artificial intelligence, big data, and analytics. So, for example, Google is using deep learning in its voice and image recognition algorithms, whereas Netflix and Amazon are using it to understand the behavior of their customers. Even Tesla is using deep learning in their self-driving cars. Now imagine how much potential deep learning has in revolutionizing the world and the way we work around things. Now this growth of deep learning and its application has led to the growth of deep learning jobs even. For example, we have the data scientists, we have machine learning engineer, we have artificial intelligence engineer, and much more roles. So let's begin our deep learning interview question and answer session and understand what are the typical questions which are being asked in deep learning interview. So the first and foremost question what any deep learning interviewer asks is the basic understanding of the relationship between machine learning, artificial intelligence, and deep learning. So basically, artificial intelligence is a technique which enables machine to mimic human behavior. And machine learning is a subset of artificial intelligence technique which uses statistical methods to enable machines to improve with experience. Now, deep learning, on the other hand, is a subset of machine learning which makes the computation of multi-layer neural network feasible. It uses neural networks to simulate human-like decision making. Now, coming to the second question, do you think deep learning is better than machine learning? And if so, why? Now, though machine learning algorithms, the traditional machine learning algorithms, solve a lot of our cases, but they are not very useful while working with high dimensional data. Now, that is where we have a large number of inputs and outputs. For example, in case of handwriting recognition, we have large amount of inputs where we have different types of input associated with different types of handwriting. Now, another major challenge is to tell the computer what all features it should look for that will play an important role in predicting the outcome as well as to achieve better accuracy while doing so. So these are some of the few shortcomings what machine learning have, and deep learning overcomes all of these shortcomings. Now coming to our third question, which is what is a perceptron and how does it work? Now actually our brain has subconsciously trained itself to do a lot of things over the years. Now the question comes, how does deep learning mimics the functionality of the brain? Well, deep learning uses the concept of artificial neuron that functions in a similar manner as the biological neuron present in our brain. Therefore, we can say that deep learning is a subfield of machine learning concerned with algorithms inspired by the structure and the function of the brain called artificial neural networks. Now, if you focus on the structure of a biological neuron, it has dendrites which is used to receive inputs. Now, these inputs are summed in the cell body and using the axon, it is passed on to the next biological neuron. Now, similarly, a perceptron receives multiple inputs, applies various transformations and functions, and provides an output. Now, a perceptron is a linear model used for binary classification. It models a neuron which has a set of inputs, each of which gives a specific weight. Now, the neuron computes some function on these weighted inputs, and then finally it provides the output. As we know that our brain consists of multiple connected neurons called the neural network, we can also have a network of artificial neurons called the perceptron to form a deep neural network. Now coming to the next question, what is the role of weights and biases? Now for a perceptron, there can be one or more input called bias. While the weights determine the slope of the classifier line, the bias allows us to shift the line towards left or right. And normally bias is treated as another weighted input with the input value x in our case. If you have a look at a typical perceptron, what it receives is a set of input. Now these inputs are not just input which it gathers, so weights are an additional input which it takes, and according to that it computes and provides an output. Now which brings us to the next question, which is what exactly are activation functions? So activation function translates the inputs into outputs, and it uses a threshold to produce an output. So the activation function decides whether a neuron should be activated or not by calculating the weighted sum and further adding the bias with it. And the purpose of the activation function is to introduce a non-linearity into the output of a neuron. There can be many activation functions like linear or identity. We have the binary step, we have sigmoid, we have the tanh, we have ReLU and softmax. These are a lot of activation functions which are being heavily used in the deep learning industry. So one should actually know about all of these things. Now, talking about perceptron, our next question, what an interviewer might ask is explain the learning of a perceptron. So basically, a perceptron has 4 steps of learning. So the first steps is initializing the weights and threshold. So just now, as I mentioned, initializing the weights and threshold so to the perceptron so that it can activate a neuron by calculating the weighted sum and further adding the bias in and all. This is the first step, and the second step is providing the input and calculating the output using the activation functions. And according to that, what we do is the third step involves updating the weights. Now, once a particular perceptron learns something, it has to update the weights so that it can learn much more things in a new manner. And the next step, what comes is just repeat the step number 2 and 3, which is provide the input and calculate the output and then update the weights accordingly. Now, if we have a look at the equation here, we have wj(t) plus 1 that equals wj of t plus n of t minus yx. The wj of t plus 1 is the updated weight, whereas wj of t is the old weight, d is the desired output, y is the actual output, and x is the input. So this is the equation of the learning of a perceptron. Now the next question is, what is the significance of a cost or a loss function? So a cost function is a measure of accuracy of the neural network with respect to a given training sample and expected output. It provides the performance of a neural network as a whole, and in deep learning, the goal is to minimize the cost function. So for that, we use the concept of gradient descent. Now, which brings us to the next question, which is, what exactly is gradient descent and what are its various types? So gradient descent is an optimization algorithm which is used to minimize some function by iteratively moving in the direction of the steepest descent as defined by the negative of the gradient. Now think of it as a bowl in which you start from any particular point and the goal is to reach the bottom of the bowl, which is the gradient descent. So there are 3 types of gradient descent, which are the stochastic, batch, and the mini batch. So stochastic gradient descent, it uses only single training example to calculate the gradient and update the parameters accordingly. Whereas the batch gradient descent calculates the gradients for the whole dataset and performs just one update at each iteration. Now, mini batch gradient descent is a variation of the stochastic gradient descent where instead of single training example, many batch of samples are used, and it is one of the most popular optimization algorithm. Now, if we talk about mini batch gradient descent, one might ask is, what are the benefits of the mini batch gradient descent, or how is it useful than the others? Now, the mini batch gradient descent is more efficient when compared to the stochastic gradient descent, and the generalization is done by finding the flat minima, which allows to help approximate the gradient of the entire training set, which help us to avoid the local minima. Now, this is why mini batch gradient descent is considered or is preferred over the regular gradient descent algorithm, which is the stochastic gradient descent. Now, one might ask, what are the steps for using a gradient descent algorithms? So first of all, what you need to do is initialize some random weight and bias. And after that, you need to do is pass an input through the network and get values from the output layer. Next, what you're going to do is calculate the error between the actual value and the predicted value. Now, this can be done in a number of ways. Now, the next step involves is to go to each neurons which contributes to the error and change its respective values to reduce the error, which is basically our goal is to reduce the cost of any particular function or any particular model. So after that, what you do is reiterate until you find the best weights of the network and you find the lowest cost of the particular network. So one might ask you to write any gradient descent program or write the pseudocode of any gradient descent program. So what you need to do, first of all, what we do is define the parameters, which are the weights, the hidden weights, the weight output, the bias hidden, and the bias output. We define a function std with arguments as cost, the parameters what we have discussed, and the learning rate. Now what we do is we then define the gradients of our parameters with respect to the cost function. So here we use the Theano library to find the gradients, and we import Theano as t, and finally iterated through all the parameters to find out the updates for all the possible parameters. So you can see that we use vanilla gradient descent here, and as you can see it returns the updates, and what we do is update the parameters and the cost in this particular equation. The ultimate goal of any gradient descent algorithm is to minimize the cost. Now talking about perceptron, what are the shortcomings of a single layer perceptron? So well, there are two major problems. Now first of all is that the single layer perceptron cannot classify non-linear separable data points. And the second point is that the complex problems that involve a lot of parameters cannot be solved by a single layer perceptron. Now consider an example here and the complexity which arises when the parameters are involved to take a decision by a marketing team. So first of all, we have the categories, which are the email, direct, paid, referral program, or the organic. And inside this category, we have subcategories, which are the Google, Facebook, LinkedIn, Twitter, we have Instagram now. And inside that, we have the type of subcategory, which are the search ads, remarketing ads, interested ads, lookalike ads. And again, if we do a subdivision, we have the parameters to consider, which are the customer acquisition cost, we have the money spent, the click rate, or the lead generated, the customer generated, and the time taken to become a customer. So one neuron cannot take in so many inputs, and that is why more than one neuron would be used to solve this problem. Now, which brings us to the question, what is a multi-layer perceptron? So a multi-layer perceptron, or MLP, is a class of feed-forward artificial neural network, and it is composed of more than one perceptron. They are composed of an input layer to receive the signal, an output layer that makes a decision or the prediction about the input, and in between these two, an arbitrary number of hidden layers that are the true computational engine of any multi-layer perceptron. Now one might ask, what are the different parts of any multi-layer perceptron or a neural network? So first of all, what we have are input nodes. So the input nodes provide information from the outside world to the network and are together referred as the input layer. No computation is performed in any of the input nodes. They just pass the information to the hidden layers. Now hidden nodes have no direct connection with the outside world, hence the name hidden. And what they do is they perform computation and transfer the information from the input nodes to the output nodes. Now a collection of hidden nodes forms the hidden layer, and while a network will only have a single input layer and a single output layer, it can have 0 to n number of hidden layers, and a multi-layer perceptron has more than one hidden layer. Now if we talk about output nodes, the output nodes are collectively referred to as the output layer and are responsible for the computation and transferring information from the network to the outside world, and hence they are also responsible for the prediction. Now coming to our next question, what exactly is data normalization and why do we need it? Now data normalization is a very important pre-processing step, which is to normalize the data. The data should not be either left skewed or right skewed. It should be normal, and is used to rescale the values to fit in a specific range to assure the better convergence during backpropagation. And in general, it boils down to subtracting the mean of each data point and dividing by its standard deviation so that we get a normally distributed data. And it makes computation easy in terms of the backpropagation in case of a neural network. So this is a very important part of any deep neural network. Now talking about deep neural networks, or neural networks in general, coming to our next question, which is, now what is better, the deep networks or the shallow ones, and why? Now both the networks, be it shallow or deep, are capable of approximating any function. What matters is how precise that network is in terms of getting the result. Now a shallow network works with only a few features. as it cannot extract more, but a deep network goes deep by computing efficiently and working on more features or the parameters. Now, deeper networks are able to create deep representation. At every layer, the network learns a new, more abstract representation of the input, and hence deep neural networks are better than the shallow ones. So, what exactly is weight initialization in a neural network? Now, as we saw, we had weight initialization in perceptrons. So, weight initialization is one of the very important steps. A bad weight initialization can prevent a network from learning, but good weight initialization can help it in giving quicker convergence and a better overall error. Now, biases can be generally initialized to zero. The rule for setting the weights is to be close to zero without being too small, because every time the weight is being multiplied to the inputs, the result gets smaller and smaller. Now, talking about neural networks, what is the difference between a feed-forward and a backpropagation neural network? Now, a feed-forward neural network is a type of neural network architecture where the connections are fed forward, that is, they do not form cycles. The term feed-forward is also used when you input something at the input layer and it travels from the input to the hidden and from the hidden to the output layer. The values are fed forward. Now, backpropagation is a training algorithm which consists of two steps majorly. The first one is feed forwarding the values, and the second one is to calculate the error and propagate it back to the earlier layers. So, to be precise, forward propagation is a part of backpropagation algorithm, but it comes before the backpropagation. So one might ask the question, which is one of the most important questions, is that what are the hyperparameters in a neural networks, and name a few of these hyperparameters. So hyperparameters are the variables which determine the network structure. That is, for example, the number of hidden units and or the hidden layers, and the variables which determine how the network is trained. For example, the learning rate. So there are two types of hyperparameters usually. One are the network parameters which are associated to the network. In that case, we have the number of hidden layers, we have the network weight initialization, we have the activation function. And in the training parameters, we have the learning rate, we have momentum, number of epochs, we have the batch size, and much more. Now, a lot of hyperparameters also differ when we work along with different types of neural networks. So as in CNN, we get extra parameters to work on when considering CNN, which are the convolutional neural networks. And sometimes we have to deal with less number of hyperparameters. It all depends upon the type of neural network which you are using. So, which brings us to the next question, is that explain the different hyperparameters related to networking and training. So in training, we have, first of all, we have the number of hidden layers. So hidden layers are the layers between the input and the output layers, as we just discussed. And many hidden units within a layer with regularization technique can increase the accuracy, and smaller number of units may cause underfitting. Now, another important aspect is network weight initialization. So ideally, it may be better to use different weight initialization schemes according to the activation function used on each layer. Mostly uniform distribution is used, or the normal distribution. Now, if we talk about activation function, so they are also used to introduce non-linearity to the models. They are also used to introduce non-linearity to the models, which allows deep learning models to learn non-linear prediction boundaries. Now, generally, the rectifier activation function, or the ReLU, is the most popular. Now, if we talk about the training parameters, so these were the network parameters which have to be initialized to a deep neural network before the training begins. And just before the training, we have the training parameters, which are the learning rate. So the learning rate defines how quickly a network updates its parameter. Low learning rate slows down the learning process but converges smoothly. A larger learning rate speeds up the learning but may not converge as smooth as a low learning rate. Usually a decaying learning rate is preferred so that we get the best of both worlds and we get the best expected output. Now another hyperparameter is momentum. So momentum helps us to know the direction of the next step with the knowledge of the previous step. Now it helps to prevent oscillation, and a typical choice of momentum is between 0.5 to 0.9. Now, if we talk about the number of epochs, so epochs is basically iterations. So number of epochs is the number of times the whole training data is shown to the network while training. So increase the number of epochs until the validation accuracy starts decreasing, even when tiering accuracy is increasing. So that results in sometimes overfitting. And if we talk about the batch size, so mini batch size is the number of subsamples given to the network after which parameters update happen. So a good default for batch size might be 32 or 16, 64. It depends upon the size of the data you have. It can be any arbitrary number, but it's always better to have it in the power of 2, right? So while we were talking about overfitting, which brings us to our next question, which is what exactly is a dropout? So dropout is a regularization technique to avoid overfitting, which is to increase the validation accuracy, thus increasing the generalization power. Now generally use a small dropout value of 20% to 50% of the neurons, with 20% providing a good starting point, and a probability too low has minimal effect, and a value too high results in underlearning by the network. So first of all, what you need to do is use a large network, and you are likely to get better performance when the dropout is used on a larger network, giving the model more of an opportunity to learn independent representation. Now our next question is, in a neural network, you notice that the loss does not decrease in the few starting epochs. So what could be the possible reason for this to happen? Now the correct answer is the reason for this could be the learning rate is low, first of all, or it might be the regularization parameter is high, or it can be it is stuck at local minima, so it might take certain iteration to go out of that local minima and finally reach the lowest point. So it might happen in some cases that it is stuck at local minima. So another approach to that sort of problem must be initiated at that particular point of time. Now, talking about deep learning, one might ask to name you a few deep learning frameworks which are being used in the industry. So first of all, the foremost and the most amazing deep learning library is the TensorFlow. Followed by we have Caffe, we have the Microsoft Cognitive Toolkit, which is the CNTK. We have Torch or PyTorch, which is giving a good battle, or it's standing out from the crowd, and people are sometimes preferring PyTorch over TensorFlow. Now, MXNet is another deep learning framework. We have Chainer and we have Keras. Now, Keras, as you know, can be integrated with Theano as well as TensorFlow, and Keras has been considered one of the best or the simplest deep learning framework when it comes to deep learning. Now, one might ask, what exactly are tensors? So, tensors are nothing but a de facto for representing the data in deep learning. What I meant to say that tensors are just multi-dimensional arrays that allows you to represent the data having higher dimensions. In general, deep learning, you deal with high-dimensional data sets where dimensional refer to the different features present in the data set. So what you need is a multi-dimensional sort of array or a data structure, what you could say. So that's what exactly tensor is. And in fact, the name TensorFlow has been derived from the operations which the neural network perform on tensors. So it's literally a flow of tensor. Now, talking about TensorFlow, one might ask, since it's the most popular deep learning framework and companies prefer people having the knowledge of TensorFlow and been working on it. So what are the few advantages of TensorFlow? So first of all, it has the platform flexibility. It is easily trainable on CPU as well as GPU for distributed computing. Now, TensorFlow has auto differentiation capabilities, and it has advanced support for threads, asynchronous computation, and it is a customizable and open source framework. And most importantly, if we talk about the latest TensorFlow 2.0, which has just been released, so those come up with a lot of interesting features, and it has adopted Keras as its high-level API fully, so that the coding aspect of it is much simplified, and eager execution is now by default, so that you do not have to write loads and loads of line of code. And if you want to know more about TensorFlow 2.0 and why it's the best deep learning framework in the industry right now, just go ahead and check our TensorFlow 2.0 video. I'll leave the link in the description box below. Go check it out, guys, and understand how exactly is it better from the previous version and why it is the best deep learning framework right now. Now, talking about computational graphs, one might ask what exactly they are. So, well, a computational graph is a series of TensorFlow operations arranged as nodes in the graph. Now, each node takes 0 or more tensors as input and produces a tensor as output. Now, basically, one can think of a computational graph as an alternative way of conceptualizing mathematical calculation that take place in a TensorFlow program. Now, the operations assigned to the different nodes of a computational graph can be performed in parallel, thus providing better performance in terms of computation. So, one might ask what exactly is a convolutional neural network? Now, a convolutional neural network, or CNN or ConNet, is a class of deep learning neural networks which is most commonly applied to analyzing the visual imagery. So, CNN use a variation of the multilayer perceptron designed to require minimal processing. Now, one might ask the next question: if you are going for an interview which requires you to work with a lot of images or videos, so in that case, CNNs are very much used. So, having a good knowledge of CNN is always better in that case. So, the next question which we have here is, what are the various layers of CNN? Now, there are 4 layered concepts everyone should understand in convolutional neural networks are: first, the convolution layer; the second is the ReLU layer, and finally we have the pooling layer, and finally we end up with the full connectedness or the full connected layer. Now, if we talk about CNN, we have to talk about RNN also. So one might ask, what exactly is RNN? So RNN, or the recurrent networks, are a type of artificial neural networks which are designed to recognize the patterns in the sequence of data, such as text, genomes, handwriting, the spoken word, numerical time series data from sensors, the stock markets, and the government agencies. So recurrent neural networks use backpropagation algorithm for training, but it is applied for every timestamp. It is commonly known as backpropagation through time, which is BTT. Now, our next question is, what are some issues faced while training an RNN? So, recurrent neural networks use backpropagation algorithm, as I just mentioned, for training, but it is applied for every timestamp. And there are some issues with backpropagation, such as vanishing gradient or the exploding gradient, where the gradient vanishes or it is too much to handle. Which brings us to the next set of questions, the first of which is, what exactly is a vanishing gradient and how is it harmful? Now, when we do backpropagation, that is move backward in the network and calculating gradients of loss, which is the error, with respect to the weights, the gradients tend to get smaller and smaller as we keep on moving backward in the network. Now, this means that the neurons in the earlier layers learn very slowly as compared to the neurons in the later layers in the hierarchy. Now, the earlier layers in the networks are the slowest to train. Now, how is this harmful? So, earlier layers in the neural networks are important because they are responsible to learn and detect the simple patterns and are actually the building blocks of our neural network. Obviously, if they give improper and inaccurate result, then how can we expect the next layer and the complete network to perform nicely and produce the accurate result? So the training process takes too long and the prediction accuracy of the model will decrease. Now, another question here arises is, what exactly is then exploding gradient descent? Now, this is just the opposite of vanishing gradient descent. So exploding gradients are a problem when large error gradients accumulate and result in very large updates to the neural network model weights during training. So the gradients are used during the training to update the network weights, but typically when this process works best is when these weights are small and controlled, when the magnitudes of the gradients accumulate and the unstable network is likely to occur, now which causes a poor prediction and results, or even a model that reports nothing useful whatsoever. So vanishing gradient and the exploding gradient are two problems which occur while the backpropagation happens in a recurrent neural network. So our next question is, what are LSTM? So long short-term memory, which are the LSTM, is an artificial recurrent neural network architecture used in the field of deep learning. And unlike standard feed-forward neural networks, the LSTM has feedback connections that make it a general-purpose computer. Now, it can not only process single data points, but also the entire sequence of data. They are a special kind of RNNs, or the recurrent neural network, which are capable of learning long-term dependencies. Now, one might ask, what are capsules in a capsule neural network? So capsules are vector, or what we can say an element with a size and a direction, specifying the features of the object and its likelihood. Now these features can be any of the instantiation parameters like the pose, we have the position, size, orientation, deformation, velocity, the albedo, which is the light reflection, hue, texture, and much more. A capsule can also specify its attributes like angle and size, so it can represent with the same generic information. Now, just like a neural network has layers of neurons, a capsule network can have layers capsules, so there could be higher capsules representing the group of objects or the capsules below them. Now, this helps in getting deeper knowledge of a particular object or a particular data set and having the knowledge from different aspects or different angles. So the next question arises is explain autoencoders and its uses. So an autoencoder neural networks is an unsupervised machine learning algorithm that applies the backpropagation, setting the target values to be equal to the inputs. So autoencoders are used to reduce the size of our inputs into smaller representation, and if anyone needs the original data, they can reconstruct it from the compressed data. Now one might ask the question, how does autoencoder differ from PCA? So an autoencoder can learn from nonlinear transformation with a nonlinear activation function and multiple layer. It does not have to learn dense layers. It can use convolution layers to learn, which is better for video, image, and series data. It is more efficient to learn several layers with an autoencoder rather than learn one huge transformation with the PCA. An autoencoder provides a representation of each layer as the output and can take the use of pre-trained layers from other models to apply transfer the learning to enhance the encoder or the decoder. So these are few of the reasons why autoencoders are better from PCA, as we know both of them perform the same task, which is mostly dimensionality reduction. Now give some real life examples where autoencoders can be applied. So the first of all, we talk about dimensionality reduction, or the first thing that should pop up in your mind is dimensionality reduction. So the reconstructed image is the same as our input image but with reduced dimensions. Now it helps in providing similar image with reduced pixel value, and it can be used in various areas where we have limited storage or we have limited processing power. So when there is a high input or an image or a data with high dimension or which has higher values, pixel values, it can compress and provide the same image with a lower pixel value. Now, autoencoders are used for converting any black and white picture into a colored image, believe it or not. And depending on what is in the picture, it is possible to tell what the color should be. Now, feature variation, if we talk about feature variation, it attracts only the required features of an image and generates the output by removing any unnecessary noise or unnecessary interruption. And if we talk about denoising image, the input seen by an autoencoder is not the raw input, but a stochastically corrupted version. A denoising autoencoder is thus trained to reconstruct the original input from the noisy version. Now talking about autoencoders, one might ask about the different layers of the autoencoders. So basically an autoencoder consists of three layers, which is the encoder, we have the code, and the decoder. Which brings us to the next question, explain the architecture of an autoencoder. If we talk about the three layers, which are encoder, code, and decoder. So if we talk about encoder, this part of the network compresses the input into a latent space representation. Now the encoder layer encodes the input images as a compressed representation in a reduced dimension, and the compressed image is the distorted version of the original image. Now coming to the middle part, which is the code. So this part of the network represents the compressed input which is fed to the decoder. It is basically the channel. And if we talk about decoder, this layer decodes the encoded image back into the original dimension, and the decoded image is a lossy reconstruction of the original image and it's reconstructed from the latent space representation. Now one might ask what exactly is bottleneck in an autoencoder and why is it used? Now the layer between the encoder and the decoder, that is the code, is also known as bottleneck. So this is a well-designed approach to decide which aspect of the observed data are relevant information and what aspects can be discarded. It does this by balancing two criteria. The first, the compactness of the representation measured as the compressibility, and second, it retains some behaviorally relevant variables from the input. Now, one might ask, are there any variation of autoencoders? Surely there are. So there are convolutional autoencoders, we have sparse autoencoders, we have deep autoencoders, we have contractive autoencoders. All of these autoencoders have a different structure or the different code layer. If we talk about the convolutional autoencoder, we have the convolutional CNN algorithm sort of structure in that particular autoencoder with encoder in one side. We have the convolution layers, the ReLU layer, the pooling layer inside it, and then finally we have the decoding layer. So another question what might pop into the interviewer's mind is, what are deep autoencoders? So the extension of simple autoencoders is a deep autoencoders. The first layer of the deep autoencoders is used for first order features in the raw input. Now the second layer is used for second order features corresponding to the patterns in the appearance of the first order features. So the deeper layers of the deep autoencoders tend to learn even higher order features. So a deep autoencoders is composed of two symmetrical deep belief networks. First 4 or 5 shallow layers representing the encoding half of the net, and the second set of 4 or 5 layers that make up the decoding half. Interesting, right? So another important topic in deep learning are the restricted Boltzmann machines. So one might ask, what exactly is an RBM or restricted Boltzmann machine? So RBM is an undirected graphical model that plays a major role in deep learning framework in recent times. And it is an algorithm which is used for dimensionality reduction. Not only that, it is used for classification, regression, collaborating filtering, feature learning, and topic model. So when we talk about RBM being useful for dimensionality reduction, another question might arise is, how does RBM differ from the autoencoders? So autoencoders is a simple 3-layer neural network where output units are directly connected back to the input units. Typically, the number of hidden units is much less than the number of visible ones. And the task of training is to minimize an error or the reconstruction, that is, find the most efficient compact representation for the input data. So RBM share a similar idea, but it uses stochastic units with particular distribution instead of deterministic distribution. The task of our training is to find out how these two set of variables are actually connected to each other. One aspect that distinguishes RBM from the autoencoders is that it has two biases. The hidden bias helps the RBM produce the activations on the forward pass, while the visible layer biases help the RBM learn the reconstruction on the backward pass. Now, this brings us to the final question of our deep learning interview, is that what are some limitations of deep learning? I bet you weren't thinking of this one, but there are some limitations. So, deep learning usually requires large amounts of training data, and deep neural networks are easily fooled. Now, the success of deep learning are purely imperial. Deep learning algorithms have been criticized as uninterpretable black boxes. Because one important thing about deep learning is that you do not specify what you are looking for, right? The algorithm learns on its own. So that is one of the shortcomings of deep learning, and deep learning thus far has not been well integrated with prior knowledge. So a lot of people still don't feel it as a way to solve their problem, as a way to approach to their problems, because a lot of people don't understand what exactly is deep learning, how it works, how to initialize all of the variables, which are the hyperparameters per se. These all things are some limitations of deep learning as of now, and we hope by the time technology advances, people get to know more about what deep learning is, how artificial intelligence can be achieved through deep learning. They'll be more open to this, and all of these limitations will be laid off. So guys, that's it from my side, and I hope you got to know a lot about deep learning interview questions which might help you in cracking the interviews and landing a great job as data scientists, machine learning engineers, or artificial intelligence engineers, as a matter of fact. And one important thing, what I would like to say is that data scientists' role are somewhat, industry specific, or I would say, if you are working in healthcare, you should know about healthcare industry too, rather than just knowing about the data and the numbers. So if you're working in, suppose, imagery, so you should know about images, you should know what you're dealing with. So a good knowledge of the particular industry which you're working for will also provide you a great advantage over other competitors. And since you know a lot of this stuff with this video, I'm sure you might be able to land a job, a great job in any of these industries.